is Anita Gale. I'm CEO of the National Space Society. It's a pleasure to have you join us for the 2021 International Space Development Conference. All virtual this year, at least we have content for you and programming for you. We hope you enjoy it, and we'll see you next year in Arlington, Virginia. Thank you.
So Steve, thank you for joining us today. On the behalf of the National Space Society and all of our wonderful members, we wanted to present you with this Space Pioneer Award for the Space Pioneer Award for Space Development Investing. So cheers that, and we even spelled your name right. So
that's right. Oh
and so the reason that I think this award is so appropriate was that, you know, they say put your money where your mouth is, and there's a lot of people that talk the talk, but there's few people that walk the walk. Excuse me. There's few people that walk the walk, and so you know, somebody that's willing to stand up, put their money on the table when the going is not clear as to how this is going to work out. So we thought that that was an exemplary thing to do, and you've not only done it once, you've done it many times since then, and so we just wanted to recognize you for that contribution. So on behalf of the membership, give you this award.
It's actually amazing. It's probably the most gorgeous award I've ever received. It's the moon and this representation, and you can play with it. This is amazing. Thank you, Bruce. Thank you to the National Space Society. I'm truly honored. Thank you.
So let me, we were going to do a little Q&A here to try to, since we can't do this in person because of COVID, hopefully next year we can invite you to come and speak in person. But I wanted to just kind of take a little trip down memory lane. And if I'm not mistaken, it was almost exactly 12 years ago that you made your first investment in SpaceX. Could you tell me, you know, what led you to go from not investing in space to, you know, going over the line and deciding, you know, to write the check and invest in space?
It's a great question. And for some context, I've been a space enthusiast and collector, a rocket hobbyist myself for decades prior. In fact, our entire office here is full of Apollo era artifacts.
I can attest to that.
Solar panel behind us. And so one would have thought I had a prepared mind, a predisposition, if you will. And I went at least a decade of not thinking any space-related investment warranted the partners meeting. I mean, I might hear of it, but I wouldn't even bring it in to pitch to the partners until SpaceX. And late 2008 into early 2009, the Falcon 1 was just starting, you know, its shakedown flights, and they had not yet launched a customer payload. And so the simple answer to your question is that SpaceX changed everything, not just for us, but I think for the venture community at large, for entrepreneurial community at large, and for the degree to which innovation is occurring across the planet. Mm-hmm. Obviously, literally, Planet Labs and other companies that followed were partially inspired by the fact that the cost of launch is coming down, innovation is ripe and new, and launch prices are listed on the website for the first time. It's like you can actually put a business plan together, right, and anticipate as an entrepreneur what it might cost to put a different proposal together. So again, prior to SpaceX, not 10 years, nothing of interest. Afterwards, Planet Labs was the next major investment we made. And as many people can attest, the industry investment in space-related companies just exploded. I think it was around 2015 when SpaceX raised $1 billion, Planet Labs raised $100 million, and that alone exceeded all prior years of venture capital investment in space combined times 2.
Right.
It was like a hockey stick, and it's been going up every year since then. So I think the entrepreneurs around the world who are thinking about all kinds of things, from tourism to communications or observation, are beneficiaries of what SpaceX has enabled and has catalyzed, of course, in the landscape, right? It's not as if they're the only company you can launch with, but it certainly has lit a fire under the pants, if you will, of many other companies and governments to rejuvenate their space program and modernize it and make it more accessible.
And so SpaceX has just had 100 launches in a row that were successful, and they've had 85 recoveries of the first stage that were successful. Can you talk about that whole thing of going from an expendable vehicle, cheap and powerful and everything, but from that expendable mindset to the reusable mindset?
Yeah, I don't know if there's a game changer of comparable scope in the world of business history, where people are all doing business a certain way. They're operating in some way. Imagine, again, by analogy, you threw away an airplane after every one-way flight, or every car you bought was, thrown away after it ran out of gas. That would be an entirely different industry. And complete reusability, which Starship should bring, and sort of 80% ballpark reusability, as you have with Falcon 9, is the biggest game changer in launch business, probably, since chemical rockets or liquid fuel propulsion. So it can't be understated. It took, by Elon's estimate, about $1 billion of R&D. So it's not something anyone would undertake, even though now in retrospect, it's the obvious inevitable future. And this is what I love about companies like SpaceX and Tesla, and frankly, a whole bunch of others that we've invested in. Once the entrepreneur proves that it's possible, everyone slowly but surely comes around to realizing, oh my gosh, this is the way it's all going to be going forward. Like, why would you build anything but that going forward? You can imagine you can't compete with disposable rockets if someone's reusing. So I'm not sure everyone in the industry has internalized that, by the way, quite yet.
There's some skeptics out there that are they're being drug kicking and screaming into the future.
Sometimes I feel like I have a sixth sense. I can see dead companies.
Yeah.
Dead companies walking. Yeah, exactly. But I mean, the beneficiary, of course, will be all the other users of this, right? NASA, other companies, what have you. And so reusability, though, here's one little detail that I love. I read an introduction to a book about Virgin Galactic, and it was about Spaceship One. It was written in 2007, and the foreword was by Arthur Clarke. Yeah. And in there, he quotes himself as saying, my gosh, it doesn't actually take that much fuel to get to orbit. Why does it have to cost so much? If you throw away a rocket after each use, like an air, you got to make it more like an airplane, get rid of this missile mentality of single use. The most important thing for a thriving space economy, the next thing we should focus on is reusable boosters, specifically. And so I'm like, wow, that sounds pretty familiar.
Yeah.
And he said this in 2007. And then the jaw dropper is the next line in that introduction says, when I wrote these words in July 1969, Apollo 11 was on its way to the moon. So Arthur Clarke said those exact things in 1969, and it's just been a little bit of a digression from there. We're finally getting back to the most important imperative for the next phase of space exploration. And fully reusability, of course, was motivated by getting back from Mars. That was sort of the star on the horizon, if you will, that motivated the hard engineering effort. No company would have done it if you lived in a comfy world of just launching things to low Earth orbit and geosynchronous orbit. Why would you bother, right, to go through all this effort? If your government is your only customer, or people are willing to pay the amount they were, why would you try to restructure the industry if your prize is just market share of that one niche? Right? If you have something grander, like colonizing Mars as your objective, you have to do things differently.
So one of the interesting things about the new business model that SpaceX and NASA are involved in is that instead of being a straight contractor that you work at the government's behest, that you're doing this actually as a public-private partnership where the government paid part of the cost of developing the system, but not all of the cost. And, SpaceX picked up in excess of 50% of the cost of that. But they also get, at the end of this, to own and operate it. And what that's enabled is now you can sell this to other people, not just to NASA astronauts. And I noticed that you've got signed up a couple of commercial flights. Can you talk about that a little bit, about how do you see that playing into your business plan?
Right. So in the case of SpaceX, this idea of dual use is essential. The idea that there's commercial applications that can drive volume, drive the prices down for the benefit of all, both the commercial users and the government accounts. Of course, having an early government customer can be game changing, as it was for NASA, as it was for SpaceX with NASA. And being that sort of, known fixed price purchaser is invaluable. And it's a very healthy way to build businesses. So stepping back in general, as an investor, we would never invest in a company that depended on contracts that were specific only to a government account, that didn't have the ability to be more of a mass market product. And I think that's true for a lot of investors. And so you can, as you said, leverage more than just what the government's willing to pay, and have a market feedback mechanism that says, is this in fact competitive? Is it the best that can be done? When you have a planned economy like the Soviet Union, you get a lot of things that didn't necessarily make sense. The Buran shuttle, there are many examples. I like to think of, like, would you rather have the Soviet Union model, or would you rather have, the Silicon Valley competitive model? Right. And I think that experiment has been run, and the results are pretty strongly indicative that the competition works. So, whenever an industry's gone through change, where something used to be bespoke, you might imagine the transition is unsettling for those who are used to the old methods. So
Right.
there was a time when custom computers had to be custom ordered for certain applications because you couldn't just buy an off-the-shelf computer that was capable of what you wanted, either in the Apollo era or what have you. But now we wouldn't imagine that NASA should build their own laptops. I mean, we don't even think to question that.
Yeah.
That industry is transitioned to a point of maturity that, where possible, commodity off-the-shelf parts are obviously a better way to go to allow you to push the vanguard in exploration or in areas that aren't, currently being pursued by the market. And there's plenty of those. And our solar system has barely been touched, right?
So the other thing that I thought was just, excuse me. The other thing that I thought was really spectacular was one, Elon basically cannibalized the Falcon 1 to do the Falcon 9.
Mm-hmm.
And now you mentioned Starship and Super Heavy. He's now cannibalizing willing to cannibalize the Falcon 9 and the Falcon Heavy and the Dragon capsule for the Starship and the Super Heavy. Could you talk about that, thing from an investor point of view? All that sunk cost, and now we're going to roll the dice on the next generation.
Mm-hmm. No, that's right. Well, it's interesting. You can look at it one of two ways. It would be inconsistent not to. In other words, if Starship hits its design goals, it is a logical truth that you would no longer fly the Falcon 9 or Falcon Heavy for any mission. In fact, even smaller satellite launches where you're only using part of the payload capacity, because your cost per kilogram, even with, without further utilizing the craft, it just makes it, just like Falcon 1 before it, no longer needed.
Right.
The next vehicle is so much better. So think about what has already happened. It was a bold and difficult decision at the time to shut down Falcon 1, but it was now clear in retrospect, you'd want all those missions on the Falcon 9, reuse the booster, especially in the later days and what have you. I don't know that everyone in the industry has or is forecasting success in their own business plan. No, forecasting success for SpaceX when they're pursuing something that won't ship until years from now, sometimes many years from now, and barely keeps up with Falcon 9 or Falcon Heavy. Realize that another 10x to 100x improvement is around the corner. You got to go where the hockey puck is going, right? And Falcon 9 was, a 2008 to 2009 design, improved dramatically over the subsequent years, but that's not where we are going. That's where we've been.
It's like the guy with the turbocharged buggy whip. It's just really not going to keep up with the evolving technology. And so let's take a step into the future. So Elon has made no bones about that Mars is his destination, but he just won a contract, the Human Landing Systems contract with NASA to deliver cargo and astronauts to the lunar surface. So how does that fit in, and how do you see the rest of this decade kind of unfolding, both for using Starship in Leo, using Starship to go to the moon, and using the Starship to go to Mars?
Well, I'm not sure how much I can add publicly to what's known, but the moon, it's a lovely stepping stone to Mars, and there's a lot of capabilities that you can test and iterate on more rapidly here, right? So your launch windows are frequent. You don't wait for these, 26-month alignment periods for learning, if you will. So everything from habitats to human self-sustainability. In some ways, the moon offers unique challenges with the lack of atmosphere that are, if it works there, it might work on Mars for initial landing party. You can imagine it being a test bed for all kinds of capabilities up and down the chain, right? Because it's not just one company that's going to help make this vision of making humanity a multiplanetary species possible. Like there's habitats, there's food production, there's a lot of things, radiation shielding. You'd like to work on a lot of these things and have, near-term iterative learning. And I guess I've said this twice, let me just back up. That's one of our major investment theses, is to find companies and teams that have a process of learning that's faster than any other company. This is true at Tesla, this is true in other places. If there's some reason why you can run experiments in the course of days or months that others might take years or decades, you're going to win. Whatever winning means. You're going to push the vanguard of progress. You're going to achieve things others thought were unachievable. And that's largely based on your cycle rate of learning. So anything that increases that. So that's why I like the moon personally. And I like anything to be tested in a rapid cycle as a gateway to Mars. Not because you physically need to go there, by the way, to get to Mars. That doesn't make sense. But you just learn things that you will then apply elsewhere.
What some of my colleagues have said is it doesn't, sustainable travel and occupation of Mars, isn't likely to happen until you can regularly and consistently go to the moon, because it's just such a harder problem. So we're running out of time here. So the last question I wanted to ask is, you probably looked at as many space pitches as just about anybody in the world. So what advice would you have for the next generation of entrepreneurs and space enthusiasts as they look at the world that's going to be enabled by not only the Falcon and the Falcon Heavy and the Dragon, but now the Starship and the Super Heavy and whatever comes after that? What advice would you give them as they look to their futures to be able to catch this wave?
Yeah, no, that's so. Some high level advice would be, try to do something that others aren't already doing.
Right.
That feels like maybe obvious, but at times I scratch my head when I see 160 different companies trying to build Falcon 1 equivalent or smaller small sat launch companies with price per kilograms that exceed the market price today. I don't get it. And so, do a Google search, find out if there are over 100 companies doing whatever you're proposing to do, and then do something else. That would be my first piece of advice as a meta level.
Go read Blue Ocean Strategy.
Yeah, exactly. Don't go in the red ocean where the sharks are already feeding on the carcasses of your predecessors. The other is to just imagine what all is enabled by cheaper access, right? So Starlink is a wonderful example of that. You wouldn't imagine tens of thousands of satellites or even thousands of satellites before the cost of access to space came down. Mm-hmm. By analogy to the internet, before there was cheap access to the internet, fiber optic builds, ways to connect, you wouldn't have imagined the cloud services layer or e-commerce or any things that followed. And frankly, where most of the money was made. It wasn't the fiber infrastructure, it was the apps and services riding on top of it. So by analogy, take launch and commodity launch is a given. Multiple launches per day, right? Not just per week or year or month. And what would you do that wasn't possible before? There'll obviously be a lot of things to solve and opportunities to innovate in tourism, in communications, in Earth observation, in exploration. And then, of course, on Moon and Mars, everything else terrestrially, terraforming, the ultimate recycling challenge of reusing as much as you can.
Fixing the Earth,
and learning how to, ideally things that can go both directions.
Right.
How do we make the most of what we have and be sustainable? Because, by the way, you're going to want to be sustainable. If you're trying to do an off-world colony that's not relying on the mothership, by definition, that's a sustainability challenge. So if nothing else, I think, kind of like the pale blue dot, if you will, the blue marble of being this inspiration. In a way, how do we live off the land when we're in space or on Mars?
And the land is far away.
The provocative challenge, right? How do we make that work? And if we make it work there, we might reflect back on how we're so far from that here.
Right.
And like, oh my gosh, our energy sources, they're not sustainable. Why would we accept that for planet Earth? Lifeboat Earth. Why would we pump toxins in the air and avoid obvious clean energy sources and still build more coal plants in the year 2021? More additional coal plants. Why would we do that? And I think at least the zeitgeist, I hope, and the environmental movement will have a second coming, if you will, of enthusiasm based on what we learned from the challenges of doing it elsewhere.
Well, anyway, once again, thank you for your contributions. This award is very much deserved, and we look forward to working with you in the future to make the future all that it can be.
Oh, thank you so much. Appreciate it. Thank you.
Thank you.
Thanks for coming back with us, everybody. I'm very pleased to introduce Dr. Pascal Lee to you. He is the chairman of the Mars Institute, a senior planetary scientist at the SETI Institute, and director of the NASA Houghton Mars Project at the NASA Ames Research Center. Pascal has an ME in geology and geophysics from the University of Paris and a PhD in astronomy and space sciences from Cornell University. So Pascal, I'm humbled to be in your presence. Thanks for joining us today.
Hi, Ross. It's good to be with you again.
So we're going to talk about Mars, and I'll just kick this off by saying if the moon is a harsh mistress, Mars is a tough old SOB. It seems to be a place that wants to forever stay 10 or 20 years out of reach. And the more we discover about it, the tougher it gets in terms of human settlement there. So maybe you could tell us a little bit about that.
Mars to me is still the challenge of the century. Going back to the moon is the immediate tactical step that we have to take. But I think the strategic destination for humanity in space in the 21st century is to achieve Mars. And, of course, a lot of people are working on that and making really good progress. But the rocketry, for instance, is just really one aspect of it, getting there. Once you get there, that's where the problems really start. The thing about Mars is that, it appeals to a lot of people, I think mostly because of its landscape and what it evokes in terms of possibilities. It looks so much like, just a virgin occupiable land, and a place where you can really, reshape and redesign a human future. It's an inspiring place in that regard. And, but the physical reality of Mars is that it's really a godforsaken place that is going to be extremely unforgiving to not just mistakes, but even lapses in technology or mechanical failure. I often explain that, for one thing, in spite of how beautiful the landscape is, there are 5 things that will kill you on Mars if you somehow, walk outside unprotected. And here they are in chronological order of cause of death. The first one is the low atmospheric pressure. You will die of, decompression within seconds. All the oxygen and nitrogen that are dissolved in your bloodstream will boil instantly if you are exposed to the ambient low pressure of the Martian atmosphere. And so you're dead in seconds. If that doesn't kill you, then the carbon dioxide that the atmosphere is made of is a toxic gas for you. You cannot breathe that. Even if it were pure oxygen, there would not be enough of it for you to breathe, but it's made of carbon dioxide, which, every kid knows you shouldn't put a plastic bag around your head. Every kid knows it's a toxic gas. If that doesn't kill you within minutes, which it would, then you have the low temperatures. The temperature on Mars on average, minus 80 degrees Fahrenheit, okay, minus 63 C. That will kill you within a few hours. If a human body were just left standing naked at the surface of Mars, by nightfall, you are frozen to the bone. You are a human popsicle. Now, if that didn't kill you within hours, then the dust is toxic on Mars. We know now that, since Phoenix in particular, that it's replete with peroxides, perchlorates. These are toxic to you. The peroxides, for instance, will attack your thyroid. You are dead within weeks. In the book and the movie The Martian, as much as I enjoyed them as sort of exciting and fun adventures in space, the reality is that Mark Watney would not have survived doing what he did, because he's brought into the habitat tons of Martian dirt to grow potatoes in them. He would have been exposed to this Martian dust, which is bad news for 3 reasons, right? One is it's extremely fine grained, so it's going to clog the pores of your lungs. That's essentially Miner's disease, silicosis. The second thing is that the grains we think are still substantially abrasive because of relatively little erosion on Mars, a bit like lunar regolith, maybe a bit better, but still. So that will tear up the tissues of your lungs. And then the third thing is again this toxicity, this chemical toxicity of the dust. And Mark Watney's would have died within a few weeks, exposed to the Martian dirt like he was, and then the potatoes he would have eaten would have been contaminated. And then finally, the radiation. The radiation, which seems to be the thing that everybody keeps bringing up as if it were, the one thing that we needed to solve, or the main showstopper. But the truth is, the radiation thing is probably the least of your worries on Mars, in the sense that, sure, you want to protect yourself from radiation. It's difficult to do with a spacesuit or habitat. But by burying yourself in sandbags, in particular, your habitat, you're going to cut off, a substantial amount of radiation. And even if you were exposed to radiation, unless you were really there exposed to a solar particle event, like a solar storm event, this will just increase your chances of dying of cancer by a few percent after a few years of exposure. So, you're going to Mars after all. The truth is we are taking much greater risk with astronauts by just the launch alone to Mars, let alone the stay on Mars. And so radiation is really one of those things that keep coming up. I think mainly because there's very little we can do about it, especially in deep space. But other than that, it's hardly the main concern about getting humans to Mars.
When we were young men, the solar system was a friendlier place. When Ray Bradbury wrote the Martian Chronicles, which I know we both read, I remember one story in particular where Sam, I don't remember his last name, builds a hot dog stand at a crossroads of a couple of ancient Martian canals. And he's walking around in street clothes and selling hot dogs, and then gets visited by an ancient Martian, and the story goes on from there. But from the time of Mariner 4 on in the mid-60s, not just Mars, but the whole solar system suddenly became a less friendly place. I think for many decades, hundreds of years really, we sort of assumed that the solar system, the other planets, are sort of like slightly different versions of Earth. Couldn't have been more wrong. So when you talk about how dangerous Mars is, I guess our choices are, as you said, to bury your habitat under a bunch of soil or regolith, or to put it in a cavern, which you've written extensively about, or to try and terraform the planet, which seems to be a very, very long baseline activity, and something that may well take longer than moving on to other solar systems with friendlier worlds in them. So what's your advice for those entrepreneurs?
Yeah, well, don't, in spite of how God-forsaken the place is and how foreboding it is, I'm not deterred to try to get humans there. I think it's absolutely where we need to be going. We need to be going there as soon as possible. And it's going to be a very exciting place to explore. I'm just not on board the idea of having a colony of 1 million living on Mars, because I don't quite see the point of it. And historically, there really isn't that kind of example anyway, although, one could argue that there are reasons why there were no examples of that in the past, and this is now, conceivable. But the point is, I don't see the value of having 1 million people in essentially an intensive care unit on Mars. That's what a life support system is. And so, it's a place you want to visit. It's a place you want to explore. But is it really a place where you want to raise children and have your family there? My personal desire and vision for Mars is that we establish there as soon as we can an international research station. It's sort of the Antarctica model, where we have researchers and technicians who support the exploration mission go to Mars, have tours of duty or rotate different personnel each year or each Mars launch window, and where we're really exploring the place while preserving it as well, a bit like we do in Antarctica, really, okay, and even in parts of the Arctic, where you are exploring the place out of a scientific research station. I also do see a desirable room for tourism, and tourism can go there, a shipload at a time. And I think that would be just like we do for Antarctica, which is actually very good for Antarctica because it raises awareness. It's much better to have organized tourism than people just going off there on their own and doing their own thing. There are ways to go to Antarctica to sort of have a feel for the place. And I do think that, a time will come when, one launch window at a time, there might be a few hundred people going to Mars who can afford it, or either who are really lucky at some lottery, who will take a year off to do that. You can go to the moon in a week. You need about a year off to go to Mars. Okay, so you travel there and then you spend some time at the surface. But where you would go to, in my view, would be something like a bit of a resort of some sort. A combination of resort and something like the dorms that astronomers use when they go up to high mountain observatories. Where there is some facility, there's a gym, there's a swimming pool, there's a few things for you to sort of stay human, but really you're there to do your mission. So I envision a tourism facility actually that would have a swimming pool for one thing, a court for basketball maybe, or volleyball, something that would be really fun in Martian gravity. Swimming pool as well, and the dive boards would be a lot of fun too. In that sense, I can see a sort of a hotel industry on Mars of sorts, appended to the research station, okay, and where people might even go on a train ride to the edge of the canyon and the flanks of the volcanoes. But that's very different from envisioning somehow a self-sustaining human society on Mars, and I'm just not on board that. And this was tried before. Chile and Argentina, for example, in their efforts to claim parts of the Antarctic pie more vigorously in the 60s and 70s, established colonies of their citizens down there. They built housing units and had families move there and encouraged them to have kids. There are kids who are now growing up in Chile and Argentina who were born in Antarctica. But that failed, essentially, because everybody was eventually repatriated, and they learned the hard way that it's not cost effective, nor is it even desirable. You want to taste Mars, you want to experience it for sure, but do you really want to raise kids there in your family? No polar explorer that I know of that I admire, or the Shackletons, the Douglas Mawsons, the Amundsens, none of them wanted to raise their families in Antarctica or at the North Pole. They saw those places as places for either adventure or exploration or science, but they were not, as much as they loved the place, they realized that this was just not the reasonable proposition to turn these places into large settlements of humans. I still see a big future, of course, for humans in space, especially in larger stations and in Earth orbit, and and even in interstellar travel down the road. But this whole occupying Mars thing in a big way, it's not that. I see it as a sort of a world park model, going down the world park model. There will be some people who might live there, several Mars windows at a time. The hardy park ranger, so to speak, or the old hand who will really know the place and know how to survive there will guide the newcomers, and then do maybe a 3 or 4 Mars window rotation. But that's what happens in Antarctica as well. But the notion of having kids growing up there, I don't see that as being something even desirable in the big picture. It's not fair to the kid. They would never have a breath of fresh air. They would never really experience the beauty of the Earth. So I mean, they would be very hard pressed to if they were growing up on Mars.
You could say the same thing about some kids that grow up in parts of New York, but that's a different conversation.
Yes, I do say the same thing about that too. Yeah,
it's interesting. You used some historical citations to talk about why it might not be the best idea. Of course, many other people, as you know, pull out a lot of historical connective tissue about this is why we must go there. And I guess, my reaction to that, and this is on a very simplistic level, is I think part of the appeal of Mars, and you touched on this earlier, is it's a planet, it's a place, it's got a familiar feel to us. It looks like something we can imagine living in because it looks like Utah or parts of the Arctic or what have you. And it's a little harder for some people to picture resettling permanently, if indeed that's a good idea, on the moon or in the moon or in free space colonies, which is, of course, what the NSS is very interested in. Do those make more sense to you as places to go with some permanence than Mars?
Free space colonies, to me, make a lot of sense. You have a much more controlled environment. You can be arbitrarily close to the Earth almost. You really have a plausible historical phasing approach to creating these. And of course the purpose is different. I'm not spending myself a lot of time thinking about large space colonies in Earth orbit because I'm a planetary scientist. I'm interested in the science of Mars, but I actually see that as being the direction in which becoming multi-planet or multi-based in the solar system as the direction to take. I don't see necessarily creating a settlement on Mars being the solution to being a multi-planet species. By having a research base on Mars, which incidentally, we did an estimate, we can probably achieve by at the cost of about $1 trillion. Okay, and I'll get back to that in a second. But the notion of creating a base on Mars, I think, would make us a multi-planet species. If we have a permanently occupied base on Mars that's doing research and exploring the planet, or a couple of bases on different sides of the planet, that would be a human making us a multi-planet species. Whereas going to the moon, of course, it's to the extent that the moon is not a planet by definition, we're not quite multi-planet yet, but the idea is already there anyway with the moon. But going to Mars would ensure that. But that's very different from requiring 1 million people being there and going about their business. Not to mention that there's a huge collateral with having people there living there. Okay, you have to take care of the waste, and we generate a huge amount of waste. Think of our sewer system, of how we dispose of waste. Of course, we would emphasize recycling, but just wastewater, gray water. I mean, that takes, at the very least, a huge infrastructure to process reliably. And meanwhile, we wouldn't want to do that without really, impacting the immediate surroundings of where we live on Mars. There are no oceans, there are no rivers to carry away your light waste. There's no, I mean, it's in the Arctic communities that I visit often when we go to Devon Island in the Arctic. The biggest worry and concern, even now in the winter, is to lose power, even momentarily, in these communities, because the water is going to freeze in all the pipes, in all the lines that are going across the town. It's a big danger. If they freeze, they burst. If they burst, even if the power comes back on, you might not have water anymore. It's a real concern, and this is here on Earth in the Arctic in the 21st century. So, again, it's not that it's technically not feasible. It's just that we're generally underestimating the magnitude of the investment in infrastructure that would be required to sustain a population like this. And before, a population on Mars were productive and from an industry sort of standpoint, so that it could be self-sustaining economically. I really am wondering who would invest that much to create such a colony there. Okay. But again, naysayers are often, don't have a popular view. I tend to view my view as being still optimistic. I do want to see humans go, and I think we have a great future in space as explorers, above all for now. And what we settle, I'm more inclined to believe that we will settle, an exoplanet that's actually habitable, semi-habitable for us, as opposed to a place like Mars. We'll go the greater distance, but we'll get to a place where it's more turnkey. Yeah. Now, as far as the cost is concerned, we've estimated that it would cost to establish a basic little base on Mars, that's an international base on Mars, within the next 25 years, about $1 trillion. And, a lot of people recoil at that number. It sounds like, wow, what a huge cost to taxpayers, But again, $1 trillion over 25 years, that's 40 billion a year. Bearing in mind that NASA's current budget is already 20 billion a year, and the other nations are spending combined, the equivalent of about 10 billion a year as well, collectively. So we're talking about beefing up I would envision beefing up NASA's budget from 20 billion a year to 30 billion a year. People can protest, but that's still well below what we were doing during Apollo.
Oh yeah.
And in terms of equivalent dollars, and then making sure that the international partners contribute at least 10 billion. And so now you're at 40 billion a year. Then we can, within 25 years, have a base on Mars, a research base. Now, it's not claiming that Mars is too expensive, because, just like during the Apollo program, which cost 26 billion of 1960s dollars, during the Apollo program, we spent over the course of 10 years to make Apollo happen, what was spent each year in the Department of Defense's budget, roughly speaking. Okay, so 26 billion at the time of the Vietnam War was about the budget of the Department of Defense. Today, I've got news for people out there if they don't know this, but the annual budget of the Department of Defense is about $1 trillion. It's 978 or something like that $1 billion a year. So we are talking actually about spending 1 year's worth, roughly speaking, of the Department of Defense's budget spread over 25 years to get this base set up. It's actually, if anything, likely to be an underestimate of the cost. So people wanting to go to Mars more cheaply than that are just kidding themselves, because you do want to have a base there. You do want to have some infrastructure. Otherwise, you're not going to be equipped to explore the place, properly. Anyway, then meanwhile, you have Elon's efforts. Okay, Elon, of course, is really into the transportation issue right now, and getting there, of course, is a big part of the issue and the solution as well. But it's not the solution yet. You still have to create the surface systems, the habitats, the mobility systems, the spacesuit. The spacesuit alone. We have a spacesuit right now that weighs about 300 pounds. Okay, the EMU and the Apollo suit weighed about 250 pounds or so. The EMU weighs 300 pounds. Okay, the X-EMU that we're thinking of having for the moon will weigh roughly, again, about 300 pounds. You take that suit to the moon, it weighs 6 times less. So it has a felt weight of 50 pounds. You take that same suit to Mars, it has a felt weight in 0.38 g of 125 pounds. That's not even close to being usable as a suit. We need a suit that weighs literally twice less. Okay, how do you cut the mass of something that is already lean and mean in half? We want the suit to weigh, in reality on Earth, 150 pounds, so that by the time you take it to Mars, it has a felt weight of only 60 pounds. Okay, well, that's a big leap. And in fact, we've been working on this with Collins Aerospace, the NASA's contractor for life support systems and spacesuit life support systems since the Apollo era. We've been working with Collins Aerospace on some solutions to make that possible. And I think we're getting there. The solution, we think, is to offload some of the mass of the portable life support system onto an ATV, a vehicle that would follow you, a smart cart, essentially, that you can drive around. And it carries actually a good load of your life support system. Part of your backpack, think of it that way, is it sort of stays on the vehicle, but the vehicle follows you. So now you're walking around with something a lot more shorter in autonomy and in sort of ability to allow you to walk around without recharging, but at the same time is much more manageable. And then you plug in to recharge your smaller backpack with this, your lighter backpack, I should say, with the supplies that are on the ATV. And so, we're thinking of the human explorer and the ATV as the exploration unit. Not so much the astronaut alone, but it's the astronaut alone and his or her ATV with the portable life support system reserves on it. The ATV being a drivable but also a self-driving smart vehicle following the astronaut. So if you think of that as an exploration unit, now you have something that's a lot more capable to take you around and allow you to be an effective explorer. Anyway, where do we begin?
Well, when do we begin is the question, I guess. You've given us a lot to chew on and think about, and I appreciate it. And for those of you who might want to know more about how, at least some aspects of how settlements on Mars might be worked out, there's an article in the first edition of Ad Astra for 2021 that Pascal and I worked on, talking about the upsides and downsides of lava tubes and lava pits and caves on other worlds. So well worth checking out, along with his website and other resources, which I'll put at the end of this talk. So thank you very much for coming on again. And you'll have to update us in a few months as to what you've been up to.
Thank you so much, Rod. Take care.
Take care.
This was fun.
Hello, my name's Stephen Daire. I'm an NSF Space Ambassador, CEO of Protean Industries, Confers member, SGAC DIA Moonbase author, and Masters of Science and Systems Engineering candidate. Today, I'm here to talk to you about humanity's return to the moon using robotics and aquanautics for astronautics development. As a cave diver, I've worked in numerous environments throughout the world. I've worked on shipwrecks and in open ocean settings. Cave diving has been one of the most primary utilities in my belt in terms of developing new systems and theories using robotics and aquanautics for astronautics. As a cave diver, I have spent numerous hours in underwater caves in Mexico. Through my research and development, I've identified how these experiences can be translated into new potentials for EVA missions on the Moon, Mars, and on the ISS. Science has observed most of the known universe. 13.8 billion years of cosmic background radiation have allowed us to map the universe. Yet, 95% of Earth's oceans remain unexplored. 99% of Earth's caves remain unexplored. 100% of caves on other planetary bodies remain unexplored. As a cave diver, exploring these areas on our own planet provides me insights to be able to connect the dots of how cave diving can promote astronautics research. Underwater caves provide unique research sources and proving grounds to conceive, design, implement, and operate lunar bases for human exploration and the development of space. Much like Sea Lab did 50 years ago, Mars Desert Research and High Seas do today, cave labs will extend the immediate future of humans' possibilities in space. We know too little about our own environment, and we need to be able to play catch up on the learning curve with immediate field research. NASA planetary science, technology, and research analogs allow for engineering and design to push the limits of our capabilities in underwater caves as well as in EVA settings. Analog surveys can also promote new procedural elements and perspectives in human-machine environment interactions in order to complete in situ research and resource production on the moon for moon-based development. Laser scanning in underwater caves on Earth provides real-time planning data to locate natural resources and work towards exploratory missions related to future interests on the Moon and Mars. These ultimately improve human exploration and development of space. Laser scanning assists in real-time planning to locate natural resources, plan exploratory missions, and identify features of interest for future explorations on the Moon and Mars, ultimately improving human exploration and development of space. These in turn promote the capacity to identify resources and potential sites to build a lunar base on the South Pole. Completing long-term, long-duration projects on Earth in underwater caves can promote our successful colonization of the moon by promoting the development of new technologies and procedures for human factors and human systems design. These ultimately allow for human capabilities to be extended beyond traditional survival settings on ISS and shuttle missions. By completing underwater cave research, we can identify ways to complete wear and tear analysis on spacesuits, the ISS, and space shuttles. We can also use them to identify resources for in situ resource utilization. And we can map out the moon to be able to identify the best places to develop moon bases for long-term human habitation.
Hello, I am Tony Paustian, and I am the Director of Branding and Communications for the National Space Society. It is my pleasure today to introduce Dr. David Gallo. David is an oceanographer and explorer who has spent decades leading projects and exhibitions for the Woods Hole Oceanographic Institute. He has appeared on numerous documentaries for the Discovery Channel, History Channel, and National Geographic, and has one of the most viewed TED Talks of all time. He serves on the X Prize Deep Ocean Advisory Board and Jane Cameron's Deep Ocean Task Force. He's led missions to the Titanic and led the mission to successfully find the Air France Flight 447 that crashed into the Atlantic Ocean after others had failed. David is a National Fellow of the Explorers Club and a recipient of the Lowell Thomas Medal for Imagination and Exploration. He's also an elected Fellow of the American Association for the Advancement of Science. It is my pleasure to introduce David Gallo. David, thank you so much for taking your time to join us today.
Hi, Tony, and thanks for such kind words. But at the end of the day, I'm just me. It's
And you are a great guy. I will tell you. I've known you a long time, David, and I really appreciate all the time you give to me and give to us for your busy schedule, because I know you are a busy guy and you're a very, very active guy, because a lot of people reach out to you all the time for your insights. So thank you for taking your short time today to share with us some of your insights related to the oceans and how they relate to space. So let's start with talking about exploration. The oceans are vast. I mean, space is vast, but they are linked. In fact, Jules Verne had written a book, 20,000 Leagues Under the Sea, and then he followed that up later with another book, From Earth to the Moon. Arthur C. Clarke wrote, is famous for writing 2001: A Space Odyssey, but he also wrote The Challenge of the Sea. So talk a bit about the similarities and differences when exploring each of the oceans and space, and what we can learn from the oceans to help us better understand and explore space.
Yeah, I mean, those are very good points, Tony, actually, because I think many of the oceanographers I know got their beginning from Jules Verne, 20,000 Leagues Under the Sea, anyway. And also at the time, if you're old like me, from Jacques Cousteau, the TV show Jacques Cousteau, the undersea world of Jacques Cousteau. I think in both cases, what drives it in many cases is curiosity, and about what might be out there, what's around the next corner, what's on that next rock. And both of those things, I grew up, I was born in 52, I'm 68. I grew up in the age of Apollo. So of course I wanted to be an astronomer or an astronaut. Didn't have the grades to do that, but somehow fell into ocean exploration, which to me was not the same as being out in the backyard with my telescope, but in another way, very gratifying to know that just in our own backyard on this planet, it's full of stuff to discover and understand.
I know that NASA has had an impact, or had a role in exploring the oceans. So can you talk about that a little bit, about NASA's role in that?
Yeah, I think we've always had some sort of relationship with NASA. I mean, oceans got their big kick in after World War and during World War II, about how to find and to hide submarines. So that gave ocean research a big boost forward. But and since those times, we've learned a lot, because we go in the oceans, we go to a very hostile, we used to call it the most hostile place on Earth. I mean, it's debatable now, but deep, dark, incredible pressure, toxic, all that stuff. And in many ways, it's the same thing as space. It's a world, it's hostile to us, but it's also definitely unfamiliar to us, where you never know, again, what you're going to see around the corner. So we've always shared that, because both of them, science depends on observation, and in the oceans and in space, observation depends on technology. And that technology of how to go to a hostile place and explore, we share with NASA.
I know that part of ocean exploration also often involves human beings in tiny little submarines, right?
Yeah.
And I know you spent some time in those subs. Can you talk a little bit about what it's like to work in a tiny space in complete darkness like that?
Yeah. The science in a submarine is very romantic and dramatic. And oddly enough, like with space in many ways, one of the first things we had to explore with was the manned or human-occupied vehicle. In the oceans, we had a submarine, long because of the computer revolution hadn't happened yet. But we did have a way of protecting ourselves from the ocean called a metal sphere. And so we were doing probably the reverse order, the way things should be, which would have been making maps and understanding and then putting a human in. So we're doing things in in the other way around. And there's something about being there. You know, it's not comfortable in the sub. You've got 3 people, a sphere that's 7 feet across. It's uncomfortable. It's hot at the surface. You're sweating like crazy. You go down. The average depth of ocean is about 2 miles. You get down in that world, and it's freezing cold. So your body's going through all these different hot, cold, cramped, can't really stand up. But all that gets blotted out by the excitement of exploration and about actually being there. You know, it's not the best view. You might get a better view from a robot, but what it does to you spiritually and what it does to you internally is something that you're not going to get out of a robot. So still like the old submarine way of doing having a person in the loop important to me.
You know, traveling to Mars takes about 7 months. You know, and I think we have an image that we'll put up with the Elvin that you were in, the small little tiny sub. It's not very big, right? I mean, it is small. It's actually, yeah.
On my screen, it's about that big.
It's actually I think internal space wise smaller than the command module that went to Apollo. So.
I mean, the business part of the sub up in front, right below, that's a diver that's there to make sure the scientific gear is in place before you begin the dive. Right beneath him is a titanium sphere, again, diameter about 7 feet across. The windows, something like that in terms of thickness. So incredibly thick windows and wedge shape. So the pressure of the ocean makes the seal tighter. But the business end of that submarine is that capsule up front to protect you from the pressure of the ocean. So in a way, it's opposite from space because we've got pressure in, not pressure out, and a lot of it, thousands of atmospheres of pressure, where from here to Mars is about 1 atmosphere. From here to the bottom of the oceans, thousands and thousands of atmospheres of pressure.
Well, you know, so you've been in this confined space for a period of time. It takes about 7 months to travel to Mars. And, you know, obviously, yeah, it won't be a huge spacecraft that goes to Mars either, right? I mean, it'll be bigger than this, but it won't be huge just because of the mass and the energy it takes to get it there. So what do you think some of the psychological effects, as well as some of the physical effects, but will be with traveling and working in such a tiny space for such a long time? Because
well, you know, Eldon said thousands of dives now, and offhand, I don't know of any issue where we've had to cancel a dive because of claustrophobia. And, you know, I feel like I'm claustrophobic. I haven't had a dive in a long while, but I've always been claustrophobic. And, you know, that's one of the first things you think about is, can you stand being in that confined space? Because you don't want to freak out. There's not much you can do if you're 3 miles down and you want out. There is no out. So you need to be able to deal with that. But also the idea of being alone, whether it's 1 or 3 people, that you are in this unbelievably strange world by yourself. And so I think aside from what it does to you physiologically and mentally, you know, you have to deal with that whole idea that I'm out here all by myself or with 2 other people. But you know, these are things, you're going places and doing things that probably no one's ever done before. And so it's a, you know, it's a learning experience, the whole thing.
Yeah, I think I think about, you know, the fact that like the ocean, you'll have very little to no direct sunlight inside the spacecraft for extended period of time.
Right.
You're going to be in long hours, rotating shifts. So there's the whole internal clock issue that your internal clock's going to be off.
Right.
In terms of what's happening in life.
Right.
Well, there's no fresh air. I mean, it's all recycled air and filtered air. So you know, you can't get all the contaminants out of that, obviously. But just beyond that, I think coping and stress would be an issue, just because, you know, I think about COVID for crying out loud. I mean, people were going crazy just being forced to stay in their houses more often than not, right?
Yeah, everything in the ocean is slow, really slow. I mean, what I forget off the top of my head what a typical spacecraft, how fast that goes. But a submarine on a good day will go half a mile an hour across the seafloor. So it takes 2.5 hours to get from surface down and back up again. 5-hour commute. So it happens very slowly, but sometimes that is interrupted by fault. I mean, a short circuit in the electronics or something of that nature, and it jars you into reality very quickly. Very quickly.
Well, so I I just try to picture myself because, you know, I mean, I personally like being stranded at home working during COVID because I got a lot done. But at some point, I do like going outside too. And I like a change of scenery. So I would think that that would be a difficult thing to get used to for long periods of time.
Oh, I don't know, Tony, about that. You know, because a 2.5 hour trip to the bottom, you'd say, oh, well, maybe I should take a break. Every time you look out that window, it's pitch black. But if you can turn on the lights for a while or strobe your lights, you're seeing animals and things that are indescribable because you've never been seen before. So if it doesn't have legs and eyes and a body, how do you begin to describe that when you know it's alive? You know, and that so there's always something to see. You almost never get bored from being. I had my thesis research was some of the most boring research ever done on the planet, but it kept me transfixed for months at a time.
Okay. Well, I know robots are also used a lot to explore the ocean, and they're also used to explore deep space because it's just feasible to send human beings there. You know, so what are some of the differences between human and robotic exploration, and how do they impact the outcome? Because I know you were one of the first oceanographers to use a combination of manned subs as robots to map the ocean floor.
Yeah, I mean, that was a Navy project about how do we map a place using multiple. So we had sonars, we had cameras, we had submarines, we had robots. And the idea was to pick a spot in the ocean, in this case, off San Clemente Island, and just how do we bring that back to the surface in a virtual sense? Mm-hmm. So, but I think that the big thing is if I said to you, have you been to a Super Bowl? And you said, sure. And I said, oh, really? That's awesome. Which one? And you said, well, I watched the last one. You know, well, no, you really haven't been to the Super Bowl. And that's the same thing that, you get a better view of the Super Bowl and enjoy it probably better, more comfortable at home, but you're not going to match the emotion of really being there. So I don't think that there's any way on Earth, no pun intended, or space, that a robot's ever going to take that away from actually being in that robot, in that environment. So
right, because we're seeing Perseverance now, on Mars, and pictures are great, but I guarantee it will not be the same as a human being standing there, or the experience of standing there. Right?
No, it is. I think people making a big mistake thinking that. And it's a hotly contested thing now. Why do we have to put money into keeping people alive? A submarine day, a good day is 10 hours. 2 hours down, 2 hours back up, and then the rest exploring at a half mile an hour. And then in the meantime, you got to recharge the batteries and all that stuff up at the surface. Is it really worth that? And my answer is, yeah, it's really worth that. Now, you need both things working together. For instance, for Air France and for Titanic, during the nighttime hours, we put robots in the water, and they were fantastic. So it was a combination of robots and submarines working together to bring that information back up to the surface.
So, speaking of, the deep ocean and being miles deep, there have been a lot of discoveries related to some life forms that have been found down at the bottom of the ocean, where there is absolutely no oxygen, no light. Talk a bit about why NASA has shown some interest in these. And first of all, talk about the life forms themselves, and then talk about why NASA has had some interest in this recently.
Yeah, but it was for the longest time. If you take away these the clouds on the Earth and the water, you find out that the bottom of the ocean's got the most incredible topography on the planet. And pretty much we were sure that once you get below sunlight, you have the big the funny bright lights of the surface, dolphins, whales, and everything, that lovely colored blue. But then you get below that when you're in what we call the twilight zone, where you just can barely start to see things, or lights just fading out, and most of it positively pitch black. So pitch black, no sun. If no sun, no plants, no animals. That's the way we used to think. And here we find this 50,000 mile long mountain range, and we were positive that life wouldn't live there. And at the very least, if there was life, it'd be worms and stuff. So, but instead, geologists that were bumbling around looking at rocks find communities of life that honestly, living where we said there should be no life, they rival the tropical rainforest in terms of diversity and density of animals. So we were absolutely dead wrong about life on this planet. The big key was you don't need sunlight. So we have chemosynthesis. animals living off of chemicals coming out of the Earth, not from the sun down. And then that opens up a whole bunch of different moons of Jupiter. For instance, Europa is a great example, where you have a moon that's actually smaller than our moon, yet has more water on it than Earth. It'd be almost impossible, in my mind anyway, not to have life beneath that the outer icy crust of Europa.
Well, we have a couple images of some life forms that were found at the bottom there. Take us through a couple of these. Like what is this?
Yeah, that's because I'm a geologist, I can call it a jellyfish. I think more accurate, it's called a ctenophore. But the amazing thing is that it's geared to live in that part of the world. Two things. One, it's got, if you're used to fireflies, lightning bugs, these animals make their own light. They mix the same chemicals together that lightning bugs do. And they do that to attract one another, to avoid prey, to find prey. But so that they're making their own lights. They're clear so that it's tough for predators to actually see them in the water. And if you take all the animals like this, small, big, large, little tiny things that look like tiny shrimp, put them on one side on one scale, and across from that put whales, dolphins, whale sharks, all the big animals, whole schools of fish. Those guys, these little guys, it's lopsided. They win by far in terms of biomass. So most of the life in the sea is things like that, these little smaller animals that don't seem like much to us, but hugely important in terms of biomass.
We also got a shot of some tube worms too. So talk about these for a second.
Yeah, here's a very strange animal. They can be 5 to 7 feet long. A lot of them are smaller, but it looks like a worm. And the white is a chitinous, just like your fingernails. The red, the color is a hemoglobin, just like hemoglobin. So it's a blood pigment. No digestive system at all. So they're really just a sack full of bacteria. And that bacteria that lives inside these organisms and these worms loves to eat this kind of hot water coming out of the earth, thermal vents, and turns that into sugars. So bacteria do for larger animals. So it's like a food machine. These things do. So eating things that we think are toxic, turning it into food for larger animals. Incredible looking creatures.
We also have a shot here of some toxic gases coming out of the crust of the ocean. Now, and I think you guys found that there was light that was actually consuming these toxic chemicals, correct?
Light?
Yeah.
Well, one of the questions we have is that I mentioned all the different animals. One spot, 300 species, about 290 never seen before. Octopuses, some fish, some other animals with eyes, really good eyes. Why? And there have been some studies done that said there is a light there at a frequency that we really don't see, like a night light. When you think about it, in the perfectly pitch black world of the deep, animals got to be able to find their way back to food. If it's not all based on sniffing, that there may be these night lights that are lit up all along this mountain range that allows these animals to find their way back to where the food is. But something, again, never predicted. In fact, we bet against it, and we were absolutely dead wrong. And that's one of the beauties about true exploration, is that you go out there not knowing. And it's the sad part in a way about funding today, is that you almost have to predict what you're going to find by exploring, and that's crazy. You should just say, I think I have reason to believe that there's something important here, and then turn that scientist or that team loose. Don't make them tell you what you think they're going to find. So, because we've been wrong every time since.
But now the gas in that photograph, and I think that's like a sulfur and some other things coming out.
Hot water, and we call them black smokers because it's really thick with hydrogen sulfide. Right. Yeah, it would kill us like that. It's that rotten, eggy smell that you find around any kind of hot vents. But that's superheated water at the base of that, where you see the water coming out, the black smoke, which is really water. It's about 700 degrees Fahrenheit. So incredibly hot water. In fact, the first time we measured it from the submarine, it melted the probe. And that's scary because if you can melt a probe, you can melt your way through the porthole of a submarine pretty easily. And more than once, the sub came back to the surface with the skin scorched from backing into one of these things. So it's it's just amazing that you can get water up that high because of the pressure, and that these exist almost all the way along the top of that 50,000 mile long mountain range.
See, I'm amazed that with the pressure that's in the bottom of the ocean, that any life form can even exist down there, because I would think the pressure would crush it. That really does amaze me, because I know that.
Well, watch what I got here, Tony, for you. So, the ocean could take a ship like the Titanic, if that was the Titanic, and do that easily. Rip the Titanic, at least the stern, ripped it up like confetti because of the amount of pressure. And you're talking about, you do the depth in feet, divide by 2, that's PSI. But if you put an object on the sub that you treat the oceans with respect, often we put styrofoam cups on the outside, which are basically, mostly air. And then as this goes down outside the sub, the ocean slowly squeezes the air out of it. And at the end of the dive, you end up with this. Okay? So that's one of these that began its life like this, went to the bottom, and ends up like that. And look at that. I mean, the ocean does a really good job at what we call hydrostatic pressure, squeezing this from every different direction in a way at the same amount. So it preserves the shape. So, there's these animals, that's where they live. We think they're extremophiles because they live in this very strange world. But we're the idiots that decided to come out of the ocean, where we have all sorts of climate change and floods and droughts and hurricanes and all sorts of diseases and stuff. We would have been a lot better. We're the extremophiles. These animals were smart enough to stay where they began.
Well, I know that NASA is funding a lot of research now to the at the bottom of the oceans, because I do think there's a belief that like you mentioned before, that if these life forms can exist in the harsh climates of Earth, where there's no light, no oxygen, high pressures, whatever, that they could very easily exist at the bottom of these,
I promise, Tony, that you'll see in the next few years that we'll start to get some evidence that there's life. You need the cookie dough of life, and almost every object in the solar system has that, because we come out of the same supernova. You need water, and we got that. Most people, we used to think water was scarce. Apparently not that scarce. And then we need the energy source, which we thought had to be the sun, and now we realize that it could be the planet itself, coming from deep. I used to, right across the street from me, 100 meters that way, Anita Williams, shuttle astronaut, by just par excellence. That's her mom's home. So I would always get a chance to sit with Anita and talk a couple times from the shuttle. And amazing, her stories. I love listening to their observations from space about life on Earth, and she can see from there the oceans. You can see all the blue of this planet that's covered with water. So
let's talk about water for a minute. A number back in the 70s, we lost meters, and about when the voyage was 4 billion miles from Earth, it turned around to Earth. Carl-Sagan called it the pale blue dot, and it's pale blue because of the water on the Earth. The oceans cover, I think, about 70% of the planet. Yeah. But I know that you talked a lot about this. There's a lot less water on Earth than we think there is, regardless of how it's in space, right? And so talk about the amount of water.
I'm going to pull a fast one on you, Tony, because I didn't.
And we have an image I think we can pull up and show as well to kind of help you talk about.
I'm going to go one step better than that.
Okay.
So on Earth, there's the Earth on the left. If you take all the water off the Earth, you get that the big blob on the right. But let me show you it this way. So here's the Earth, a globe. You see that globe?
Yeah.
No ocean on it, but 70% covered with water. Let's see the Pacific. If you take all the water off this planet, that's it right there. Okay, that's it. So hard to believe that to make the oceans, you've got to take this little ping pong ball size water and sprinkle it on this planet. That's because, I said that the oceans had to be, on average, were 2 miles thick But the distance from California to Asia is about 3,000 plus miles. Same thing across the Atlantic. You're talking about thousands of miles this way by 2 miles that way. So it's thinner than frost on a mug, So there's really not, we're fooled because we see all that blue, but in reality, there's hardly any water on the free water on the planet at all. So what we have is precious.
On the image you showed there, so we have the Earth without water. We have all the water pulled off into that ping pong ball from like the basketball size Earth.
Yeah,
little tiny. You can see a little teeny tiny blue dot beyond that, and that's actually the fresh water, correct?
That's it. That's all the lakes, all the rivers, all the streams. So that little bit of fresh water has got to go in just the right places in just the right amounts at just the right time of year, or civilization gets really upset. And the times that there have been major civilization collapses, it's because we couldn't predict where that water ends up. And, and then that's our big trouble is not so much things changing as it is being able to not being able to predict that change about what's coming next. That's where we always get in trouble. So when you're looking at that little, that's how sensitive the system is. That you've got this tiny little sprig of water, you're asking for trouble. So it really behooves us to understand oceans on this planet. Look, hey, it's every other breath of fresh you take air, of fresh air you take. The oxygen comes out of the sea. Every other breath of fresh air, oxygen comes out of the water. Most of the water you drink, 98+% from evaporation comes out of the ocean. That's ocean too. And the food we eat, about 2 billion plus people count on the oceans for protein. So the air we breathe, the food we eat, the water we drink, all tied into the ocean. And to date, we've explored about 5, 6, 7% of what's out there. And that is just explored. That doesn't mean we understand it. It just means that we've been there and had a look around. So we're behind the 8 ball, and we need to catch up on our own planet. And I'm not saying take anything away from space exploration. That's equally as important. But we do have to figure out what's going on here on this planet.
Yeah, I mean, we often take water for granted on this planet, and
yeah.
And we have such a fragile ecosystem. And when you consider that our planet is what it is and how far it is away from the sun, which puts it in that we call the Goldilocks zone, and our sun is a pretty stable star. And I know that the Keck Observatory and the Kepler spacecraft have photographed or found exoplanets orbiting stars all over the place. But many of those stars are not that stable. So what we really have here is very unique, and it is very special. And I know that you've talked a lot in the years since I first met you about how we've learned so much of our oceans here on the Earth just because of our work in space.
It's true. Well, without space, that idea, that image that we have of the Earth from space, looking back at the planet on route to and from the moon, is incredible because people just take it for granted that, we turned around, we took a photo. The amount of technology that went into that, the man hours or human hours that went into that, that allowed us to take that photo. That's one thing, incredible. But two, what it means that as a society, as a species, to be able to have that kind of information. Now, it doesn't mean we understand the Earth, but the idea that we can see it all at once, again, like being there in person at a sporting event, it does a lot to us spiritually. That's the view we can turn around and look at home. On the other hand, we do learn an awful lot from space that NASA, you can't see into the water. Water's opaque to electromagnetics and things like that. So you can't really see into the water, but we can see the surface and things like moving heat around and weather patterns and all that. We can get out of that view from space.
Well, I know that water is always the big conversation point when it comes to space settlement and exploration. We talk about going to the moon, and there's a lot of discussion about the water they found on the moon, and how that can be converted into fuel and used for survival on that body. And it is very important that we understand our own water in our own planet and how we utilize water, how water is created and recycled throughout our system.
Yeah.
So yeah,
we're getting in a big mess. Actually, we're using up water at record amounts. We're polluting what we've got. What we're not doing is managing really well. And I'll tell you, there's in the Great Lakes or Lake Baikal, for instance, 20% of the world's fresh water is in Lake Baikal. 20% in one lake. 20% of the water is in the Great Lakes. So between the two, you're looking at almost half the water on the planet is in two different lake systems. And, it behooves us to really understand better about how to manage that kind of, it's not getting better. I'll put it that way. The water situation is not getting better. It's getting worse. And in many ways, getting worse faster than we ever thought it would be. So, we're focused a lot on the temperature for climate change, but really we need to focus just as much, maybe more in some cases, on what's going on with the world's fresh water supply.
Well, David, we're about at our time, so I want to thank you for taking your time to participate with us this year in ISDC. Any final words before we call it a day here?
No, I just thank you for the opportunity to talk to you and the group. And, Tony, anytime, and I do mean this, everything you do is a class act. So anytime you ask, I always say yes, without probably a big mistake on my part. But I would say yes with anything you do. So I really appreciate it.
Well, thank you, David, and I appreciate it, and we all appreciate it. So with that, we'll conclude, and thank you very much.
You're very welcome. Take care.
Hi, my name is Anita Gale. I'm currently the CEO of the National Space Society. I'm here today with Greg Autry, who's a member of the board of directors of the National Space Society. We're going to chat about some of the things he's been doing. So, Greg, do you want to say anything about yourself? Just a little bit of introduction.
I'm the space jack of all trades. I teach space. Now I'm excited to be at the Thunderbird School of Global Management, Arizona State University, part of a really broad space ecosystem that is building at ASU, and I'll be teaching in LA in a program of space leadership, policy, and business aimed at executives and folks who want to join the executive ranks of the commercial space industry. I have been a tech entrepreneur and startup founder, and I have had the honor of serving in government, specifically at NASA on the transition team and as the White House liaison. And regrettably last year, although I was nominated to be CFO at NASA, I suffered the politics of hashtag 2020, and the Senate never got around to holding a vote on that confirmation. But in all this time, I've always been an activist for space as a cause for humanity globally and for the benefit of our nation economically.
So what inspired your interest in space?
Honestly, this is probably classic for folks of my generation, but it was Buzz and Neil on the moon when I was 6. I came from kind of a dysfunctional family household, and that was an outlet for me. It was amazing to see these people doing something so bold and astounding in a way that seemed methodical and organized, and again, for the benefit of all mankind, literally. That just appealed to me, and I took it to heart. And if there had been opportunities for a lot of jobs in the space industry when I graduated, I think I would have gone there. But like a lot of people of my era, we saw that there was kind of a downturn in space in the late 70s, early 80s, and we ended up in the software and computing industry, which is what I did. But I remember my peers going to things like the West Coast Computer Fair and talking to the other computer nerds. And we said, you know, if we made millions of dollars like these guys over there, and that was Bill Gates and Steve Jobs, what would we do? Well, we would found a private space program. We all agreed on that. And thank God some of those people did, and I'm happy to have moved over with them into the space domain.
So when I was 6, it was Sputnik. I'm a little bit more.
No comment. But, that was great too.
After I graduated, just after I graduated from high school and before I went into college. So you alluded to a successful career in technology. Why did you transition to teaching and political advocacy?
Because I think, as Henry Ford said, if a business has no other purpose than making money, that's not much of a business. And so I really felt that I wanted to change the world for the better before I left. And I didn't think coming out with the latest piece of technological gizmo or app was really making a dent in the universe. Like Steve Jobs used to say, I wanted to make a literal dent in the universe. So I began to research the commercial space context in 2003, back when it wasn't cool. And I remember my faculty peers looking at me like I was nuts for doing that. I said, "No, there's this Elon guy. You're going to hear about him, right?" And then I started knocking on doors in Congress. I paid my own way, and I'd walk through the Rayburn building in DC and talk to members and staffers about the benefits of space for our country. And I got hooked on it.
Wow. So is there anything else you wanted to tell us about your role as professor of space leadership, policy, and business at the Thunderbird School of Global Management at ASU?
Yeah, first of all, it's international, so I'm excited about that. The school has always been an international outreach. Thunderbird was founded by U.S. Army Air Corps officers on Thunderbird Air Force Base in Glendale, Arizona. After World War II, they felt that America needed leadership in the new global trade domain that was going to emerge in the 20th century, and they were right. So I'm excited by that. I'm excited about the folks I work with at ASU. Lindy Elkins-Tanton is the PI on NASA's Psyche probe, and she's VP of the Interplanetary Institute there. Jim Bell, who just finished up as president of the Planetary Society, is at the New Space Center at ASU, and I'm excited to be working with him. So it's a great great place to be, and we hope to see a lot of NSS members perhaps coming in our door as students soon.
And it sounds like they let you stay in Southern California.
They did, so I couldn't beat that. And I do get to go to Phoenix to teach. They've got locations in London. I just opened one in Dubai, where I'll be in October for IAC. So I'm excited about that.
Great. You work with both the National Space Society and the Beyond Earth Institute. At USC, you hosted the Mars Society and the Moon Village Association as well. What role do you see these nonprofit advocacy organizations playing in shaping humanity's future, and how can they improve?
Yeah, that's a great question. And I wouldn't have joined NSS, of course, if I didn't think that they didn't have power, and they did. I'll tell you, as a high school student, the first political action I took was joining the L5 Society and fighting against the Moon Treaty, which at that time threatened to make some international agreements that sounded like a good idea, but in reality would have held back our development of the space domain significantly by decommercializing it, essentially. So that inspired me, and we can make a true difference. NSS or its predecessor, L5, really is the cause behind that. Like I mentioned, I'm excited to be working with Jim and the Planetary Society. I've always admired Bob Zubrin over at Mars Society, and what Moon Village is doing is great. We need this broad community. Each of these organizations has kind of their specific angle, but we all, I think, share the same vision that God or nature made a vast domain out there, and it isn't for us to sit here and look up at some sparkly stars and say, "Isn't that pretty?" There's a bigger purpose out there, and we need to fulfill it. And the members of the National Space Society are in the vanguard of that.
You need to make some new stars out there.
There we go.
Yeah. So you have the ears of some very influential people in NASA and the U.S. government. Would you tell us a little bit more about how that happened?
Well, the first thing I tell my students is network, and then when you have any spare time, network. Don't be afraid to approach people, and if you have good ideas, put them forward. Of course, make sure that they are good ideas and carefully vet them. Don't waste anybody's time. But in the space community, I have to say, whether that's at businesses or top government officials or folks at NASA, there's an interest in listening to what people have to say that is different than just about any other domain. So no, honestly, I started studying the commercial space domain, and I reached out to people and connected with them. I connected with Elon and Richard Branson and got to spend time talking to these individuals about their passion, and more importantly, the people that work for them, like Gwen Shotwell and George Whitesides, who did a lot of the actual work on these programs, and they were always very open to ideas. It just so happened then that 4 years ago, when the incoming previous president needed commercial people on the space policy team, I got added onto that team because of my work. And again, I found that although we didn't agree on everything, we came to a lot of agreements, like returning to the moon, which is part of the Artemis program now, and advocating for Space Force. And I'm excited to say the new administration has kept those things. Artemis, Space Force are proceeding, and I found the voices of folks like Pam Melroy and Bobby Alal and in NASA under the Biden team to be very receptive to honest suggestions.
So you've done something that most of us will never come near doing. You mentioned that you were interviewed for CFO of NASA. That didn't happen, but that means you were questioned by U.S. senators.
Yeah, and I had my 15 minutes of fame there, and I made a point, I think, of trying to advocate for space, because by that time, unfortunately, my hearing was scheduled after the kind of toxic election we had in 2020. I felt it was pretty clear I might not get a vote, but I wanted to go make a stand for what we were all about. So if you get a chance to watch that video, I hope you like what I had to say there. But before that, what was really amazing is I spent a lot of time in online meetings like this with senators and with their staffers and with everybody of influence at NASA, all the mission directorate leaders and people from the centers, talking about everything that was going on. And it was both highly informative and a chance for me to get some of those ideas I wanted out there. And I can tell you, I'm very impressed with the people running these things. It'll be okay. And even on the political side, it looks ugly. on television, but when you speak to these people directly, whether they're senators or their staffers, there is a strong desire to do the right thing within the constraints of what it takes to get reelected and appease their constituents and donors. But they're doing the right thing, and a lot of smart people are working hard for us.
Good. We appreciate your perspective on that. If there are people in our audience who have aspirations to become influencers for space policy, like you, what advice would you give them?
Yeah, the first thing is do your research, right? So I spent almost 20 years researching the commercial space industry, 15 years of that before I went to do anything for the government. So learn the domain, talk to the real people. And this isn't just going on Twitter and having 144 character arguments about what's right or wrong. And don't be a fanboy, okay? I love some of the individuals out there who have made space exciting recently and the companies they founded, but it isn't an either or, black or white. There are people across the domain in traditional and commercial space working hard to move this vision forward. There are people around the world, even in countries that don't agree with mine, that I know are doing great things. I have a phone case with a picture of Yuri Gagarin on. In fact, I own this Simon Krieger original print. I can't really turn my webcam around, but it's on the wall, the actual oil painting. And, that means a lot to me because regardless of what the relationship is right now between the United States and Russia, what they achieved at that time, as you mentioned, with Sputnik and then with Gagarin, was magnificent. And we all owe them a credit for that.
So with the growing aspirations and capabilities of commercial companies in space, how do you see NASA's role in the future?
Yeah, NASA needs to continue to push the envelope. This is super important that they don't dwell on the details and they don't try to do things that have already been done over and over again. So it's why we felt it was important that we return to the moon and do what NASA could do to help be an anchor customer and a technology developer for things like human landing systems and help companies develop multiple lift vehicles so that we can have technical redundancy and economic competition. I've been adamant about that. You've got to have multiple companies fulfilling launch, fulfilling transportation, fulfilling landing. We've got to do an ISRU, but you need multiple companies so you get a competitive environment. Then once that's working, NASA moves on to Mars, moves on to broader robotic studies in our solar system. And I think that the leadership gets that. I think even Congress gets that. And so I'm confident that NASA will continue to be very relevant going forward.
Yeah, I agree with you entirely. NASA being a good customer, multiple commercial companies providing services, and NASA doing the things that the old NACA did back in the aircraft days, doing the hard stuff that can benefit everyone, like developing the characteristics of wing sections. Okay, let's get a little bit too nerdy. Sorry.
No, but you're right. And too many of, I would say, my good libertarian friends are under the impression that government can never do anything helpful in an economy. And that's just nonsense. The internet was developed by the government. Spaceflight was developed by the government. Nuclear power was developed by the government. Solar power was essentially made real by NASA, first of all, and then later government. These are all benefits back to us when it's done right. That doesn't mean that there aren't boondoggles out there and money pits. But you're right. When there are things that need to be de-risked for industry and things like nuclear space propulsion. Who's going to do that? That is not going to be done by some startup. Okay, that's going to be done by the folks at Huntsville, and we need to get on it.
Amen. So, Greg, we're actually here because National Space Society has sent you a new piece of decoration for your office. And what if you show that to us? There it is. So that is the 2021 Space Activist of the Year Award that is being awarded to Greg Autry right now. And from the discussion, you understand why he earned that award. Yeah, it does come apart.
I love this awesome metallic moon. It is so cool, and I want to thank everybody so much. I couldn't be more pleased than to be recognized by NSS for this work that I've been doing, and it'll just inspire me to keep doing it, and I hope it'll inspire whoever next year's winner is to do some great things as well.
All right. Thank you so much. Enjoy that. I have one of those myself. It's for an educator award from a few years ago, and it's a wonderful addition to your office. So, and thank you for continuing to do the wonderful things you do with influencing and activism and all that kind of wonderful good stuff. Thank you. And keep working with us as a board member.
I'll keep being tenacious and difficult because that's what sparks change.
I like difficult. That's good. Thank you. Thank you so much. Appreciate it, Greg.
Thank you very much for the invitation to the International Space Development Conference. My name is Sandra Häublich-Meusburger and I teach and research at the Technical University in Vienna. Today, we are happy to show you and introduce our Space Architecture Design Studio program that we have developed at the TUV in the last few years. And I will do this in dialogue with Sabrina Kerber. And you will also see a project from her. Thank you, Sabrina, for joining me today.
Hi, thanks for having me today. So I'm a graduate from the TU Space Architecture program and now working as a UAV pilot and analog astronaut. And today we will tell you why space architecture education matters. Next slide, please.
So the Department Building Construction Design at the TU Wien has a clear focus on construction, materials and technical integration, and we also have a regular studio in Europe on space architecture. On the table you can see, I'm sorry, here should be the video. So I make a pause and I'm just saying the text to the video. My department, Building, Construction and Design at the TU Wien, has a clear focus on construction, materials and technical integration. And next to regular design studios, we also offer a unique space architecture studio at the TU Vienna. This is a video of the final exhibition and panel discussion that was followed the design studio of the topic of the Moon Village. You will see a few projects of this later. As usual, the studio starts with intensive preparation because the master students in architecture usually have to get to know all the particular physical conditions of the moon, and all the conditions outside of the Earth are new to the students. So on the table you can see a number of models that are important part of our teaching strategy. We mix all kinds of methods, models, sketching ideas and drawing technical plans is all important and round up the portfolio of an architect. The presentation was connected to a public discussion with lunar experts, including people from ESA, also a cosmonaut and some scientists. And the principal idea of this particular design studio on the Moon Village foresaw to create facilities for a united Moon Village. So this was different because usually students work on their own project, but because we worked on the Moon Village project, all the students had neighbors, which had an interesting effect. The Moon Village brought new topics to the fore. So in this slide, on this image, you see the project of an astronaut training center on the moon. So in addition to the usual suspects like lunar rovers, research labs and habitats, we have a whole new load of new facilities and new typologies that the lunar base and the moon villages needed.
So the campus itself consists of the training and workshop areas, but also living areas, sport facilities, virtual reality training, everything for learning new skills. So the living on the moon, living together in those specific spatial conditions is considered to be part of the training itself. But let's move on to the next slide and have a look at a different project.
So this is another innovative idea for a mobile rover type habitat. Mobility is important, especially in the first phase of a moon village. This project is called Sundial Explorer because it's a mobile rover type habitat that moves and follows the sun. It moves along an elliptical path between the equatorial regions where there is water and other volatiles that are needed for life support, and connects the resources with the habitation.
I think it's especially worth mentioning how this design plays with the resources that can be found on the moon. In this case, of course, with the sunlight. So using in situ resources from the lunar environment was a key to many of the designs developed during this Moon Village design studio. This reached from using the ice water in the polar cold traps over using the shielding qualities of the lunar regolith, or even using in situ created waste products in the design.
Thank you, Sabrina. Resources of all kinds are necessary and an important resource. There is a famous saying from Buckminster Fuller that waste is, oh, sorry, next slide, please. There is a famous saying from Buckminster Fuller that waste is only resources that we haven't yet learned to use. So this is an important aspect of any extraterrestrial habitat, and for sure for a facility on the moon. All resources are used as long as possible and for many reasons as possible. This image shows a 3D printing lab integrated in an underground habitat, and Sabrina was the designer, or one of the designers of that.
Yes, so the project itself focuses on harvesting the ice water that we can find in the lunar craters and using it to sustain a lunar base inside one of the moon's lava tubes. So a human crew is working closely together with all kinds of robotic applications, both in the construction but also in the habitation phase. So if correctly processed, the ice water can support robotics, human, and also plant life.
Next, please.
Next slide, please.
Indeed. Resources are important, so is fresh food. And with the food that the astronauts and inhabitants need to eat, also nature is most important. Because many things are not there, meaning they are the moon yet. So those have to be substituted. This project is called the Tube of Eden, and it combines the necessary needs for the production of food that is necessary for living, for surviving, with the cultural features of cooking and living as a pleasant social activity. It is also a project that creates a research facility that offers on the one side the research growing plants with fungi and algae, and also includes insects. It also offers the recycling of the food products, but at the same time establishes a life-friendly environment for temporary visits for all Moon Village citizens.
It is also meant to encourage the inhabitants to exercise physically. It creates a certain sense of wideness in a very enclosed structure. So in addition, specific windows to the outside allow views of the moon and of space. Next slide, please.
Here you can see an outer view of this Tube of Eden, and it's always important, another important issue is to plan for future development. So it will start with one element and then continue to 3-4 elements until it forms the ring. And from the research facility itself, it would progress to a mare garden with attached production units, and thus turn eventually into a fancy lunar restaurant. Next image, please. The integration of a greenhouse into the living situation and even into the habitat itself was also an important aspect in Sabrina's diploma.
So the diploma project that I did last year is the design for a lunar base for different crew situations. And one important aspect here was the integration of greenery, both to support the crew's dietary needs, but also to kind of leverage the psychological benefits that plants can have in such an isolated environment. Therefore, the design includes a large greenhouse that serves the sole purpose of growing food and is a highly restricted area. But the design also includes green walls in, for example, common areas inside the main part of the habitat to allow for crew interactions with the plants on a daily basis. Next slide, please.
So the question is, why space architecture? Why do we, I think, Sabrina, it would be interesting for the audience to hear from you, because you have done 2 projects at the TU Vienna, all related to the lunar base design, the last one for the Moon Village and your diploma. So I think it would be interesting, why did you choose this space architecture studio in the curriculum of architecture, and what do you think is the benefit for an architect?
Yeah, so when I heard about the possibility to do this, I was immediately fascinated, and I think it was a really good choice for me. So I learned to look at architecture from a completely new perspective, both in a terrestrial and extraterrestrial setting. We can learn so much from space and from designing in isolated environments. The space architecture, or also the moon architecture program at TU Vienna, taught me to not only design space habitats, but also how to use this approach that I learned to improve what I design on Earth. It taught me about new materials and how to use them, how to sustainably design for small spaces or for very isolated situations. And I think that's a topic that is very, very up to date and important, especially nowadays.
And now that we are in this moon architecture session, why do you think, first question is, why do you think space architecture, or what you have you experienced, is so important for the skills or developing skills or as an architect? And what relevance has the moon architecture with the current development?
I think the main relevance that it has is that it allows us to see architecture from a different angle, and to give us a new understanding of spatial and technical needs. So it teaches us to really listen to the environment that we build in and to find customized solutions, as opposed to just reusing the existing concepts. And I think especially in times like these, where architectural needs are changing really, really quickly, it's important to not just recycle concepts that we already have, but to find new solutions for more and more extreme environments.
And now people will probably think, but space architects, are there jobs for space architects? What shall a space architects do? There is already the ISS on orbit. What is the future outlook? How can you contribute?
Yeah, there are definitely a lot of jobs for for people with an education in space architecture that does not necessarily have to be per se designing habitats for space. It could also be designing analog facilities, for example, or anything actually in the aerospace or aviation sector. So space architecture education really opens up a broad field of possibilities. Personally, I'm working as a UAV pilot at the moment, but also as a space architect for an organization that's doing analog missions. So it's a very, very good mix out of doing design, but also more applied engineering on Earth.
And may I ask you, what is your path in the next 10 years? How do you think you can contribute with your abilities to...
So, well, in the future, I would definitely like to go on working maybe for the European Space Agency, because I think this is the best platform to really help kind of improve not only the way we live or explore in space, but also the way we live on Earth nowadays. So whatever we design as a space architect, whatever we come up with, all of the new concepts that we develop, they can go a long way to help us improve life on Earth. And I think that's a very worthwhile task for any architect.
Okay, thank you. I think we can say thank you to the audience. Before we say goodbye, I would like to put your focus on our online publications from the studio. It's on eso.com, it's freely available, and it might help you find your own way to your space architecture pathway. Thank you very much, and thank you for having us.
Thank you so much.
Hi, I'm Jim Plaxco, a National Space Society Space Ambassador, the economic subject matter expert for the Space Ambassadors Program, and president of the Chicago Society for Space Studies. As a space ambassador, the focus of my presentations is on the economic issues associated with space development. We live in a universe of limited resources, particularly limited capital and limited human resources. And we have a large range of interests and activities that are competing for the use of these resources. Economics is about how we deal with the allocation of the resources we have at our disposal, with the objective being to maximize the benefits or utility that we can get from the use of our resources. On the whole, the economic rules that determine the success or failure of any Earth-based project are going to be equally applicable to our space-based projects. For example, in my presentation, The Globalization of the Solar System, I examine the economic factors that have driven globalization and extend those concepts to a human civilization that spans the solar system. Of the relevant factors, the one representing the greatest challenge is that of transportation. One thing should be clear, and that is that economic incentives matter. Last year, I was on a team that submitted a design to the 2020 Mars City-State Design Competition. Designing our Martian economy proved to be the most challenging and controversial aspect of our work. I took serious exception to the numerous economic disincentives that were put in place, like, for example, banning the private ownership of land. In fact, I was so dismayed that I gave a presentation on this subject at a NSS Space Forum earlier this year. Also, last year, I had the good fortune to speak at the Lunar Development Conference on the subject of the economic sustainability of a cislunar economy. The degree to which a lunar economy can succeed will depend not just on the economic incentives that are in place, but also on the identification of markets for lunar products, with markets that are large enough to financially support lunar infrastructure and its expansion. The bottom line is that in order for space-based activities to succeed, we need to be sure that the regulatory environment we put in place incentivizes both investment and innovation. Space, like life, is a game of inches. And policymakers need to understand that the rules they put in place can make or break our efforts to extend humanity's presence beyond the surface of the Earth. The main reason that I am an NSS Space Ambassador is that I want to see humanity succeed with our efforts to develop the space frontier. And I hope that you will support our efforts to make humanity a multi-planetary species. Thank you.
Hello, my name is Pekka Janhunen, and my topic today is a Ceres megasatellite idea, an idea how to settle the solar system in a particular new mode using Ceres as the source body and putting the settlement orbiting the dwarf planet Ceres. Next slide, please. The problem with Mars settlements is that it has low gravity. The problem with O'Neill cylinders is that each cylinder is an island, so it's a non-trivial problem how to travel between them. So let's look back a little bit and think what is a really good living environment for human beings. So a really good living environment should be Earth-like. I mean, radiation level, atmosphere, gravity, day length, insolation, reasonable population density, not too high, and interconnected world so that travel is possible between all parts of this world. But since we are allowed to hope, then it would also be nice if this new kind of environment would be better than Earth, in the sense that there would not be any adverse weather, no natural disasters like volcanoes or earthquakes, and it would also not be limited by Earth's surface area. And last but not least, this settlement or environment should be long-term sustainable, meaning that all atoms should circulate. So how to meet these requirements? So the idea is simply to take several O'Neill-type cylinders, attach them to a rigid frame, which we call the megasatellite. This megasatellite frame itself is lightweight because it is in microgravity. And to attach these rotating cylinders to this kind of frame is not so complicated technically, because the bearings can be of the magnetic type, so there is no physical touch between these bodies, so there is no physical wear. And then there is the question of the source body. So one could use any of the asteroids, for example, but in this work we are considering Ceres, the dwarf planet Ceres, as the best source, as potentially the best source body in the solar system, because Ceres has nitrogen, which is a necessary ingredient for the habitat atmospheres, and it also has all the other necessary elements. And we put the settlement orbiting Ceres so that it is in free space, and it stays relatively close to the source body all the time and doesn't drift away. And then we only have to solve the problem how to lift the building materials from Ceres to this settlement. One could simply use ordinary rocketry, have a propellant factory on the surface, or one could invest more into infrastructure, so one could have a space elevator or an electromagnetic catapult. In these cases, the energy that must be expended per kilogram lifted is an order of magnitude smaller than in case of the rocket. The megasatellite looks like this. So there is a disk, and this disk has both on the upside and downside attached these cylinders, and then there are two mirrors up and down which are inclined at 45-degree angle, which reflect sunlight towards this disk. And please notice that the sunlight direction in this rendering is not realistic, because if I would make it realistic, then it would be hard to visualize how it is. Here is a detail of this megasatellite. So these cylinders are there, and there is a small slit near the top of each cylinder, which is the entry slit of the light from the parabolic mirrors that reflect the sunlight in. So we really use natural sunlight because that's aesthetically pleasing, and also because it's cheap, because then one doesn't need so much solar panels or LEDs. And in this example, we have, or in this particular embodiment of the invention, we have a 50-meter high rural area which is sunlit, and then on top of it we have a 15-meter high urban space which is artificially illuminated. And then we need the artificial day, so 24-hour day length. And there is a neat way to achieve this by having 3 time zones which are 8 hours apart from each other. And if one does this, then the sum over the time zones of sunlight is constant, temporally constant. We don't waste any sunlight. So when there is noon in one of the time zones, then the other time zones have darkness and so on. Thermal design is a very important ingredient of these settlements always. And it turns out that Sierra's distance from the sun is actually almost perfect for having the thermal design without any extra apparatuses. So even though Ceres is so far away, then it is still so that cooling is just about right, the radiative cooling. So there is on the left there is the soil and the habitat, 1.5 meters thick soil, and then there is a vacuum gap, and then there is a radiation shield. The gray area is the radiation shield. The soil is rotating and the radiation shield is stationary, so therefore there must be sufficient vacuum gap between them. And then heat flux goes through this soil by liquid circulation, and we can use water there because it's above freezing point. And then it goes across the vacuum gap by radiation, and then it has to pass through the radiation shield again by liquid heat transfer. And there we need to use some other liquid than water because that is in a cold environment. And then eventually this heat flux is radiated into empty space. And then about mobility. So one of the key requirements and motivations for this kind of geometry is that it is possible to travel between these individual cylinders. There are many ways to do it, and I don't discuss them in detail. There's a main choice that whether or not the passengers are okay with weightlessness during the trip or not. So if weightlessness is okay, then it's a bit simpler to make this mobility network. But if they require that there must not be any weightlessness periods, then or even in that case, it probably can be arranged in a little bit more complicated way. And of course, for the sake of redundancy, we should have more than one mobility system on board, so that if one of them fails, then the other one still works. The mass budget of this megasatellite is such that almost all the mass is in radiation shields, soils, and biosphere. And those are, luckily, we can obtain those from the Ceres soil almost without processing. So, and then most of the production energy goes into making the tensile structures which take care of containing the artificial gravity. So withstanding the centrifugal force, which is related to the artificial gravity and rotation. And the baseline material is just steel wire, and there is a lot of iron on Ceres, so there is a lot of enough raw material for making steel. There are also other alternatives, but steel is a simple baseline selection. And then one point to note is that nothing, probably we can enter a regime where nothing needs to be abandoned, because the radiation shields can basically be our trash bins. So we just mine Ceres soil using open pit mining basically, and then we separate some of the materials, but then the rest of the materials we just put to the radiation shields, and then we don't have to abandon anything, absolutely anything, to the surface of Ceres. How to travel to Ceres is, of course, a non-trivial problem. So Ceres is farther away than Mars, and the trip time is longer. And currently, we don't have very good technology for transporting people to the distance of Ceres, I would say. However, this is, in principle, one can think of ways how to improve our propulsion system. So we could use electric propulsion with water propellant or oxygen propellant. These are lightweight molecules, so they naturally give higher specific impulse than xenon. Although they have some other drawbacks, but they nevertheless work. And these kind of engines have already been demonstrated for different purpose on ground, although they are not in operative use yet. So there is, in my opinion, there is clear road ahead how to achieve this kind of capability to actually move even people to Ceres. So in a little bit more concrete terms, how to bootstrap this kind of Ceres settlement. So the things that we need are, first of all, power system on Ceres surface, then surface vehicles to collect Ceres material from the surface. Then we need to separate at least water, iron, oxygen, and nitrogen from the mined material. And then we need a propellant factory on the surface. Then we need reusable rocket which lifts materials. And later we could replace this reusable rocketry by space elevator or electromagnetic catapult. And then we need a steel factory for making those tensile materials. And then financing, the first settlers would teleoperate the robots to build more habitats once on Ceres. So they are better positioned to operate the robots because they have zero communication delay, because they are in the vicinity of the robots. And therefore, their location on Ceres is economically valuable, and that's how they can make money, by living on Ceres and teleoperating the robots. And that's how they can pay back the initial bank loan that they took before first moving to Ceres. And then the next generation of settlers is larger, next group of settlers is larger, and then in this way this settlement can grow exponentially. Always builds more settlements to the newcomers, and then it grows exponentially. So in conclusion, we proposed an idea of settling the solar system by using a megasatellite in orbit of Ceres. And this basically is an attempt to combine the benefits of O'Neill settlements and Mars settlements. So we have Earth-like gravity, like O'Neill settlements have, but we also have interconnected world, not only isolated islands like ordinary O'Neill habitats have. So it's an interconnected world, like a planet. The overhead of the megasatellite frame itself is negligible, so almost all the masses in the settlements themselves, which are basically O'Neill settlements, and most of that mass is in radiation shields. And the main attraction of living off Earth is that there are no natural disasters, so there is higher living quality in that regard. And this idea can be made long-term sustainable, so all the atoms circulate, because we don't make use of daily use of rocket propulsion when moving inside the settlement. And lastly, I would like to acknowledge my co-authors, not co-authors, but my collaborators, Kadri Puus of Sinimerikallio and Al Globus, as well as the Academy of Finland.
Hi, everybody. I'm Dame Dr. Susan Ipjewell, and I'm actually in the Mojave Desert here in California at our MMARS base camp, and I'm inside the pod, and it's right now about 101 degrees, and we're fighting a 40-mile-hour wind. And so it's the closest simulation that you will get to see in real time. So I'm so happy to be here to speak to you and talk to you a little bit about what I'm doing and what our organization is doing. So first of all, let me introduce myself. I am a space physician, research scientist, and also an entrepreneur, having founded several startup companies, and very interested in education and being able to expand the the space exploration conversation and to be more of a global voice to really include others who really haven't been involved or participated in this arena. And so here I am, as you can see, I'm inside one of my pods, and we are actually developing the very first Martian lunar base here in the Mojave Desert. And we're literally about 35 minutes drive from the Mojave Spaceport. And in this area, it's kind of like the epicenter, I think, within the next decade of commercial space. And I'm really excited because really at this juncture in our civilization, we're literally about to open civilian space and have many more people involved in space exploration and having the opportunity to actually go out into space, right? Be involved and have this opportunity to go into lower Earth orbit, and maybe within the next 10, 20 years, have the opportunity to settle on an off-world, celestial body. And of course, the moon is the closest neighbor. And then into deep space and to Mars within the 2030s, 40s. So that's kind of what we're focused on. So my organization is called MMARS, which stands for Mars Moon Astronautics Academy and Research Science. So we have the research science because I'm a scientist. I'm very involved in frontier novel technologies. So, exponential technologies that will enable us to support that vision of humanity becoming multiplanetary. And so we do a lot of R&D in this area, and particularly space medicine, because obviously that is my passion and that's my training background. But what we've been doing as well since 2016 is deploying real-time, fully immersive analog astronaut missions in different fidelities. What I mean by that is that we deploy crews to the Mojave Deserts, where our training facility is. But we also are the first commercial analog training organization that have deployed crew missions to austere, isolated, confined environments. Like we've gone to Nepal to 10, 15,000 feet. We're going to be heading to Everest Base Camp and beyond in 2022, 2023. Obviously, when COVID is more managed, and then going to other austere environments and employing analog astronaut crews. But because of COVID last year, it actually expedited our vision to develop the first analog virtual astronautic program. And it's been going really well. And in other words, what we've done is to be able to use the virtual platform to actually engage more people, to bring them into the astronautic community, and they get to train. And then with what they learn virtually, all the knowledge, the interactions, they get the opportunity to come into one of our in-person training missions here, which we're reopening again in August. And we deploy monthly missions here in Mojave. So you actually get to apply practically all the knowledge and skills that you've learned through the virtual astronautic training, and then you come in and apply that in real time. So, that to me is really exciting. And so I am very, very passionate. I'm also a strong advocate about the UN SDG of inclusivity, diversity, and equality, right? Because if we really are to think about developing the future of humanity becoming multiplanetary, we really need to say everybody is involved, right? Everybody should be in the discussion, but not just in the discussion, but actually participating. So MMARS has actually started several initiatives that I think is about time. And one of the initiatives is the para astronauts. In other words, we are open to wanting to have the disabled community to be able to partake and participate in astronautics, and in particular, train as an astronaut in our missions. Because I think that just like we have the Paralympics, we should also have para astronauts. So that's one initiative. And I think it's about time that we actually incorporated, individuals who are really competent, very skilled to be part of the community. the other initiative that I really am excited about is the Apollo-nauts. And we call them the Apollo-nauts training program is because we're the baby boomers. If you know, the baby boomers like myself, we actually saw humanity step on another planet or another celestial body. You know, moon is not a planet per se, but still it's another celestial body. So, you know, in the last decade or so, when I meet the people in my age group, the baby boomers, we call them, right? Say, hey, you know, do you want to be an astronaut? Do you want to be involved? Because I'm too old. You're never too old, you know, and we say, no, you're not. Here's the opportunity, especially the opening up civilian space, commercial space. Here's your opportunity, because most of us, like myself, right? When I saw Neil Armstrong, when I was 7 years old, step on the moon, I said, I want to do that. I want to go to the moon. I want to go into space. And then for the last 51 years, they say, no, you're too old, or no, it's you know, X, Y, and Z, you can't do it, you know. And also the opportunity is very limited. Not anymore, not with the opening of the commercial space, civilian space. And that's why I'm so excited that we want to start the Apollo-naut training initiative. So it doesn't matter what age you are. You could be 60, 80, 85, 90. And if your cognitive function is intact and you're passionate about it, then reach out to us, you know. So that's kind of what I'm really excited about. And the other one is initiative, I think, is really for the underserved minorities that we're working with. We're working with communities and countries like the Caribbeans, Philippines, Vietnam, you know, all these countries, they have really wonderful talents, but for whatever reason, you know, usually financial, they don't get the opportunities. So, you know, that's such a shame. So what we've done is say, no, you have the opportunity, reach out to us. So really what I'm saying to anyone here, if you're listening and you're excited, is reach out to us and be part of this community, you know. And I thank you so much, ISDC and NSS, you know, because I think your vision aligns with us, is that we're all about inclusivity, diversity, and equality, and spaces for all. And that's kind of what our vision is with Mars, which actually stands, like I said, Mars, Moon, Astronaut Academy, and Research Science. So and I think our website is, we'll give you the website. It's www.mmAARS.com, and you can find out more information about us. But we'd love you to reach out. Even if you don't want to be part of the training, we still want to have your voice, you know, because we do also offer internships, mentorships, and we offer scholarships for qualified individuals. And it doesn't mean that you got to have an academic background. No, we're very, very much supporting citizen scientists, you know, anybody that's passionate, that has an idea, that wants to have a voice. We really want to encourage you and embrace you and bring you into the community. I think we need more diversity, you know. And so that's really what I wanted to share with everyone here today. And you can see, you know, there's the wind. Hopefully my pod doesn't collapse in real time. But I really am very, very excited. So here I'm going to say thank you so much for listening. And it's Dame Commander Susan Jewell. And I will say over and out from the Mars base in Mojave.
Hello, I'm Kevin Simmons, NSS Space Ambassador, educator, and principal investigator for 2 NASA CubeSats. Today, I'd like to share a little bit with you about CubeSats and their importance in education, particularly with younger students. So let's begin with a quick review of what is a CubeSat. A CubeSat is a small satellite form factor originally designed and created by Professors Twiggs and Sawari about 22 years ago in order to train university students to design, build, test, and fly a satellite in the time that they were at the university. This is a 1U CubeSat, actually the first CubeSat flown by middle school students. And by definition, a CubeSat is a form factor of 10 by 10 by 10 centimeters a liter of volume, and a mass not to exceed 1.33 kilograms. Now, you can have multiples of this unit, and they're called 1U, 2U, 3U, etc. And in the past 20 plus years, they have become very disruptive as far as educating not only university students and those headed towards STEM careers, but also even high schools and a few motivated middle school students. So how do you train and motivate young students, particularly at the middle school level, to build a real satellite? Well, the process that I used involved emulators, then tethered balloons, and high altitude balloons. So first of all, the emulators we used were Raspberry Pis, and the students 3D printed CubeSat chassis. We used Wi-Fi dongles, and then we suspended the balloon a few hundred feet above the school, and then the students practiced using dashboards and talking to the sensors in the tethered balloon payload to send down data. Then we moved to high altitude balloons, and what's important there is that we used a radio that would be very similar to the one that we flew in space, and it involved using the Global Star network. So we talked to a network of satellites high above us, and then all of our data came down through a dashboard. One of the most helpful things as an educator in that process is that all students could download all telemetry through CSV files. We then applied to NASA, and were the first middle school selected from NASA's CubeSat launch initiative. And we were selected in spring of 2017. So for the next 18 months or so, we finished our design, build, and then testing. We had to go through a number of acceptance test procedures to meet the NASA requirements. We were assigned to Spaceflight Industries as our integrator. The group of students you see here flew to Seattle, and we integrated our satellite into something called the Free Flyer that would be mounted on top of a Falcon 9, which would directly deploy our satellite into space. Now, our first CubeSat was called the YSAT-1, and its mission was to evaluate extremophile bacteria in space. And as you can see in this frame, on December 3rd, 2018, we did launch the YSAT-1 into space as it was carried by this Falcon 9 from Vandenberg Air Force Base, deployed into a sun-synchronous orbit at about a 575 kilometer apogee orbit. We began immediately receiving telemetry from our experiment, which lasted about 3 weeks. And then we continued to receive heartbeat and other telemetry from our satellite for the entire 18 months of our FCC license before we shut it down. Now, the enthusiasm of our first satellite led to our now annual application to NASA with other ideas, so that my CubeSat students literally propose their own ideas, and whichever ideas are down selected for that year, those students become the co-investigators for that project. We had another satellite selected in 2019. It was called the CubeSat-1. It is scheduled to fly on a Falcon 9 up to the ISS this December, where it will be deployed into low Earth orbit. Now, the CubeSat-1 utilizes a novel electrical power system, and we're going to evaluate some capacitors to see if they might be used instead of lithium-ion polymer batteries in the future. Now, as you would imagine, these students become very competent at technology and engineering and using things like the NASA Systems Engineering Handbook. But what we've also done, my colleague and I have created what we call the Techies and the Talkies. And our Talkies are very active in outreach. Our sixth graders literally create outreach books for 5-year-olds, and then they distribute them at the museums. Our older students created a policy team where we actually worked with our congressman to introduce 2 resolutions on the floor of the House of Representatives. We are active every year in Florida Space Day and the legislative blitzes by the National Space Society and Space Exploration Alliance and the AIAA-CVD as well. This was a brief review of the first middle school CubeSat development team and some of their activities. And thank you for your time. Please reach out to me by email if you have any questions. Thank you.
Dear Earth, we're sorry for all the things we've done to you. We're sorry for coal plants, oil spills, nuclear waste, dirty factories, auto emissions, wildfires, and climate change. We really didn't understand. We didn't mean to hurt you, but our needs got the best of us. Now we know there's a better way, one that will give us everything we need without harming you ever again. Can we start over? We have a new plan, and we really mean it this time. We promise. It's all about electricity. We know, we've tried that before. Coal, oil, gas. Those were the choices for a different time. But we promise to do better because we have a new source of power at our fingertips. Space solar power. The sun provides clean and virtually limitless power 24 hours a day. It is a huge, inexhaustible source of energy that will be kind to you, Mother Earth. The ways we currently harness solar power are a great start, but only provide energy for part of the day and are limited by weather and other conditions here on Earth. And your atmosphere, while we cherish it, reflects about 1/3 of the sun's energy back into space. Solar power generated in space and sent back to Earth frees us from these limitations and will allow us to provide virtually unlimited amounts of energy to the entire planet, night and day. Space solar power is clean, abundant, and the costs of collecting and transmitting it back to you, dear Earth, are negligible. And space solar power is virtually emissions-free and kind to you. We have the rockets and the proven technology we need to start building space solar power now. We may even be able to utilize the resources of your neighbor, the Moon, to build these orbiting power stations. We really want to do the right thing, Mother Earth. We're ready if you are. Space solar power will help us to repair the climate and make you healthier than ever. So what do you say, Earth? Ready to give us a second chance? Space solar power is the answer. To learn more and donate, go to go.nss.org/SSP.
Some of my earliest memories are skipping off school to stay home and watch the Apollo moon landings, and those experiences set the tone for the rest of my life.
I think I really got excited about the Kepler mission, and I thought it was so interesting how they actually found planets so far away from Earth.
It began when I was a young child growing up in southern Minnesota. Not a lot of population there, so real beautiful views of the night sky, and I can just remember looking up at the Milky Way and the stars and just being absolutely fascinated by what I saw and wondering what was out there.
I was 5, 6 years old, and I saw people preparing to go to the moon and walking on the moon. It was life-changing.
I found out that I had a passion for physics in high school, and I knew then I wanted to be an engineer.
John Glenn was about to fly, so there's a lot of excitement in England about that. And from that moment on, I wanted to be an American because they seemed to be the only people who knew what they were doing and where they were going.
My mother used to work for NASA. She used to bring home these pamphlets called NASA Facts. I started reading them when I was a kid and started playing Rocket Man in my closet. And then when I was a Navy pilot, thought about going to test pilot school. 3 missions on the shuttle and 1 on Soyuz up and down to the ISS, where I spent 7 months.
We as humans have a thirst for adventure, we have a thirst for knowledge, and we want to be better. And the exploration of space is the greatest adventure we can ever undertake. And we must do it for knowledge and because it's in our nature to do things that are difficult.
Well, this debate opportunity has taken that bold step of bringing it into the domain of young adults. If what we've done is created that energy and that interest. When you see these students speaking about it and using the terms that we use as if it was always their term, I don't think there's anything more rewarding, quite honestly.
Universalization is the act of all the nations on Earth, all the people coming together to tackle problems that affect us all.
Universalization, in my point of view, will change the world to a better place in a whole new league of problem solving together.
Figuring out a plan for universalization space is something that's really important and is really impacting us right now.
We want every individual involved in every matter because we're humans and this is our world. We need to rule it together.
We want all countries to be able to have that international collaboration that's going to bring us all together for a common cause.
Find a way to agree on new laws in space that are helpful and that everyone can cooperate and agree on.
I think it starts now and we begin that conversation, and as we plan, we are making way for generations to come to go to space in peace and borderless to boot.
You don't see that borders, you don't see that differences. Just like we have seen in the debate now, the students from different countries are actually part of a team.
The opportunity to put it in the hands of our next generation of leaders is what we need to do, because they're the ones who are going to help us really resolve, because it's their world. They need to own this.
Do you guys all want to live in space?
Yeah, sure.
It's my dream actually.
It's like a magic. So we can discover all the things in space.
Space is a mystery, it's filled with adventures, and I just want to touch the stars.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam.
Hello, I'm Geoffrey Notkin, President Emeritus of the National Space Society. I'm also a member of the Board of Governors of the NSS, and I'm a science writer, a television host, a producer of science television and feature films and documentaries, and a longtime NSS member. And for many years, I have been either a Master of Ceremonies at ISDC or one of the plenary speakers where I got to entertain our visiting students from around the world, or both. And being an officer with NSS and being involved with the International Space Development Conference has been a big part of my life for many years. So I'm very excited to be part of this virtual presentation of ISDC, especially because I get today to present the Space Pioneer Award to not only someone I admire tremendously and a valued colleague, but also a close personal friend of mine for many years. Now, the Space Pioneer Award is given to one or more individuals who, in the estimation of the NSS, have helped to open the space frontier. And that could be a literal interpretation, such as an astronaut, or it could be a writer or a thinker, a scientist, someone who in their work and through their life experience has helped further the NSS goal of establishing a permanent human presence in space. Now, the list of previous recipients is very impressive, and among others includes Elon Musk, Tom Hanks, John Glenn, Dr. Frank Drake, Eileen Collins, Martine Rothblatt, many other notable scientists, thinkers, astronauts, engineers, and so on. Today's recipient is not only a brilliant science writer and communicator, blogger, public speaker, but he is also a very charismatic individual who has a real history in science. He started out his career as a NASA engineer and went on to be a science writer and blogger, one of the top science writers and bloggers in the entire world, I might add. He has appeared on numerous television shows and documentaries. He's also written a great deal of science television, including working on the Bill Nye Saves the World show and many others. And I've had the pleasure of seeing him speak in person on numerous occasions, and he is one of the most entertaining and colorful science speakers. Someone who, in my professional opinion, as a fellow science speaker, helps maintain that sparkly, sassy, enthusiastic dialogue between science and students and listeners that has been done so well in the past by great speakers and educators like Richard Feynman. And so it is with genuine pleasure and delight that I welcome to virtual ISDC my great friend, Dr. Phil Plait, the bad astronomer. Over to you, Phil.
Well, thank you, Jeffrey. That's quite a list. I had to laugh when you said.
And that's not all of it.
Yeah, well, you do this stuff for a while and you get around, I guess. And I laughed when you said colorful. I don't think I've ever been described that way, but I think that's actually pretty good. I do tend to enjoy myself when I'm talking about space and astronomy, space exploration, and I think that's part of it. I mean that's part of this whole thing. Is one of the reasons I love doing it is that I'm having fun. I just like thinking about this stuff. I like talking about this stuff, and it's a pleasure. And so honestly, and hey, let me show you this ridiculously phenomenal award here. This is so cool. I mean, well, it has my name on it. That makes it cool for me right away. But it's also massive. I would say heavy, but it's the moon, and so it wouldn't be as heavy on the moon. But it is. This is actually the moon, and it comes off. I love this. I love this so much. It comes off, and I was looking at it when I first got it, and I pulled it out, and I was just sort of looking at a random spot on it, and I thought, is this just a random sort of artistic, or is this actually supposed to be the moon? And this is the life of a science writer, an astronomy writer. I saw that feature right there, and I went, oh, that's Mare Orientale. So that goes over here. And then as soon as I did, I was like, oh, there's Okeanos Procularum and Sinus Iridium. Okay, got it. And I was able to put it. Now I have to do it again. I was able to put it back on the stand, not only right side up, but also oriented so that you can see the near side. And yeah, so I have to make sure I do this exactly right, or else I'll feel like I'm not worthy of the award.
Well, you see, here you've amply demonstrated what I'm talking about: enthusiasm, great communication, being colorful. You immediately take the award apart to see how it works, and then examine the surface features to compare them to the actual moon that you know so well. I absolutely love that. So Phil,
I don't think any amateur astronomer would do differently, to be honest. I've spent a wasted childhood, as I had been told by one or two people, taking my telescope out every night, right, and looking at the moon or the planets or whatever. And it's like, someday, I'm going to get an award, and I'll be able to look at it and go, oh yeah, there's features on this. This is right. It's beautiful and artistic, but it's also accurate. So yeah,
right on. Well, I would be so disappointed if an award that the NSS gave you wasn't scientifically accurate. So
yeah, I'd be writing a blog post about it right away. They got this wrong.
So Phil, I'd like to talk about a few of the projects that you've worked on in the past,
and I would be remiss if I didn't mention one of my favorite of your works here. Of course, being a meteorite specialist, which is how you and I originally met many years ago, I am immediately drawn to a book that's called Death from the Skies. But you've had an extremely successful blogging. If I'm not being a snob, I would describe you as a columnist more than a blogger. So I know it's a semantic difference, but you write fully formed, thoughtful, detailed articles and have done for many years. So I like to think of that as a column, as the Bad Astronomy column, instead of maybe a more, I don't know, a more personally oriented blog. But that's just me being a writing snob. So would you tell me and our listeners, especially those who are enthusiasts about your work, a little bit about your process? How do you pick a title? Are you a writer? Are you a Somerset Maugham type writer who says, I will write for X number of hours every day without fail? Or do you wait until the moment takes you? This confluence between art and science is something that's very important to me, as you well know. And so you are an artist as a writer, and you're also a hard science guy. You're also a generalist, if you don't mind, which I mean very much as a compliment. And I know that astronomy is your great passion, but you also have very extensive knowledge in many different scientific disciplines. And I've seen that demonstrated during your talks and also just when we've been hanging around. So now I'll let you answer that question. Tell us a little bit about how the Bad Astronomy column comes to be.
Right. And when I started blogging, I actually described it as like, if you go to a newspaper and there's a regular column in the same spot every day, in an op-ed or something like that, that's more what I do. I mean, I was blogging back in the day when people would say, well, you take pictures of your breakfast and write about it? It's like, no. And happily now, 20 years later, something like that, it's more accepted and it's part of the vernacular. So I don't fret too much about what people call me, because I've been called a lot of things. And I will note that giving free advice on writing is worth every penny you spent. So this doesn't work for everybody, and everybody's style, everybody's method is different. I don't have a method. I have a few general things that I do. Like I was thinking about this last night. I stop writing when dinner is served. At that point, it's like I'm done for the day. Otherwise, at 11 at night, I'm lying in bed with my eyes wide open thinking, oh, I could be right. I was doing, because if I was writing an hour ago, my brain is still sort of in that mode. And so I tend not to have a lot of rules. I write because it's a creative process. You can't always make it work. And so there are days when the past couple of days, for example, even now, it's been a struggle to write some of the things. I've got a bunch of different deadlines, and this big deadline, it's not happening. So, okay, you know what? I can always write another article for the blog. And that process is mostly just finding out what's going on. I'm on a bunch of different email lists for news, so I get a lot of press releases. I check the journals to see what's being written, if there are any interest. I mean, there's always a lot of interesting papers that are being written scientifically in astronomy, but the question is it something that is, I don't want to say worth, but is it something that is appropriate, that's a better word, to put on a blog? Because if somebody makes some incremental, we looked at this spiral galaxy and we found that it's blah, 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 and it's like, well, that's good scientifically, and I appreciate it, and it's progress towards the goal of more knowledge, but writing about it for the public, it's not really that sort of thing. So you have to go through that process. And it's like, oh, I just wrote about this. That's another thing. It's like I've been writing about neutron stars a lot the past week, and it's just coincidence, but a lot of news has come out about neutron stars. So I've been writing about pulsars, magnetars, what they're made of, when they explode, how they're formed, and it's just a process of what it boils down to is it interesting to me? And if it's interesting to me, then I will write about it, because one of the things I learned a long time ago is that if you're passionate about a topic and you write about it, a reader will be far more interested in reading about it. And they would say, oh my gosh, I would watch this person, read the ingredients on the back of a pack of bubble gum. Look, there's some truth to that. I mean, honestly, I wouldn't want to do that for a long time. There's only so much you can get out of bubble gum. But if there is an interesting scientific topic and clearly the person writing about it is passionate about it, I think that comes through and it makes it that much more engaging.
That's so true and so well said, and very relevant to your writing. Your enthusiasm does come through in your writing and also very much in your public speaking, which is something that I've enjoyed tremendously. Now you and I met, if I remember, I think it was about 11 years ago, and it was at Space Fest here in Tucson, and we were both attending events, and I was talking out on the lawn loudly and enthusiastically to someone about meteorites or spaceflight or who knows what, and I heard someone go, "I know that voice." And you came over, and I go, "Oh my gosh, it's Phil Plait, the science writer." And he goes, "I've been watching your Meteorite Men show. You know what?" And my heart just kind of stopped for a moment. And then you said, "I really like it." And we've been friends ever since. And we have a shared interest in meteorites and asteroids and astronomy and all things space.
I have one here.
Ah, excellent. I have one too.
Oh, yours is bigger than mine. Is that a Campo?
No, this is actually Northwest Africa. This is a stone meteorite that I acquired quite recently. Look at the thumb printing on it.
Oh, I see now. Yeah. Yeah, this is an old Campo.
That's a beautiful one.
And it weighs about, what is it, 600 grams? Yeah. I've been collecting meteorites forever, and known a few dealers over the years. And then after you and I met, I mean, the stuff that you have, I've just always been kind of in awe of it. Every time I get to see one of your displays, I'm very excited because the quality of your stuff. You have a very keen eye and excellent taste.
Oh, thank you, sir. Well, I appreciate that very much. We've always had such good times when you've come to visit us at one of the GEM shows, or when we had Aerolite Meteorites set up at quite a few years ago now, the Science and Astronomy Expo here in Tucson, where you were a panelist on a wonderful science and science fiction event that we did, which I still look back at as one of my most favorites public events. And then
fun. Yeah, we watched a Star Trek episode and talked about it afterwards.
Oh yes. And I have a thing that you will recognize. So this is my magnum opus. This is a project that Phil and I have worked on. This is a prototype of the cover of a science and arts book. I mentioned science and arts earlier. So it's called Empirical World. It's been about a 5-year project, between 4 and 5 years. I've been photographing scientists and science writers and people in the science realm to show them as the fascinating individuals they are. And not only is Phil and his wife subjects, not only are Phil and his wife Marcella subjects in the book, he also wrote a smashing introduction for it, which is very, very moving. So it's still, we're still.
I was honored you asked me to do that, especially given some of the folks who are in that book, who could have also have written something quite good. So thank you so much for that. That really was truly wonderful.
Oh, my pleasure. Well, you've brought so much to the project. So I'd like to ask you one more question and then turn it over to you if there's anything you'd like to mention about perhaps ongoing projects, and also how viewers can learn more about you and your work. I know you're easy to find online, and you have a very active and very engaging social media presence. But the brief question I'd like to leave you with is, I'm thinking about the between 10 and 12 years that have elapsed since you and I first met, and how very much has happened in space flight and space exploration since then. And I wonder if you would pick a topic or an event or a concept or something that you see happening now or in the very near future related to space flight that you find particularly interesting or inspiring and that you are watching.
Oh my gosh, that's like asking to pick your favorite kid. You know, you have one, but you don't want to admit it. There's so much. I mean, we've been waiting for James Webb Space Telescope to launch now for a long time. I didn't work on it directly, but I was involved sort of very, very tangentially with it when it was vaporware, when it was still just an idea. And so to see it finally launching and knowing what it's going to do, and just thinking about, oh man, over the past 10 years, I mean, SpaceX started launching and landing rockets, and Blue Origin has been doing the suborbital flights, and that, you know, in space. And then we're talking about things like James Webb, which I still want to call the next generation space telescope. That's what it was in my head for a long time. I hate it when they rename observatories. I still think of the Fermi Gamma Ray Observatory. I still think of that as GLAST, which was its original pre-launch name. It's hard to get those out of your head. Of all the things, I mean, the things that excite me the most are the fundamental advances we've made in exoplanet exploration, looking at planets around other stars, and gravitational wave astronomy. And both of these start on the ground. I mean, we've been looking for planets around other stars for centuries, and to actually then start to find them in the 1990s, to the point where astronomers were like, yeah, these are real. We're not screwing around here anymore. There's a lot of doubt, a lot of skepticism, which is great. But now we have this evidence. It's like fairly overwhelming, and nobody's really doubting it. And then NASA says, yeah, we better build an observatory to go into space and look at these things. And they built Kepler. And now we have TESS, the Transiting Exoplanet Survey Satellite, and there are a bunch more planned. And some of these are going to probe the atmospheres of these planets, characterize the stars better. The Webb Space Telescope will be doing this as well. And so that's something that I love seeing, because when the first planets were found in the 1990s, I was still working on my PhD, and then getting involved with some of that tangentially, to be able to see that field take off, I guess in this case literally, is fantastic. And it's sort of the same thing with gravitational wave astronomy. We've been looking for these things for a century. This idea of Einstein that when something like two black holes merge, they will literally create ripples in the fabric of space-time. And nobody had been able to see this. And then suddenly we were able to, just not that long ago. Years ago, before LIGO, the Laser Interferometry Gravitational Wave Observatory, I think I got that right, before they even detected their first one, NASA and the European Space Agency were collaborating on a project called LISA, which was the Laser Interferometer Space Array. Space antenna? Space array, I think. 3 spaceships that would float in space, and when these ripples would pass over them, they would be able to detect them very cleanly, see where they're coming from, tell you all about the 2 objects that were merging. And this has been pushed off because it's incredible, difficult technology, but it's still something that is very real, and there's a path toward it. And so again, seeing something that started on the ground and is going to be put into space, and these are cutting edge scientific projects, it fills my heart with glee. Happening.
Great answer. Everyone, see what I mean about the enthusiasm? If you haven't seen Phil speak before, this is not even full on Phil. So if you ever have the opportunity to,
well, it's been a couple hours since I had my coffee. So if you let me get another cup, you know, I'll do a 2-hour impromptu discussion on gravitational wave detection. So
I would absolutely love that. I would pay to see that. So, all right, Phil. So, are you one of the most fun things we ever did together was the Science Getaways event in Tucson, which is a marvelous series of educational events, vacations for science nerds that you're involved with. Any chance that will return in the future?
Well, it's funny you'd ask that. This is a company my wife and I run, Science Getaways, where we take people on science vacations. Go places you want to go anyway, but then add science to them. And one thing we found is going to ranches. For example, I live in California. I lived in California. I live in Colorado. And there are lots of dude ranches here where you can go horseback riding and go on hikes. We bring a geologist with us. I take my telescope. That's actually why I have this meteorite here, is because I put together a talk on meteorites that I'll be giving, and we're having one next week. It's the first one we've had now for 2 years because of scheduling difficulties and of course the pandemic. So we're gonna try to get our feet out. I was thinking our water wings on, and that's not right. And then I was thinking, get our feet under us, out from under us. No, it's the other way. We want to get our feet under us, get them planted again, and get back into doing these 1 or 2 a year. Very excited, and thank you for bringing that up. I'm very
Oh,
excited
of course.
to do this again.
It
And
was one of
Jeffrey was one of our guests, and he came and we in Arizona, and we went on a meteorite hunt. We didn't find any, shockingly, but we did find some Civil War relics and some other things that were really pretty cool. So it's a lot of fun, and I'm really looking forward to it.
Good. Well, I'm so pleased to hear that you are back in action with Science Getaways. So, Phil, as we wrap up, would you like to tell our participants where they could find out more about that and your About Astronomy column and any your social media, any other things that you'd like to share, and then we'll say goodbye.
Okay, well, there's a lot of that, actually. Science Getaways is the company. It's just sciencegetaways.com. I write the Bad Astronomy blog for sci-fi-wire.com, and you can find that fairly easily. I'm on Twitter as I think just Bad Astronomer. I get the handles mixed up sometimes. Instagram. I'm looking at TikTok, thinking about that one. I like that venue a lot, but I don't have time to work on it right now. Just writing a lot of different things. I've got a newsletter on Substack called Bad Astronomy, badastronomy.substack.com. Basically, you type my name into a search engine and you'll find the stuff I do.
And there's a lot of good stuff out there. So I am a newsletter subscriber to Phil's marvelous newsletter for a very long time, and keeps you up to date on the latest and most fascinating and sometimes unusual, unexpected science news and science stories.
And dumb jokes, don't forget that. A lot of puns. Yeah.
Yes. Well, you do have a famous sense of humor. So it's with really great pleasure that I am the first person to say Space Pioneer Award winner Dr. Phil Plait, also known as the Bad Astronomer. Thank you so much for joining us for virtual ISDC. On behalf of everyone at the National Space Society, and for me personally, as an admiring friend of many years, congratulations. Thank you for all you do with your intellect and your heart for spreading science and helping us get further into the frontier of space.
It is a huge honor for me to get this award from the NSS and from you personally. So thank you very much.
Hello, my name is Tony DiTora. I am Vice President of Policy Coherence and a co-founder of the Beyond Earth Institute. Our mission at Beyond Earth is to create and sustain a legal and policy framework to enable economically vibrant communities of people living and working beyond planet Earth. We generally refer to these economically vibrant, self-governing groups as communities beyond Earth. I'd like to introduce my Beyond Earth co-panelists, Brett Jones, Vice President for Communications and Digital Media, and Jonathan Torvelson, Research Associate. Brett, Jonathan, welcome.
Thank you, Tony.
Thank you.
All right, our topic for this session is space solar power. Is it finally time to harness the sun? Space solar power, which I'll abbreviate SSP sometimes, invented by Peter Glaser, who was deeply involved with our hosts, the National Space Society, served on their board of advisors and board of governors. And then SSP was further popularized by Jerry O'Neill as part of his vision for many people living and working in space. Here we are nearly 50 years later. Are we closer? And if so, how close? It's been said that clean, plentiful fusion energy is only about 30 years away. Of course, that's been said for the past 50 years. Is space solar powered any different? And if so, how? And then we have questions about the different markets. SSP could provide energy to space projects, but how about to people on Earth? Could it upend the entire energy industry? Should it be worrying to the US and her allies that China and other competitor nations are pursuing SSP? Right now, the Naval Research Laboratory has a program working to overcome some of the last technological hurdles to make SSP a reality. The Air Force Research Lab also has a program, though it seems like they've managed to develop a space-based system which only works during the daytime, which we all know is one of the key problems with Earth-based solar. Of course, the NRL and AFRL programs are focused on delivering small amounts of energy for specific defense uses, forward operating bases and the like. It's clear that the goals of these programs will not lead to economical baseload power systems, so further work will be necessary, even if these programs are successful, for SSP to fulfill its potential. So I'd like to move to Brett. Brett, as we look at space solar power, is this just another fusion-like project where the future looks great, but you can never reach that pot of gold at the end of the rainbow? And if not, if the promise of SSP is real and achievable in the relatively short term, how will that be important for communities beyond Earth?
It's a great question, Tony. Thanks for asking. I certainly hope that it's not going to be, kicking the can down the road with space-based solar power, for decades. From what I can gather, the European Space Agency, JAXA in the United States, as you mentioned, we're all dabbling, as well as China and others. We're all dabbling with space-based solar power. I think the competition is healthy. Competition will drive innovation. So I really hope that these programs, while they may seem in their infancy, that they'll grow rapidly over the next 5-10 years or so, if not sooner. And I do think space-based solar power is imperative not only for space exploration and enabling human communities beyond Earth, but also fulfilling that Jerry O'Neill vision of taking industry and energy production out of the territory of Earth and declaring Earth a recreation zone. I mean, that's the real ideal, right? Start taking care of our planet while we get everything we need from space, not just solar. So I hope that we see these advances continue rapidly, and I'm confident that it will be instrumental as we expand beyond Earth.
All right. So, Jonathan, you've been thinking about space solar power as it relates to providing energy to people on Earth and how it intertwines with environmental goals, especially in comparison with other energy sources. Can you share your thoughts on that?
Yeah, so, with space solar power, you get a clean, reliable source of energy. And we're really seeing a problem with global warming, with climate change, and CO2 with carbon. And if we can move our energy production off Earth, we can significantly solve those problems. Similarly, if you want to compare it to nuclear power, it takes away the dangerous aspect of nuclear power that can be used by bad actors. So I really think that it's the way we should be going. It will help the Earth. It will help the people of the Earth. Bottom line is it will get us away from non-renewable sources of energy, and that's what we need to do. And we don't have much time. Every time you see another climate prediction, how long do we have? It seems to get shorter and shorter and shorter.
So
yeah.
So one of the key questions is, and you sort of alluded to safety there of nuclear systems, but one of the main concerns for providing energy on Earth from space-based systems is the transmission from space to Earth. So how do we address that in a safe way? Have you looked at that specifically, or Brett, would you like to touch on that?
Yeah, I mean, from what I can tell, you hit the nail on the head right there. Is transmission of that solar power back to Earth. Right now, some of the prototypes or concepts that I've been seeing utilize the electromagnetic waves beaming to an antenna, that kind of high frequency, beam. So long as it's directed properly to the right direction, it shouldn't cause any harm. However, that kind of beam might be detrimental, at those kinds of levels to the bad actors statement Jonathan was making before. So that comes down to, the importance of cybersecurity. Once again, not just the solar energy, but being able to maintain control of those systems through your headquarters of command.
Sure. So concentrated RF beams could cause problems. Obviously, you design the system so that they would be more dispersed and would not have those impacts, generally speaking, though you want to make sure that there are safeguards in place so somebody can't reconfigure it in some way.
Exactly.
Yes.
We don't want death rays from space. That'd be a bad thing.
Oh, no, you definitely don't want that. So but let's go back to then the other question about the technology. As we move forward here and we're sort of doing these systems for space-based work, does that actually translate to Earth-based? There are different systems going on. How do those sorts of things interplay? I don't know how much time you spent thinking about that.
Is that to me?
Sure.
Yeah, I think, it is, I guess it remains to be seen as to how much of the space-based solar power that we use for space exploration might be able to be adapted and converted for Earth-based territories. I think space and Earth-based solar generation are two different entities altogether. Not sure how much technology transfer we'll see between the two realms, if you will. But that said, the realm of science is interesting in that you might be looking to solve one problem in one category and you find out how to solve a problem in another category, slightly unrelated. So it's very possible that through space exploration, space-based solar power, that we'll discover new means to make solar power more efficient here on Earth.
Okay, great. So Jonathan, as we look at this, and I know that there's a public perception that if it has to do with space, it must be super expensive. And so you look at what John Mankins, the work he's done about making modular systems and potentially making modular systems using asteroid material or lunar material. Can you talk a little bit about how that enables communities beyond Earth, if you're able to do those types of systems?
Well, I'll take the lunar example. As most space people know, it requires a lot less delta V to get something into low Earth orbit from the surface of the moon versus the surface of the Earth. So if you can use lunar materials to start building these things and developing them, that'll create a need for workers essentially on the moon, beyond Earth, whether it's assembly stations in geo where they'll likely be put, or whether they're in on the moon, on the lunar surface itself. It requires, or the gateway, it requires that workforce to be able to do it. And that's one thing we look at when we're talking about communities beyond Earth is why would people live beyond Earth? And a big answer to that, I think, is always, well, to work. So
okay. Very interesting. So do you envision those communities on the surface of the Earth or in space or both?
On the surface of the moon or in space?
Sorry, yes, on the surface of the moon.
Yeah, I think it's a little out there to consider, permanent settlements on the moon. There's still too many questions we don't have answers to know if that's even possible. Okay. But certainly in Earth orbit, potentially lunar orbit, and maybe these won't be beyond Earth communities in the sense that we define them. Economically viable they will be, but maybe you won't want to raise your kids there. So maybe it'll be, especially at first, more akin to an Antarctic base, where it's you go work, maybe it's a few year stint and then come back. But just that in itself will really, in my opinion, catapult and let beyond Earth communities start to thrive more and more. Gotcha.
So one of the things that we've seen recently is, for example, with SpaceX, their Starlink satellites, they have been putting up basically a lot of solar power panels. So they've been generating a massive amount of solar panels, solar energy in space, and they've been doing it at a cost reduction. And if you look at that sort of equipment, the price per kilowatt hour has come down dramatically. In addition, with their reusable launchers, the price for launch has come down dramatically. So I guess what are the key economic showstoppers for space solar power that you two see in the short term?
I think right now you still have the launch issue. I think we still need to get the cost per kilogram down, and I think hopefully Starship might be the answer to that. But yeah, I definitely think launch cost is something. It inhibits all space activities, so
okay,
something to figure
out.
out.
What I love about Starship and reduction of cost to get to space, the barrier of entry coming down, is the ability to put the kind of elements in place in space to manufacture these solar panels, in space. We mentioned at the top of the discussion that it costs a lot less to get material off the surface of the moon than it does the surface of the Earth. So we could take the Starship to build a factory on the moon in order to manufacture these solar panels. And once you really kind of think bigger and like Jerry O'Neill with his lunar regolith mag launcher, where we just throw regolith into space and begin 3D printing these solar arrays, in situ, that barrier to entry comes down even more dramatically. And hopefully we get, from a few solar panels in space to a Dyson sphere. I mean, that's the real exciting part of this whole endeavor is, for those who don't know what a Dyson sphere is, it's a community, it's a hypothetical community that has built so many solar panels around their star that the star becomes invisible to observers outside the solar system, because that community, that civilization has been able to harvest the entirety of the star's energy. Rather than letting that sunlight escape into the darkness of space, we're actually harvesting every kilowatt possible. And that is down the road, Tony, but hopefully it comes sooner rather than later.
Yes, building a sphere the size of Earth's orbit around the sun. That sounds like it needs a lot of resources. Mining the Oort cloud and beyond, right?
Exactly.
Absolutely. Very interesting stuff here. So let's go back to the international question for a minute. So with the Artemis Accords, we've built a coalition with several other countries to live and work in space in a certain way. Russia and China are going a different way, though we continue to be friendly with them on the International Space Station. So there are concerns about one country controlling this technology and being able to sort of become the global powerhouse for energy in the future. Can you talk about that a little bit?
Yeah, it's a delicate one. The cooperation, competition, dialogue. I want to be careful because as we speak about the United States versus China, if it gets too much of an us versus them situation, it could be harmful for forward progress. There's the Chinese people, there's the Chinese Communist Party, and then there's China itself. So I believe that at our heart, at our core as a human species, most everybody wants peaceful expansion of outer space. There might be a few key players out there vying for that ultimate high ground in order to achieve full spectrum dominance, but I would hope that we, as a species, can avoid those baser instincts of, trying to compete for these resources. Because if you look at it, the data is there, the resources are available, the solar system can provide for all 8 billion of us and growing, no matter what country we flag over our land. So I am hopeful that, the competition breeds innovation and that we remain friendly because, maybe I'm just an optimist, but I don't want to live in a world where the alternative may come to life. I'll tell you that much.
Okay. John?
Yeah, no, I like what Brett was saying about friendly competition. If it's too competitive, it could turn into a dangerous scenario. I think it's also important to think about, different countries that would benefit from space solar power, but might not be at that anywhere close to the level of developing it themselves. And some of these countries don't like the United States. North Korea, Iran, perhaps it could, space solar power could benefit them in great ways and their people in great ways, but it's very unlikely that they would go ahead and buy it from the US. So I think an international approach to it would be the most successful. But yeah, like Brett said, the competition breeding innovation is always a huge part of it as well.
Very interesting. Very interesting. So one of the things that we try to do is engage in policies at the Beyond Earth Institute that will move the ball forward, so to speak. We have to come up with new analogies, I thought we decided, right? Yes. So but to further enable communities beyond Earth. And it sounds like this is one of those things. It creates infrastructure in space. It teaches you how to do manufacturing with in-space resources. It requires people to be up there, even if they're just there to fix the robotics that are doing the work and putting the panels out there and whatnot. So this seems like one of those sweet spot projects that really can speak to everything we're talking about communities beyond Earth. In addition, it hits those other sweet spots for providing energy here on Earth, which is you're no longer mining and drilling, carbon zero, zero for the criteria pollutants in the Clean Air Act. So across the board, as long as you can get the costs down to where it's supposed to be, so it can compete on a global scale, then I think this shows great promise. So
it certainly does.
All right. Any final thoughts? We're getting to the end of our time here.
I guess I'll close with, I think it's important that as advocates for space solar power, we remain honest about space solar power. And what I mean by that is space is hard. It's going to be expensive. There's things we still need to figure out. So it's important to, to show people that we don't just have our head in the clouds, so to speak, that this is a real idea. And yes, we're not quite there. But like I said, it's very real.
Yeah, and I'll echo that, Jonathan. I think it's a great point. Space is hard, but that challenge, it can be a unifying challenge for humanity. I believe, we don't need, alien invasion to motivate us to get off the planet. We just need to look around and say, we've got limited resources here. We have to get on the planet if we want to have not just human communities on Earth, but human communities living, thousands of years into the future. I believe that if we don't harvest the energy of our solar system, starting with the sun and the other materials that are hanging out there waiting for us just to go and pluck from asteroids and elsewhere, then we're doing ourselves a disservice. We, as human beings, have been explorers by our nature since we took our first breath. And I think we should continue that spirit of exploration for as long as humanly possible.
All right. I think that's great. Brett, Jonathan, thank you very much for taking the time and providing your insights. Personally, I agree. Space solar power feeds into communities beyond Earth, and I think it, in fact, requires them. So,
absolutely.
Great. Take care.
Thank you, Tony.
Thank you, Tony.
Hello, my name is John Mankins. I'm the director of Solar Space Technologies Limited and a founder and president of Mankins Space Technologies, as well as a member of the board of the National Space Society. Today, I'd like to speak with you briefly about space solar power and the status of the solar power satellite in 2021. The vision of space solar power is well known to most space advocates and not known in the least by many people who are not space advocates. It involves placing large platforms in a high Earth orbit where they would harvest the almost continuous light of the sun, which passes by Earth, and transforming that power into a wireless beam, send it to receivers on the Earth, and deliver, in principle, power to locations and to people around the world. This vision was first framed in the late 1960s by Peter Glaser and has been looked at repeatedly over the decades since. There is, however, now a new urgency in developing novel and no-carbon energy sources. In particular, the goal of net zero carbon energy has become an urgent matter for many developed economies around the world. Some 59 countries have established goals, either in law or in policy or in principles, to achieve zero carbon emissions in industry, in electricity generation, or in transportation during the coming several decades. This would entail massive changes in the energy infrastructure across the world. And the real question is, do we have time for space solar power to be a part of the solution of this challenge? An important question is how to compare solar power satellite options, and in particular, how to create a taxonomy for solar power satellites. And one of the things that I've looked at in the last year or so is the definition of critical characteristics for SPS. Things like the frequency and type of power delivery that would be used from space to ground, the voltage and scale of power management, the kind of wiring that would be on the platforms. Would it require active cooling of the major system elements? How would it be assembled? Would it be deployed like a spring-loaded device, or would it have robots? How would the power be generated, either with photovoltaics or with solar dynamic systems, and so on? Another key issue is how to establishing a common framework for comparing solar power satellite options is in how to set common assumptions. It makes no sense to compare one concept that's delivering a megawatt and against another concept that's delivering 1,000 megawatts. So here are some common assumptions that I've put together for the concepts that I'll be comparing in the next few minutes. In particular, power delivered to the local grid, about 2 gigawatts, lifetime, about 30 years, the total power to energy to be delivered, rather, that's over the 30 years with a 2 gigawatt peak power, the cost of launch, which will be assumed of getting it into space, where would the platform be located, what's the cost that will be charged to the economics of a platform per year for operations and maintenance, and per year for financing costs, the cost of in-space infrastructure to be used to deliver a total of 300 gigawatts, that's 300,000 megawatts of power, and the cost of the receiver, which is assumed to be the same in all cases. And of course, these are not exactly correct, but this is intended just to provide, as I said, a common framework. This then is a systematic taxonomy, a way of organizing information about SPS concepts. Type 1 is the 1979 reference system concept that came out of studies done by NASA and the U.S. Department of Energy and a team of industry engineers and scientists. Type 2, which is a large monolithic platform. Type 2, which has a set of modular power generation systems connected through a single backbone to an integrated receiver. Type 3, which are laser solar power satellites. Type 4, which is an integrated sandwich panel satellite, very much like the sandwich panel that has been developed in Japan, and by recently a prototype was developed by the Naval Research Laboratory. Type 5 is a relatively new concept, which would be a thin film substrate, like printing a solar power satellite component by component onto a large solar sail. And Type 6, which are a set of concepts that are somewhat like the sandwich. They have modular RF and photovoltaic systems, and somewhat like a sail in that they involve large thin film reflectors to redirect sunlight to the photovoltaic arrays. So going quickly through the individual assessments, the 1979 reference system, relatively simple architecture, looks a lot like a conventional satellite, but required a massive investment in upfront infrastructure, had factories in low Earth orbit and geostationary Earth orbit, had multiple Earth orbit transportation systems, much larger than the space shuttle was, had quite high voltage power management, high voltage power lines on board the platform, and was in fact a fairly expensive option. There's a new option that's come out in the last 10 years or so from China. Studies there looking at what's called the multi-rotary joint solar power satellite. It resembles in some fashion the same configuration as the International Space Station, with an integrated power management and distribution system, and the wireless power transmission system, which would be a single large transmitter. However, it involves the use of robotic systems for the deployment of the platform and doesn't have the very large in-space infrastructure required for the 1979 reference system. Laser concepts, of which this particular one is an example. It's a modular laser. Each of the transmitters would be 1 to 10 megawatts of laser power. There would be a large number of those deployed in a connected array, and then a number of the connected arrays in what's called a halo orbit in a geostationary Earth orbit, each one sending power to the same receiver down at the Earth. This has a fairly attractive in that it has a very small cost for initial entry, but it is rather negative because the laser light doesn't penetrate the clouds very effectively, so it only provides power when the weather is good, and because the individual modules are fairly large, 5 to 10 megawatts, it means that there aren't as many modules and the cost would be fairly significant. Imagine using the Hubble Space Telescope as a module in transmitting laser power. This would be quite similar to that. Then there's the sandwich panel that was looked at by the Japanese. It's called the simple SPS. Very simple, very low cost to manufacture, largely existing technology. Has one huge issue. It only generates power at local noon for about 25% of the time during each 24 hours, because when it's in orbit, it has to point at the ground constantly, and as a consequence, when it's the RF transmitter has to point at the ground constantly. When it's local noon, the sun is overhead, power comes to the PV, power gets transmitted as a wireless power transmission to the ground. At 6 p.m. or 6 a.m., the platform is edge on to the sun. And at night, obviously, it doesn't see any sunlight at all. And so this really cuts into the economics of the platform. And type 5 is the solar sail, print the SPS components item by item onto a large thin film system, like a big solar sail made out of some thin film space qualified material. Again, very low mass per square meter. But again, it has the same kind of problem as the Japanese simple SPS, planar SPS, in that it really can't deliver power very effectively at night. And it pretty much only during a portion of the daylight hours when the platform can have its back to the sun, as it were, the PV facing the sun and the RF transmitter facing the ground. And lastly are the systems that involve the use of reflectors, such as the SPS Alpha Mark III. These have quite low mass per kilowatt hour delivered to the ground. Because the reflectors, which comprise a large number of heliostats, provide illumination to the photovoltaic array pretty much constantly, you get power 24/7, 99.5% of the time. Quite small modules, relatively easy to launch. It does require the heliostats, these small reflectors, to operate correctly and autonomously, and it requires quite a large independent structural system to connect the energy transformation array, PV to RF to the ground, to connect that to the structural system with the heliostats. The integrated comparison, obviously, I'm not here walking through, because of the limits of time, I'm not walking through all the details of analysis, but what I've done is to take each of these concepts, transform them into a 2 gigawatt geostationary Earth orbit-based approach, and to use the same methodology for estimating the cost on each and every one. So I'm not going to make the argument that all of these cost estimates are exactly correct, but my purpose here is to compare them and to try to have an idea of what would be their relative effectiveness and the cost of the energy delivered from each of these. And as you can see, the cost of the reference system type 1 is quite high. That's due to the fact that it's rather massive and the very significant infrastructure that has to be put into place in order to deploy it. Type 2, the Chinese system, the multi-rotating joint SPS, is significantly lighter and has a much lower cost per kilowatt hour, price per kilowatt hour, because of the use of the autonomous robotics for assembly, the lack of a major in-space infrastructure. Type 3 is a bit lighter yet, but has a higher cost of power, again, because it's made up of this array of large optical systems which have to be built and integrated, deployed. And so again, it's like manufacturing hundreds of Hubble Space Telescopes and then transmitting power through those. Type 4, the simple sandwich, is about the same mass. Just coincidentally, as it turned out, the system concepts are very different. But the energy per unit, the cost per unit energy delivered is not significantly better because it only delivers power about 25% of the time. The single substrate thin film SPS system is much lighter, but unfortunately, because the modules are very large, an individual module is like a solar sail, the cost per kilogram for those modules appears to be rather high. And so it's on the order of $10 per kilowatt hour. The system concepts that are type 6, the modular system, hypermodular systems, highly modular systems, analogous to the sandwich SPS, but using heliostats to redirect the sunlight to provide power 24/7, appear to have the best cost per kilowatt hour at this time, followed by the type 2, the combination modular rotating joint SPS. Now, the question is whether or not an SPS can be deployed in the way envisioned, or whether or not these systems can be realized. I want to just highlight 2 items. One, there is recently proof that some of the critical hurdles to SPS can be overcome, in particular low-cost launch. Already, the classic paradigm of high cost to get to orbit, like $20,000 a kilogram, have been broken by the SpaceX Falcon 9 reusable and Falcon 9 heavy reusable, getting costs down by 90%. And if you look to the next few years, even better systems are coming along from SpaceX in the form of Starship and the Heavy Booster, and from Blue Origin in the form of New Glenn. And I think we can anticipate that now that it's been shown that reusable launch can be done, that other countries will be pursuing this in the near future. And can the cost of hardware come down comparably? We can look to a single example quickly, and that is the mega constellations that are being launched, in particular the Starlink, OneWeb, Kuiper system, and the others. Already, the Starlink system has demonstrated manufacturing on the order of 30 metric tons of flight hardware per month at a cost of about $2,000 to $1,000 per kilogram hardware. Conventional Earth orbiting satellite costs between $200,000 and $300,000 per kilogram, hundreds of millions of dollars per satellite. This is already a 99% reduction in cost in the hardware. So if you look at those two, already 90% reduction in flight, in the launch of the flight hardware, and a 99% reduction in the cost of the hardware itself. And you can see that we are well on the path to the kinds of manufactured costs and launch deployment costs that we need for solar power satellites. Can we do it in time? Can SPS really make a difference in climate change and carbon net zero goals and objectives? I would argue that the answer is yes. With the modular approaches, within 3 to 4 years, major demonstrations could be done in low Earth orbit. Within an additional 2 to 3 years, A 100 megawatt base system could be built and deployed in a middle Earth orbit, and within 10 or 12 years, and for a total cost of on order $12 billion, the first multi-gigawatt solar power satellite could be deployed in a geostationary Earth orbit and begin contributing significant carbon zero energy for the world. That concludes my presentation. Let me just say thank you so much for your attention, and I look forward to meeting with you all in person at the next ISDC. Thank you.
Hello, I'm Gary Barnhart, President and CEO of Extraordinary Innovative Space Partnerships, Inc., XISP, Inc. for short. The talk that I'll be giving today is on space solar power, ancillary services, beaming mission development. This is an effort that we've been involved in at XISP, Inc. since 2012 in earnest, and long before that in general with respect to the development of space solar power options across multiple venues. What we're trying to do with our space-to-space power beaming mission, which is one of, we think, the starting venues, if you will, for making use of space solar power, is to look at the issue of being able to unbundle or disaggregate spacecraft electrical power systems and be able to provide both beamed power and ancillary services as a utility. We feel that this is a means of supporting the further development of power beaming and ancillary beaming technologies. We break our mission development work into three linked phases: technology development, demonstration, and deployment. So-called TD-Cube missions. They're intended to effectively bridge the technology development valley of death, which seems to pervade a large number of research efforts that had crossed into this area. The TD-Cube missions that we're working on defines a civilian non-weapons use of space solar power. What we're going off and doing is addressing both real and perceived cost, schedule, and technical risks associated with space solar power and ancillary services beaming. What we're trying to do is build a bridge across the multiple venues, including space to Earth, starting actually with space to space, then space to alternate surfaces, such as the space to the moon, surface to surface on the moon, as well as the potential for space to Earth applications. Basically, the idea is that it's an effort to lead to the use of beam energy to support sustained International Space Station, co-orbiting free flyer operations, enhanced power requirements and augmented propulsion, the notion of loosely coupled modular architectures, and new potential cluster architectures of satellites that can take advantage of the beaming capabilities. There are a number of critical considerations with this sort of mission. One, space power and ancillary services infrastructure is an applied engineering problem and an economics problem. Applied engineering in the sense because the solutions are valued in terms of availability, durability, resilience, and maintainability, not as new science and or engineering. Economics, because the solutions are necessarily sustainable utilities that will circumscribe what is possible. Each application and venue has significant systems engineering and economic challenges, different fundamental figures of merit and value propositions, and the operational capabilities are best realized by leveraging a combination of technology development push and mission requirements pull. With respect to some of the work vectors that you have to deal with, I alluded to this notion of technology development, first starting on the ground and moving to space, technology demonstration and deployment. You also have, of course, the different venues. One of the interesting critical considerations is the idea that each increment of public and or private investment should lead to an operational capability that is useful and used by one or more other missions. This is very distinct from running or attempting to run a technological sandbox, or technology development sandbox, if you will. Furthermore, the efficacy of any systems architecture must consider the entire life cycle of the field of equipment with respect to both cost analysis, functionality, scalability, durability, and maintainability. Furthermore, engineering solutions which leverage other mission investments should be given priority, but not exclusivity. Furthermore, approaches should be biased to organically grow the community of interest so that they become increasingly invested in the success of the endeavors. There are a number of key variables associated with designing and fielding any form of power and ancillary services beaming capability. There's the cost and economics, which include things like the initial cost of first power, the levelized cost of electricity, market viability, anchor customers. You have the magnitude of the power, both in terms of power level that supports applications and its scalability. You have the distance, not just in a numeric sense, but from the physics that's involved. Is it a near field application? Is it boundary regions or far field applications? The frequency and wavelength, ranging from millimeter wave to microwave to eye-safe optical. Turns out the physics is the same, regardless of the frequencies or wavelengths that you're dealing with. There's different sets of equipment that are involved. The voltage and aperture, the duration, the availability, the security, the performance, the logistics, environmental considerations, and again, the technology readiness level across all of both the individual elements and the integrated system. And really, you're managing cost, schedule, and technical risk. You could go to the first slide. This shows an artist's conception of the space station mission that we had envisioned. Next, please. Okay, so what you have here is the space station on the left, which has a gimbaled, 3-axis gimbal transmitter system that could be located either on the Columbus Bartolomeo facility, exposed facility, or the Japanese experiment module exposed facility. It's designed to be compatible with both. That is going through and generating both a multiplexed power and communications beam to a 6U CubeSat satellite is proposed as the initial test article. And the idea is that that's the starting point for the test bed. For operational use, you'd have there's opportunities to use a full range of both, the pressurized, cargo carriers that come to the station and an evolving suite of commercial, modules that are hoped for. Next slide, please. Now, hopefully this works. Yeah, it should show up on your screens. Basically, one of the things that we were, had a question of is that how are we going to go through and communicate to people that this is actually working? And one of the things that we came up with was the idea that you could actually put in LEDs into the combination solar array and so-called rectenna, or receiving array, that were indicating the intensity of the beam that was being received. And this, is an artist's concept of how we might be able to do just that. The one of the things that is a key facet in this is there Is there something that makes sense in terms of the applications of space solar power on this scale? And we went through and looked at 3 different frequency cases, the low end, so-called Ka band, the high end of Ka band, and W band. The low end of Ka band, it's you're looking at power densities that, for this application, that would be less than the solar constant, or the radiation from the sun. So that's not going to scare anybody. The physics still work, but you're not really supplying much in the way of usable power. It's just test power. If you go up to the high end of Ka band, you end up in a situation where you have more than double the solar constant. But if you can find a way to push it up into well into W band, you end up with a order of magnitude higher power densities than the solar constant. We consider that what we euphemistically call the money chart. Basically, there's something there. The question is, can we make the most effective use of it? Next slide, please. Now, hopefully you folks can see the broader arcs in here. You have basically what we've referred to as ground merging into space-based technology development, which supports a range of space-to-space applications, initially starting with the station and then leveraging what's hoped for a full range of different commercial activities spanning from low Earth orbit through cislunar space, to a range of activities, surface-to-surface work with respect to the moon, particularly in support of the mining of lunar volatiles in permanently shadowed regions, and the evolution of the infrastructure there in space, the notion of space to the moon and asteroids. There are applications both from lunar orbit to support different lunar installations, as well as with respect to asteroid assay and mining, and then eventually leading to space to Earth applications, where hopefully by going through and investing in efforts to address a range of these elements of cost, schedule, and technical risk, that we can have retired enough of it, both from an actual standpoint and a perceived standpoint. The key thing with respect to space solar power is it represents an opportunity whose time has come. We have transitioned our mission from a conceptual mission that was pregnant with opportunity to a commercial mission which has recognized standing with NASA. There's now a defined confluence of interests biased towards successful execution of the mission as a public-private partnership. And we hope that the successful demonstration of space solar power beaming will reduce the perceived cost, schedule, and technical risk of space solar power in general, and pave the way for space solar power's use in multiple venues. Our tagline is, "Don't wait for the future, help us build it." Thank you for the opportunity to present this material.
Hello, my name is Martin Salto and I lead the space business for Fraser Nash Consultancy here in the UK. Last month we completed an independent study on behalf of our Department for Business and Energy into the feasibility of space solar power. It's a great pleasure and honour to be invited to share the findings of this study with this conference. Over the next 18 minutes or so, I'd like to take you on the journey we have embarked on here in the UK. We'll look at the context for our energy policy, and then I'll take you through the study approach, our findings, and what the next steps might be. The story starts with net zero, which is our government's legally binding obligations to decarbonise our economy by 2050. There is broad recognition of the many challenges for the pathways to net zero, the intermittent nature of wind and solar, constraints on the growth of nuclear and biomass for different reasons, and the immaturity of carbon capture are just some of the problems. Affordable, abundant energy underpins our prosperity and security, and innovation in new energy technologies is vital, particularly sources of baseload and dispatchable power. Fraser-Nash helps organisations with technology and strategy, and we work across many sectors, including next-generation aerospace and energy systems. Back in the autumn of 2019, we approached the government with a proposal that the UK should study space solar power to help with net zero. We were very fortunate to find a deputy director in the energy department who was receptive. Early in our conversations, the department set out the criteria that any renewable technology needs to offer to be considered seriously, and it's a high bar. It needs to be affordable, scalable, sustainable, commissioned in time to make a difference for net zero, and it should support UK jobs, plus a host of other attributes. On this journey, we found ourselves repeatedly explaining what the concept of space solar power is and why anyone would consider such ambitious technology. There are many skeptics out there, and it's perhaps worth a brief recap. A solar power satellite in GEO can see the sun for 99.5% of the time, so it offers the potential for delivering continuous baseload power day and night through all seasons and weather. Space solar power is highly attractive because of the sheer abundance and persistence of solar energy from space. Whilst historically it's been considered unaffordable, in the last decade a number of factors have combined to change this view. Space launch costs have fallen by 90%, and that downward trend is set to continue. The latest satellite designs are substantially lower in mass and radically lower in production cost, and the underpinning technologies such as in-orbit robotics are maturing. So it's becoming a viable commercial proposition. Added to this, the net zero imperative and possibly even the fear of missing out, and governments are becoming interested. Comparing its characteristics as an energy technology against the department's criteria, the case becomes even more compelling. It is inherently scalable and can provide dispatchable as well as baseload power, giving great flexibility for the grid. It has low environmental impact, with substantially less land usage than wind or ground solar, important for the UK. And finally, it has some unique characteristics, such as the flexibility to beam power to different sites. In short, it opens up new options for decarbonising our economies within a mix of other renewables. We have studied a number of international concepts, and with apologies to those in the audience who are familiar with this, I'll use the UK Cassiopeia design to highlight some of the features which influence performance, risk and cost. Keep in mind that the economics is the driving consideration, the launch cost is a dominant factor, and the satellite mass is the driver of launch cost. So one of the key performance metrics is the power output per unit mass. The system comprises four principal elements: a solar power satellite in a geosynchronous orbit, the space transportation from Earth to orbit, the ground rectenna, and the ground-based satellite and power control. The solar collection element comprises a system of mirrors concentrating collimated sunlight onto high concentration photovoltaics. The use of HCPV with 600 times concentration gives both high efficiency and greatly reduces the quantity of rare earth elements used, so good from both cost and environmental perspectives. The microwave frequency is in the atmospheric window, typically 2.45 gigahertz, making it a 24/7 all-weather system. The RF conversion efficiency is about 85%, and achieving good efficiency through the energy chain is a key driver of mass and cost. In a system of retro-directive control, a pilot beam provides a reference phase across the satellite, giving both security and high pointing accuracy. The rectenna converts the RF energy into DC electricity and then through an inverter, which delivers a net 2 gigawatts of AC power into the grid. So each of these satellites is comparable in output to a nuclear power station. The satellite is about 1.7 kilometers in diameter with a mass of several thousand tons. And the reason for this enormous size is to do with the diffraction physics and the economics. There's also a safety consideration, as one of the design constraints is the maximum beam intensity, limited to around 240 watts per square metre, or about a quarter of the intensity of the sun at the equator. The satellite physical architecture is very different from a traditional spacecraft. It's highly modular, and the main component is a lightweight solid-state sandwich panel comprising the solar PV, power conversion electronics, and the RF microwave beaming. Each satellite has a handful of module types and up to 1 million units of each type. These are mass manufactured, keeping the cost per kilogram very low. And this modularity also provides system resilience to damage from micrometeorites or degradation. A key consideration for any solar power satellite is the rotational mismatch between the sun pointing and the earth pointing elements. Different concepts address this in different ways, and Cassiopeia uses electronic beam steering through 360 degrees with no mechanical moving parts. Operational orbits are a consideration, and Cassiopeia uses a geosynchronous Laplace plane orbit, which minimizes the problem of congestion in geo and has very little delta V requirement for station keeping. Low-cost, reusable space transportation is a critical enabler. In a typical scenario, a fleet of spaceplanes transport the modules to LEO, where an infrastructure of chemical tugs would raise them to an assembly orbit just above the inner Van Allen belt and away from the risk of space debris. There, the satellite is assembled with autonomous robots, and the fully assembled satellite would then be slowly raised to a geosynchronous orbit with solar electric propulsion, powered by the onboard solar power. The use of autonomous assembly is essential for the economics, as manned spaceflight would be far too expensive. The modular architecture makes for a highly structured environment, simplifying the challenge for robotic assembly. Servicing and maintenance strategies vary. Typically, this involves periodic module replacement and replenishment of propellant using the same space transportation infrastructure and autonomous assembly systems. These are some of the considerations which the leading designs address with elegant engineering solutions, resulting in good power to mass ratio and a competitive levelized cost of electricity. Importantly, they don't rely on major advances in materials science. The rectenna itself is a comparatively simple construction, like a huge fishing net holding the small dipoles. It's elliptical in shape at UK latitudes and measures around 7 by 14 kilometres. It needs to be a contiguous area and could perhaps be sited offshore and take advantage of existing wind farm grid connections. The national grid is already starting to think about the implications. To give a comparison, this is about 1/3 of the area of equivalent ground solar. Turning to the study approach, we structured the work in 2 phases. Firstly, a technical feasibility assessment, and secondly, modelling the through-life costs and economic benefits for the UK. There are, of course, broader political, environmental, societal and regulatory issues which were beyond the scope of the study. In phase 1, we examined 3 leading solar power satellite concepts which all have the ability to deliver gigawatt levels of baseload power and which represent a range of design approaches. These concepts were John Mankin's SPS Alpha, Ian Cash's Cassiopeia and Huizenbin's MR-SPS. We reviewed the literature and looked for independent evidence to confirm the maturity of the underpinning technology. We also engaged with senior figures in the research community and defence to identify engineering barriers, as well as thinking about upside opportunities for the UK. From this, we developed a technology roadmap through a series of structured workshops involving UK space organisations, as well as our own experts in the energy sector. Importantly, John and Ian also contributed their expertise in space solar power, and they generously shared a great deal of technical and commercial information about their concepts, which helped to make the study authoritative. We developed a 4-phase, 18-year roadmap with a substantial demonstration at the end of each phase to confirm the technology and the system readiness level. The final product of phase 4 is a fully operational, first-of-a-kind system delivering 2 gigawatts into the grid and with the manufacturing processes industrialised and mature. Thereafter, the production programme would be relatively rapid, with an additional 2 gigawatts of capacity commissioned every year or so. We also looked for commercial exploitation opportunities from the demonstrators themselves. At each of these steps, it's possible that development could be completed more swiftly, and the COVID vaccine rollout has shown what we can achieve when there is a real political drive and funding. The work in Phase 1 gave us a clear view of the current technical maturity, development risks and the steps necessary to develop an operational system. In Phase 2, we focused on the solar power satellite Cassiopeia as a reference design for the cost and economic impact assessment. Our modelling technique used a Bayesian probabilistic approach, which is ideal for modelling uncertainty. It included the whole life cycle from manufacture to decommissioning, and all elements of the system, including space and ground segments, and the enabling systems such as space transportation and space robotics. From the technology work done in Phase 1, we assigned to each of the subsystems a range of values for key performance characteristics, such as specific power, efficiency, mass per unit area, and the manufacturing learning curves. These were then combined to produce a 3-point estimate for size, mass, and cost. This chart shows the cost of space solar power compared to other technologies in the UK's pathways to net zero. The levelised cost of electricity is estimated at between £35 and £79 per megawatt hour, with a 50% probability figure of £50 per megawatt hour. And these figures include a high hurdle rate of 20% to reflect the low maturity and development risk. The LCOE is highly sensitive to hurdle rate, and in practice, as the technology matures, the hurdle rate could be expected to fall substantially, reducing the LCOE. For example, with a hurdle rate of 10%, the LCOE would almost halve to about £26 per megawatt hour. We conclude that space solar power is competitive with all of the other technologies, but particularly so against those which might be considered baseload. We costed the 18-year development programme at £7.5 billion, of which a significant element is the cost of space transportation for the first-of-a-kind system. Including optimism bias factors, this is £16.3 billion in present value terms, or $21 billion. Such a development profile poses significant funding challenges where the returns are only realised at the end of the programme. Our analysis concludes that public funding will be needed to de-risk a substantial proportion. What do the economic benefits look like, and would it be a smart thing for governments to back? A public sector investment in such an infrastructure programme can be expected to support a significant economic footprint. There are a couple of ways to look at this. The GDP multiplier is 2.3, reflecting the highly productive industries involved. And this indicates that for every pound or dollar of direct GDP, an additional $1.30 of indirect and induced GDP is supported. The benefit-cost ratio provides a measure of likely scale of economic impact resulting from public sector investment. For this programme, the ratio is calculated to be 1.8. Thus, for every pound of public funds spent to develop the first-of-a-kind system, £1.80 is supported in the UK economy over the life of the programme. Those are both very good ratios, and they should make a strong business case for government support. We also identified a number of spillover benefits from a development programme in areas such as wireless power transmission, semiconductor and photovoltaic technology, autonomous robotic assembly in challenging environments, and by no means least, inspiring the next generation of engineers and scientists. We explored the opportunities for international collaboration and met with experts in Japan at JAXA, METI and Japan Space Systems, and we consulted broadly on international space solar power activities. We also considered the alignment between the development of space solar power and UK government priorities. As well as helping to de-risk net zero, its development sits very well with a range of other policies in energy security and resilience, economic growth and high-value jobs, building our space capability and markets, international partnerships post-Brexit, and environmental leadership. For all these reasons, it appears that the time could be right for the UK to embrace space solar power. So, in conclusion, it's been a broad-based independent study, and our overall finding is that the technology offers new and viable options for the UK to deliver net zero. It makes the cut as a good value investment where the benefits strongly outweigh the costs. Our main recommendation is to embed space solar power as a priority into key government policies, including net zero and the National Space Strategy, and many of our other recommendations flow from that. The government team is in the process of considering our recommendations, but it appears to have generated considerable excitement at senior levels, and we hope it may have some influence on UK policy. Our report may well have been published by the time of this conference. Meanwhile, we have started to assemble a broad coalition across industry and the research sector in the UK with the Space Energy Initiative to build momentum, encourage government and wider investment, reach out to international partners, and map out a programme of technology development. We have submitted ideas to the COP26 climate conference organisers for an international panel event and an exhibition of space solar power, and we're waiting to hear whether our proposals will be accepted. If space solar power does receive government backing, it will clearly have huge implication for the UK's space and energy sectors. It could really inspire the next generation. We hope that the UK, which has been a slow starter in this area, can join the community of nations starting to develop space solar power. And finally, we've been privileged to meet some really inspirational visionaries along this journey, engineers, entrepreneurs, scientists all over the world who have conceived these systems which could make a major contribution to our clean energy future. Thank you. That very briefly summarises what continues to be a fascinating journey.
Hello, everyone. I'm pleased to be back with Carlton Johnson. Carlton is a retired colonel in the U.S. Air Force. He is also a strategic leadership advisor, a cybersecurity expert, and has been for a number of years now the chairman of the board of governors in the National Space Society. So welcome, Carlton.
Thank you. Good to be back again.
Thank you. And we're here to talk about space security, because I'd rather not say the militarization of space, because that's a little dicey.
Thank you.
But I think what we're talking about is military activity in space, whether it's enforcement or assistance, probably a combination of both. But as we expand into space, there is this inevitable discussion of use of force, whether it's to ensure a country's national security with orbital assets, not necessarily aggressive moves, but if you have surveillance satellites, or in the case of the U.S., for instance, we use GPS for banking transactions. We use orbital observation to help us do our agriculture, global transport. Most developed countries are using these technologies to essentially run their entire economies. So these assets need to be protected. And when you've got a satellite either sitting in one spot 24/7 because it's in geosynchronous, or going overhead at a predictable rate every day, these things are vulnerable. Then we get out to the moon and we have perhaps mining claims in the future. We have strategic locations like an oxygen manufacturing plant, things like this. So I've just outlined a 4-hour discussion right there, and we don't have that kind of time, but how do you see this playing out?
You know, I think about this a lot, and there's a show, and you mentioned in a previous session how we're both science fiction people.
Right.
There's a show that's out right now called For All Mankind. I don't know if you had a chance to see it.
Oh, yes.
And there are some there's some interesting things that happen in that got me thinking about this in depth. In that particular scenario where the Russians got to the moon first and so forth as it evolved, there was that situation where a site was found and used by the U.S., and then it was taken over, by another entity. And so the question was, well, what do you do about it? And in that case, the U.S. decided, well, we're going to send in the Marines. First time you have Marines in space, and then they went in and they took it with guns in space. And I watched that episode and I thought, oh my gosh, this you could see this happening. And so this is how I kind of look at it. Number one, I'm all for, and I think if you talk to most military people, they're all for the peaceful evolution of humankind to do, whatever we're going to do, do what we're going to do in peace. That said, you have to plan for war because there's always somebody out there who's going to do something that's going to bring harm. So you have to plan for it. And as we look at advancing into space, we're going to have to look at what does that look like? Just like today, we have demarcations between federal and state, between the police force and the National Guard, between the National Guard and, in this case, the Coast Guard and the military actual. We have to look at that same type of environment. It may be a little bit different because it's in space, but notionally, if you have a settlement, you're going to have some type of law enforcement capability. If you have multiple settlements that are of a national nature, and then somebody decides that they want to go rogue and either attack or what have you, who's going to do that defense? Is it that guard unit? Is it going to be a military unit? You have to have those conversations now and work that out. And if we're smart about it, what I hope we do is we come up with the right type of mutual agreements with international entities that say, as we go out, we intend to work peacefully together. These are the treaties we will uphold. And it doesn't matter if I can't see you, meaning that if you're on Mars and you have the dilation in time, because of the distance, if I don't see you, you still need to adhere to these things. We need to focus on that and have those conversations now. I get a little concerned, but I get it. But I get a little concerned when I hear the conversation going between people of science and people in military. We just can't get along. And the reality is, just look at our world today. The politics drive what the military are going to do. So as long as you have politics, you're going to need a military.
So there will be the defensive roles. There will possibly be, I suppose, some offensive capability needed. But there's also the search and rescue and assistance for, like on Earth, the Army Corps of Engineers will come out during a big flood or something and help shore up a levee. Yeah. Do you see that as one entity that's doing both the defensive and the assistive roles, or is there a separate Space Force and Space Guard? And here I'm just talking about the U.S., but I suppose this applies to a global conversation as well.
Well, and you hit on something also that I think is really important. There are some people who all they think the military does is go out and bang, bang, shoot up things. Right. They do a lot more. There's a lot of humanitarian aid that happens. There's a lot of, like you said, search and rescue missions that happen. People don't hear about those things because they're not sensationalized, But to your point, yes, there are a lot of capabilities that military will bring forward that are confrontational in nature. So when you look at who's going to do that, again, I would look at how we're organized today. When you look at the Coast Guard, they have a very specific mission. And if you were to elevate that to space, it probably would be a very similar mission in a different environment. There's an ongoing conversation, and as an airman, I guess I have my opinion about this. But when you look at shows like Battlestar Galactica and so forth, those are kind of naval ships. So does the Navy have precedence in doing things in space versus the Air Force? Well, the Air Force will tell you, and I'm an airman, that's one of our domains. Space is one of our domains. So there are ongoing conversations about who's going to do what. And as Space Force itself evolves as an additional entity that works in that domain of space, you have Army, Marines, Navy, Air Force, Space Force, and my opinion, cyber, is another domain. Those domains have to look at how we're going to operate in that environment, both from a defensive, support, and where appropriate, offensive. So it's not going to be a one-shot-fits-all solution. It's going to be an evolution of the doctrine we have in place today in a new environment.
So let's make them even more complicated.
Bring it.
So let's say. So because I kind of think that there's a good chance that as the size of a settlement grows, mm-hmm. the enforcement of rules and laws will probably evolve with it. It might start off as a quasi-military operation or strictly a scientific operation with whatever kind of enforcement that has. But as it expands in size, it might end up needing its own police force and eventually its own military. So let's say we have 3 settlements coexisting side by side. We have one that's the European Union, one that's China and or Russia, and one that's the US and maybe another ally. So do they each have their own forces that protect that turf and have no common overlap? Or do we have this sort of, like a lot of people wish for, a kind of unified command or unified enforcement mechanism that's internationally comfortable operating within international norms? I mean, how do you think that works realistically in the next 10 to 20 years?
Well, and you keyed on something important. You time bounded it. So with the time bounding, I would submit to you, it's going to be exactly like we have here. It's going to be national and territorial based. If I could wave my hand, what I think would be better, once again, would be having those conversations now about international cooperation. Say, like, let's just use the moon let's use Mars as an example, because I'm going to pull this thread a little bit with an example, something from the show we talked about a lot. So you got the initial settlements that go out there, and let's just say we're in the year 2070, and in 2070 you do have exactly that. You have U.S. and another cooperative nation, Chinese and others. Still in 2070, I think we'll still have our national differences of opinion. So I suspect that you will see the U.S. sector being manned and supported and protected by U.S. forces. Or if it's a combined team, that coalition. Same thing with the others. So I think that's, and again, unless you set treaties that allow more cooperation, we're going to do exactly what we do now. Now, here's what I think it'll start changing. Let me expand out that time bounding, and I'm going to go into the expanse time bounding. As those settlements, those Martian settlements, are more detached from Earth, and 2 or 3 generations become born, they are no longer Earthlings, if you will. They are Martians. And I suspect you'll start seeing that they'll have a common bonding of, well, we're not really Chinese and Americans anymore. We're Martians, and we're working together for the betterment of Mars. And that's where I think you'll start seeing that transition, which now we get into what the expanse has to deal with. Depending on the treaties you set from day one, as you go from landing site to camp to settlement to settlements, and then settlements to nation states on that surface,
right?
That becomes a whole new entity. The treaties you had initially with Earth, are they still enforceable, especially if you declare independence? So it's going to have to be, we're going to have to think about this and just expect that as you go further out from terra firma, there's going to be an evolution of how people think about themselves and how they want to live. And they'll more than likely evolve for the domain they're in. And the further you go out, the less linkage they will have to Earth. So, and that gets into a whole new series of conversations about federations and all that other stuff. So getting back to what you said at another session about Gene Roddenberry, if the premise that we have is as we go forth, initially things are for the betterment of Earth, but now we're doing things for the betterment of humanity as it expands out. That is a different way of looking at things. And I think we get closer towards the utopian view where what we do is all based off of the advancement of humanity versus a nationality.
Well, it's interesting. There was recently an article in Ad Astra that was talking about some of these issues. Now that you brought them up, I want to play. They were comparing, for instance, the separation of the United States from Britain in the American War of Independence versus the way the Commonwealth, the British Commonwealth, evolved where you had these peaceful transitions where you got Canada and Australia and so forth. And then another person was discussing kind of the evolution of Singapore, which is almost, in a way, you could transplant it and make it into a space habitat, right? It's this very small nation state with a fairly diverse population, primarily Asian, but many different varieties of Asian inhabitants and others that coexist very well and successfully. And it's more authority driven than we're used to, but it seems to work there. So I've just kind of thrown you this broad, wet blanket of kind of non-questions, but this transition from, as you say, national entities extended out into space, that then become kind of maybe conjoined Earth entities extended out to space, that then maybe become an independent entity or republic. Do you have any thoughts on how that might play out beyond what you said?
Well, yeah,
in terms of the transition.
Yeah, as I kind of look at that, and again, looking at the examples you gave, the thing that the tyranny of distance will be the thing I think that helps to evolve and define that and how it plays out. And even looking at how we're organized today as various nations, one of the things that's happened, especially with COVID, the advancements in this case, cyber technology and IT have helped us to bridge the gap a little bit more. So whereas before ideologies were separated by land masses and the time it took to get to places, now we can have conversations and communications real time, and even in some cases translated. I saw a video the other day that was built during the COVID timeframe between U.S. and Japanese anime people and singers, and it was phenomenal. And when I saw this, I went, 10 years ago, 15 years ago, they could never collaborate like this. All the collaboration was done virtually. And what they ended up doing in this video was showing that we're not as different as we think. So as we remain on Earth with the expansion of technologies like that, I think that we're going to be coming, at least getting exposure to ideas faster and having the opportunity to learn together better. Now, as we go back out, getting to the heart of your question, as we go out as a planet, we're going to go out as nations. And so I think we'll have the exact same type of evolution. We'll go out, again, initially as nations, maybe with a common idea, scientific bond as an example, or what have you. But once again, that tyranny and distance settles in, we will default to what we are normally used to doing. There's a saying I used to have in the military that, again, I can't claim for myself, but I got from a mentor. You will not necessarily always rise to the occasion, but you will definitely always default to the basic level of training. And so as we go further out, I would like to think that we're going to evolve to that higher ideal, but I think we will default to the lower baser instincts, especially when survival kicks in. But once we get past that, and then we form communities, and those communities communicate and grow together, that's when I think we're going to see, again, that transformation we're talking about.
And then maybe eventually we become Astro Sapiens, and it's a whole different conversation at that point, eh?
Yeah, there's a again, I'm dating myself a little bit, but there's a book I found very insightful. It's called The Forever War. And for those of you who haven't read it, and I'll give a quick synopsis, humankind goes out, they find out through black hole technology that we can actually traverse different distances, and an initial settlement is destroyed. And the only thing they had was this video from the ship. So they found out, actually they had enemies. And so began this long war where we would go out and try to find these people. And it's all about this one, he was a scientist, but became a soldier astronaut. And as he was going to the different campaigns, the thing that happened was that the time dilation, Einstein's time dilation theory. So for 1 year in space, it was like 50 years on Earth. And so as he went back and forth between different campaigns, thousands of years were going by on Earth. When he got to the last campaign and came back, now he's a veteran, 1,000 years old, 1,000-year-old. The entity that we were supposed to be fighting had met now what was now called man on Earth, and they were all clones. And the reason they could finally understand each other was because the aliens were natural clones, and so the soldiers were now the aliens. And as I read that book, I thought, man, this is fascinating, because here, this man, the character, started on Earth as a human being, and after this long war and it's separated with time and space, now he's an alien on his own planet. So it just makes you wonder, kind of that old adage, home is where you hang your hat. When you're in space or deep space, wherever you are, that's home and that's who you are. And I think that's how it's going to evolve. I think that was very insightful of that writer.
Wow, that you have brilliantly brought us full circle. Thank you very much for that. It's been a pleasure, and we'll talk again soon. And everybody stay tuned for our next segment.
Thank you. Have a great day. Enjoy ISDC, everybody.
I'm Mark Hopkins, the CEO Emeritus of the National Space Society. When I was very young, like 3 or 4, and started thinking about things rather than just where to put my next foot, I very quickly developed this desire that I thought that the human race should expand in some sort of massive sense. And this led me to the idea of supporting space settlement. When I got to Caltech as an undergraduate, a couple of things were happening which were important. First of all, we had gotten to the moon, and the space program was collapsing because of funding being cut very radically. And secondly, there was lots of movements that were important on campus, such as the environmental movement, the civil rights movement, anti-war movement, etc. And so I got the idea that what we need is a space movement in order to support the space program. And then when I went off to Harvard as a graduate student in economics, I chose subdisciplines in economics which were particularly relevant to movements. And also with 3 other people set up the Harvard Radcliffe Committee for Space Economy. And we sat down and said, well, how can we really expand the human race massively through space? And one of our problems was, if you looked at the Mars and the Moon, which were sort of the obvious targets for space settlement, the combined land surface area of those two is just small compared to the Earth, and you're just not getting that much of a kick by settling those 2 places. And this was sort of depressing. Then along came O'Neill in his Physics Today article, and he pointed out that what you really want to settle is not the surface of various planets, but you want to build O'Neill cylinders, and you can build a very large number of these with the resources which are available in the solar system. The asteroids alone have enough resources to build cylinders so that their combined surface area of the interior of these cylinders is 1,000 times the land surface area of the Earth. All right, so now we're looking at something that's real for movement. However, being an economist, I wanted to know how you're going to pay for all this. So I called O'Neill up on the phone out of the blue. He didn't know me at all, and introduced myself and asked him a question. Turns out that O'Neill is a very British personality. And so he heard this question, and you could just feel him sort of taken aback. Who the hell was this young graduate student that was asking these questions? But anyway, we did get to talking, and he liked the fact that I was an economist and that I could help him do economic analysis. So he invited me to the 1975 NASA Ames summer study on space settlement. And this was done at Stanford University. We had 28 people there. of which 6 were graduate students, including myself. And I was personally very interested in whether these ideas of O'Neill were technically feasible. Because if they were, then we really could move forward with the movement. If they weren't, we had to do something different. And all of us worked very hard for 10 weeks in the study. I myself was working at approximately biological maximum. And towards the end of it, it became clear to me that yes, and to everybody else in the study, that yes, it was technically feasible. As a consequence of all that, I did the economics for the study, and the economics and the study itself led to the establishment of the L5 Society a couple months after the completion of the summer study. And my economics was published in T.A. Oppenheimer's book, Colonies in Space, which came out about the same time as O'Neill's famous book, The High Frontier, where he also used my economics for the basis of his arguments. And it was published in a lot of other places as well, such as the main journal of AIAA. That said, it was very clear very early that this was still a very fringy concept, space settlement, at the time. Give you an idea of just how fringy it was. A few months after the L5 Society started, 4 of the principals of the L5 Society went off to a Limits to Growth conference. At the time, Limits to Growth was a big deal. And we talked I talked during a break to one of the head guys at Limits to Growth, Dennis Meadows, and he was playing pool with a number of his friends. And I walked up to him and said, hey, look, you can get around the limits of growth by using the vast resources of space. So I started talking to him about this, and I noticed that as I talked to him, he was sort of walking away and around the pool table. And so I followed him, and then he'd sort of walk away a little bit further, then try to make another shot, and then I'd follow him a little bit further. And finally, it got through to my thick skull that this guy had walked around like 3/4 of the pool table. And the reason what was really going on is that this guy thought I was totally bonkers. Realizing that this concept was a fringe sort of thing, and I said, well, what does this mean for a movement? And it occurred to me that we would eventually win because powerful ideas do eventually win. However, it was going to take a while. And in the meantime, it was going to be fringy for a long time, but eventually it would win. And when that happened, there would be lots of debates between people who had different ideas about what the future of humanity should be, because our ideas with regard to space summit were threatening their vision of the future, or would threaten their vision of the future, like the limits to growth ideas and ideas of others as well. And therefore, there would be lots of debates about what's important for the future of the human race. And as a consequence, anticipating this, I wrote a bunch of articles in my column in Ad Astra, the magazine of the National Space Society, about answers to some of the objections which I figured would come forward. And these columns have been gathered on our website in the space movement section for anybody that's interested. So what's happened is space settlement has become increasingly mainstream because of the power of the ideas and the fact that we were right. And importantly, it has been really supercharged by the fact that some very important people have come out very strongly in favor of space settlement, such as Jeff Bezos, Elon Musk, the 2 richest people in the world, and in general, the Chinese government. And that's a big deal. As a consequence, the debate has begun. And the most important person who is opposed to space settlement at this point is Dan Doodley, a very noted professor at Johns Hopkins University, who has just completed a book called Dark Skies. And as a consequence of all this, I will be debating him later on in this conference in the 4th day. In my view, what's going to happen in the future is that NSS will be playing an increasingly important role with regards to debating what is the best future for humanity, and that we will eventually win these debates in the sense that most people will internalize the fact that space settlement is very likely to be a big part of the human future, and that this is a very good thing to happen.
Hey everyone, good afternoon, good morning, good evening from wherever you are in the world. My name is Hannah Rentz, and I'm currently a systems engineer with the Boeing Company. In my free time, I get to serve on the National Space Society Board of Directors and the Space Settlement Advocacy Committee. However, here today, I am with you to talk about the scientific feasibility of space settlement, a survey. So here at ISDC 21, I know we're in a little bit different of an environment. This is, quite different than the last time I spoke at ISDC back in 2018, but excited to be here today, even to be here in a virtual environment. So this is actually a project that I got to put together over the summer of 2021 and have been editing it all throughout the fall. I was supposed to spend last summer traveling, but due to the pandemic, that was not an option. So instead, I got to dive into this really incredible project. So first, looking at what is space settlement, just kind of for a brief overlook of our context here. I really looked at just long-term habitation in space. So I was very location agnostic. I looked at all locations, different iterations of locations as well, and really just focused on what is going to keep humans happy and healthy and sustaining over long periods of time, decades, if not generations. So that was kind of my basis of space settlement. And then looking at the scientific feasibility perspective. So that was a unique baseline that we gave space settlement to really bounce against the academic literature and figure out what level we're at and kind of what understanding we currently have. So we talked about a few different baselines similar to scientific feasibility. So as this is the first study kind of its kind that we've seen in a while, scientific feasibility was kind of our baseline to entry. We wanted to prove that the background science was there, it was understood, and mitigation methods for all of these challenges and solutions were feasible. They were achievable, something that we could implement. They might not have, level 9 technology readiness, but they're on their way there, and it's something that we can do. Other feasibility measures that we looked at, that were not covered in this paper, but are primed to be covered in future papers, include economic feasibility, engineering feasibility, and legal feasibility, to kind of look at space settlement from different perspectives and really understand where we are right now. So moving on to the next slide, I want to talk a little bit more about kind of how I got here with this paper, what process went into it, and why I'm here today. So initially last summer, there was a call that went out actually in 2019 looking for a graduate or an undergraduate student that could spend some time, some paid time, documenting every paper ever published in an academic journal about space settlement, which was kind of a huge goal, and really where that problem stemmed from is that space settlement is something that's been talked about for decades in conferences just like this. It's got a very well-known conference history, very well documented, and dozens of conferences have been held just focused on space settlement. However, when going to lobby to Congress and talking in other academic and professional settings, the question was raised of, oh, we don't really know what's out there for academic literature. We know Gerard O'Neill published his paper, The Colonization of Space, back in the 70s in Physics Today, but we don't really have a pulse, and we don't really know how many papers have been published in academic journals on space settlement since then. So who better than to pay somebody in school to go figure it out? So I got to dive into lots of literature, and there was so many topics that we'll begin diving into the next few slides, but they were such a breadth and depth of material that I really had to reach out to different experts in fields and kind of start to bounce papers off of them just as a gut check. I studied a lot of these topics throughout college, but needed that really expert level opinion and analysis of some of this material. So starting to dive into these next topics, let's move to the next slide and let's talk about radiation. So after kind of reviewing all the literature, it really appears that radiation isn't a solved problem, but it's an extraordinarily well understood problem. It's very well theoretically modeled. It's very well experimentally modeled and proven. And we're to the point now where we are tossing dozens of different materials into testing chambers to figure out what's the most effective, what kind of results are we getting against the wide variety of different kinds of radiation that we experience and that we're going to have to mitigate for in space to make sure that we stay within safe levels for humans and the habitat as a whole. So again, very well understood. This is it was one of the best first topics to dive into because there was such a breadth of knowledge and decades of research to build upon and kind of dive into. And it was, like I said, it's not a solved question per se, but it's very well understood. We're very comfortable with it. As with all of the challenges of space settlement, this is a very location-driven issue. So first off, looking at a lunar or Martian settlement, one of your first options and one of your best options for radiation protection is going to be regolith. And we know a decent amount of what regolith is made up of in different regions on both planetary bodies. So in different labs across the world, they've actually been able to test regolith simulants and figure out about how much it's going to take to adequately protect a settlement. Spoiler alert, it's about 2 meters. So they're also getting to test now, okay, if we process and modify this regolith versus sintering or other processing methods, how can we make it better? How can we move down from 2 meters into something a little bit more compact, something a little bit more maneuverable? So that is fascinating research that is going on right now. And an additional factor when looking at moving into either a large asteroid on the moon, on Mars, one of your other major options that is an essential part of the design is looking at topology-driven design, where you don't just build necessarily a house out in the middle of a plain on the moon. You need to start looking at building into craters, building into lunar rills, building into caverns, and all of the different unique geometries that you get on these rocky bodies to kind of maximize the amount of protection that's inherent in the settlement and make sure that you build enough in where you're protected. However, you're also still achieving natural light and natural views, which, especially after a year of quarantine, we know are essential to human health and happiness. Now, if you're looking at something like living in Leo, where you'll have a little bit of natural radiation protection, but you're going to need to beef it up, or somewhere out in the Lagrange points, somewhere out in free space, gray water is actually going to be one of your most locally available and abundant resources that you can use for protection. Now, depending on launch costs, you might be able to import some regolith from your nearest vendor, your nearest local supplier, but that's not necessarily going to be your best option. It's going to take some more detailed cost-benefit analysis and looking really into the specifics of your settlement, your population, your specific location, and what the market is like for those locally produced resources. But it's incredible now that we have the research and we have some of that initial backing, looking and comparing, okay, how does regolith protect you versus some of the exotic composites and different polymers that are being developed for radiation protection, as well as something as simple as water. So we've got a pretty good foundational understanding of how to build a structure to protect for radiation. Now, there are a little bit more exotic and a little bit more futuristic topics as far as radiation protection goes. So tardigrades, everybody's little favorite water bears that have a well-deserved reputation for being nearly indestructible. There are certain species of them, certain variants of them that are extraordinarily radiation resistant. They don't take on very many negative effects, no matter how much radiation they encounter. So there's also some biological research going on into the genetics and what part of their genome makes them so radiation protected, what makes them unique. And that opens the door to a wide variety of possibilities that we have the ability to expand upon in space settlement. So we're going in with the basis of designing our habitats to be radiation protected. But in the future, we have the option to expand and kind of test out this whole new field of biology and genetics that's rapidly evolving as we speak. So with radiation fairly well covered, let's move on to the next slide and talk about construction, materials, and habitat design. So these three are also intertwined, that I ended up mapping them in together because you can't talk about one without talking about the other. Again, these are very highly location dependent, and these were a little bit more well developed because we actually have experience doing construction in low Earth orbit with the International Space Station, which is an incredible resource. We gained invaluable knowledge when trying to build and learning how to build the International Space Station, but that modular build isn't necessarily going to work everywhere. We aren't going to be able to launch large components. At some point, the necessary components are going to be so large for some of these space settlements that we're going to have to learn how to manufacture and do construction at the location that we plan on living. So that's where the need for autonomous development is very great, where especially in places like low Earth orbit, where you have multiple dimensions to work with, you don't have the human resources or the safety for human resources to actually do some of this construction. You're going to rely on a network of a very large network, for one, of reliant sensors and highly accurate sensors to get enough feedback, to get enough data to know what's going on in that construction process and accurately and safely start to maneuver and build these pieces together. And this is one where we get to do some, and we can build on some lessons from Earth as far as construction in remote and extreme environments and the sensor development and the data intakes from that. So there's a lot of lessons to be learned there, but doing it in space is going to add just another layer of complexity. Additionally, when looking to build on things like the moon and the Mars, one of your major takeaways is that there's less gravity. There's no atmosphere to protect you, or very, very minimal atmosphere to protect you. But you do still have decades and centuries of foundational building knowledge that you're not just starting from scratch. You've got a little bit of experience. There's a significant amount of lessons that can be learned and are being learned from here on Earth. There was quite a bit of research as well as far as 3D printing and what 3D printing large habitats is going to look like. And while that's still very much more as far as the space application and the theoretical phase, it's a very, very strong prospect as far as building on these other planetary bodies. And especially with the idea of being able to manufacture and manipulate the locally abundant regolith in both of these locations, that's going to make 3D printing a very feasible option, very easy, and much more cost effective. And kind of wrapping this all in together, whenever looking to build and these habitats, you really have to focus also on the human aspect. And this is something where we're kind of lacking data, and I would like to see more research done, but it's a hard research to accomplish without actually living in space and kind of having that extra component of being removed from Earth and the additional challenges as far as the radiation, the scarcity of resources that you have, but making sure that whatever habitats we construct for the long term, for as far as maintenance perspectives and repair perspectives, but also just for the humans, so that humans feel comfortable living there for years and for decades and potentially raising a family there. That is a very important aspect of design that I didn't see as much research about as I would like to, but I think we will get more and more of as time goes on. So we can move to the next slide. And let's talk about gravity. So this was something I thought I knew a lot about coming into this research, living with gravity my entire life. However, in all of the research, this was by far the largest unknown. This is where most of the theoretical research was. There's very little implementation as far as what artificial gravity is going to look like, what is a safe level of gravity for humans, and there's a lot of unknowns. So looking at the artificial gravity versus the Moon-Mars gravity, there's currently research going on the International Space Station where they have a centrifuge, and they're sticking mice in the centrifuge for up to 30 to 45 days at different levels of gravity. So everything from 1/6 and 1/3 G to 1G and 2G, just to kind of begin that initial feedback of what does living, in a centrifuge do? How is that impacting the rat's health? How is that impacting diet and biology and all of the different factors of their lifestyle? And that's the kind of research that it's really going to take to be super comfortable determining of does the moon have enough gravity to live on for humans long term? Is this going to be safe? Same thing with Mars. Is 1/3 G enough for us to live and prosper? And we just don't know that. We think, we hope, I certainly hope, but we really need more research and more investigation to accomplish and answer those questions. But of course, this is the hardest field to do research in because you have to get outside. You have to get off of Earth to really actually begin to study. One thing is for certain though, we know that the complete microgravity of the International Space Station is just not going to be enough. We've got 2 decades now of research of astronauts spending long periods of time on the International Space Station, and the negative effects on our health have proven to us that it's simply not feasible for humans to live in microgravity long term. So we know we need gravity, we just don't know how much we need. And I'm really excited about the research on the International Space Station and the research that we are continuing to push and theorize and accomplish. I'm really excited to get to see, once we get to determine what is the safe level of gravity for humans. So we can go into the next slide as well. And here's another trio of topics that you can't talk about one without being intimately involved with the others, looking at agriculture, biology, and the closed ecosystems. So again, there are very complex interdependencies where every single decision you make here immediately has an impact in one of the others. So first, talking about agriculture, this is something we're just kind of getting comfortable doing on the International Space Station on a very, very small scale. A space settlement is going to take a huge scale operation to feed hundreds, thousands, or tens of thousands of people, which is going to take a very sophisticated and a very large organization. And actually, our best current take on this is Biosphere 2. And now I know there was some controversies around certain aspects of the project. However, the science that we got as far as maintaining those complex ecosystems over a significant period of time has held up. And the follow-up studies that have been published as far as taking the lessons learned from Biosphere 2 and actually implementing them have shown huge yields in growth and volume of food produced. So we've got some of the initial data, but this is another one that it's really hard to theoretically study topics like this because there's so many factors to take into account and so many factors to mitigate that it really takes going out and doing it, going out and trialing these relationships and these different ecosystems and biomes and the relationships between them and what works, changing one factor, what effect is it going to have short-term and long-term on the rest of the ecosystem? So again, we talked biology a little bit as far as the human health aspect, but some of the more interesting research I found on this topic as well was the study of viruses and bacteria on the International Space Station and how different those viruses and bacteria and fungi behave in a microgravity and in the space environment as well. So we're getting a better understanding of that. And we've got some theoretical knowledge, but again, we have a decently long way to go as far as more experimental and more implementation-based research. Now, finally, the closed ecosystems and really talking life support systems, very near and dear to our hearts in a very fascinating area of research. We've got again, 2 decades of experience on the International Space Station, and that's much more of a legacy style life support system. We've been able to gain and use the lessons learned from how maintainable, how reusable the life support system is on the International Space Station. And there's a host of new opportunities and new ideas for better ways to design a more effective and more efficient life support system. So I'm excited to see, as far as when humans return to the moon, return to Mars, what life support system is going to be used and what gains we've made since implementing the one on the ISS. And overall, one of the biggest issues proposed here is the scalability. So building a temporary habitat on the moon for 4 is a very different effort than building a space settlement for, say, 10,000 people on the lunar surface. It's going to take multiple iterations and many learning opportunities to make sure that we build a stable system, because it's not an inherently scalable science, which causes tons of fascinating research, but also challenges as far as going to actually pull this off. So we can move on to the next slide and talk about in situ resource utilization. So this is what I view as the golden ticket to space settlement. Space settlement cannot happen without effective ISRU. And what ISRU is really taking advantage of your local environment. So whatever minerals are in the regolith, being able to mine, refine, and manufacture, and make those into something else, make those into something that you can use, whether that is water or rocket fuel or radiation shielding or building materials. Kind of being able to reprocess the environment is the only way that we're actually going to be able to implement space settlement. It's simply not feasible any longer. No matter how low the cost of launch goes, we're going to have to take advantage of our local environment, where it does not make sense anymore to try and launch everything from Earth. So in situ resource utilization is another where we've got a lot of legacy technology here on Earth that we can build from and make minor tweaks to make it work for space. So especially any mining that's done in the really extreme environments, whether it's the bottom of the ocean in really hot environments and really cold environments, or with really tough materials, there's a lot of collaboration back and forth as far as making those technologies work in space and work in the unique environments that we plan on throwing them into. And the most exciting thing about ISRU right now is that we're actually doing it on Mars for the very first time. So Moxie launched on the Perseverance rover, and she is currently humming along and doing some biological ISRU and working on how to produce oxygen, breathable air eventually for human consumption. Not now on Mars, but kind of testing that concept and actually pulling off and achieving ISRU on another planet, which is hugely exciting. As someone who studied ISRU for the last few years, it is an incredible achievement. Very excited that we have finally made it. I very much thought we were first going to get ISRU on the moon, and I still think we're going to see large-scale ISRU first on the moon, but actually seeing it being done on Mars there's nothing like it. And so backing up a bit, that was a little bit more of a deep dive into some of the major challenges that we're looking at and some of the major areas for opportunity and for growth in space settlement. But there's a few things you'll notice we didn't talk about. And one of those is launch. And when writing out this paper, we kind of assumed launch is very well taken care of. It is far beyond being proven as scientifically feasible. There was nothing I could write, nothing that we needed to prove as far as launch. Additionally, we only looked at the academic literature. So there's tons of corporate research and development going on, and tons of additional research that's been published in conferences, in theses, in multiple different avenues throughout the years, but we really had to constrain our research just to the academic literature to kind of apply that specific scientific feasibility element to it. We really looked at the peer-reviewed journals. And overall, I came out feeling far more confident about space settlement than I was expecting to. I've been passionate about space settlement and pursuing the idea of space settlement ever since 2012 when I was first exposed to it. It's what I went to college with the intention of doing, and it's something that is near and dear to my heart, and I truly believe we're going to accomplish in my lifetime. However, I didn't know if that was just me being a passionate enthusiast and an engineer. I wasn't fully expecting to see the international academic community looking at space settlement as a whole, all of the different aspects of space settlement very in detail, very regularly, and they were all over it. And it was absolutely deeply exciting, just strengthened my passion and my belief that we are going to do this. We are going to establish long-term permanent homes off of Earth's surface onto other places. So thank you all for today. If you've got any questions, would love to answer them. Please feel free to find me on social media. I'm on all the major platforms, and we'll talk to you guys later. Thank you.
Hello, my name is Steve Akerley, and I am a space ambassador for the National Space Society. I am also a retired engineer, so I find that I have a lot of time to give presentations, and I'm leading a team of space ambassadors that try to educate the general public about the space and space exploration activities. There is an exciting new space age starting. Some of you have probably been seeing this in the news. It features a collaboration between legacy countries and companies, but also there is new private industry activity, and there are several what I would call space barons that are putting in billions of dollars supporting space launch activity and supporting NASA and competing with other legacy companies. The future generation of individuals growing up and coming through school are going to see more than just robotic and astronaut expeditions or excursions to the moon and the asteroid and Mars. That's not going to be good enough, because they're going to want to go too. And we've seen this in many of the youthful activities that we do at the ISDC. So there's going to be a lot of people that want to go into space. In fact, the human future will gradually grow into space and expand not just to the Earth-Moon system, but beyond to Mars and the rest of the solar system. And the nice thing about expanding into the solar system is there's a lot of resource available, and there's plenty of energy from the sun that's available. So we're going to grow into the space environment. It's important for us to think of Earth as our precious cradle, but we have grown, and we need to prepare to leave the cradle and go into the next frontier, if you will. So we will need to have a viable and growing industry to process the materials in space and use them to build new establishments, new space stations, new settlements, both in orbit and also on the moon surface and below the moon surface, as well as Mars, and going to basically harvest resources from the asteroids and other planets. So we also have to think about how we're going to sustain ourselves. This is not just us going into space and taking resources from Earth. We have to be able to take life with us, use life in the new environment. So we'll have to construct biospheres, very large biospheres, to recycle our air, our water, our waste, and to grow our food, and to make some of the other materials that we need for having a happy life. So we will be talking about that a little bit more as we go through this presentation, but also as you look at the rest of the ISDC presentations, look for the stories about life in space, the artwork that will depict the activities in space. And I think that one of the best things that we can do at this point is to branch off and look at some of the artwork that some other people have done. Now, one of our space ambassadors, Brian Burstig, is a professional artist. And you will see from his artwork that he's done a very elaborate job of depicting what a space station would look like on the surface of the moon. But there's been some interesting revelations over the last 20 years that there are a lot of what's known as skylights and lava tubes on the moon. And in this particular picture, you see a very good rendition of what a base would look like on the moon, but you also see in the upper left-hand corner what looks like a pit. Well, this pit is in fact a skylight. And that skylight opens up into a lava tube that is about 50 to 100 feet below the surface. And that lava tube runs for miles in each direction. So what we see on the surface is the surface rendition and surface establishment. But then the next slide will show us that there's more to this than just the surface base on the moon. We need to be able to get down into the lava tube and explore the lava tubes. None of the lava tubes have really been explored at all. So we only have the Earth version of these lava tubes to help us understand what we would expect to see. But now in this particular picture, you can see that there's a crane over the lava tube. There are some lava tubes that may have easier access, but most of them are in the form of the skylight. Now, in the next picture, we'll see what you could expect to see at the bottom of that skylight inside the lava tube. Now, the skylight was caused by a meteorite strike and basically stoved in the roof. And there's evidence on the moon that there's hundreds of these skylights, and there's evidence that some of these lava tubes have been totally collapsed. So obviously they're not of much use if they're totally collapsed. But one famous one is called the Hadley Rill. That is in fact a collapsed lava tube. But there are many more that are not collapsed, and this is one such picture. And so the first establishment inside the lava tube is an inflatable habitat that basically is supporting the exploration of the lava tube. And of course, you have the surface operations, and this is the subsurface operations. In the next slide, we take a step forward in time and ask ourselves, well, what might the inside of a lava tube be if we were to seal it off, give it an atmosphere, and provide some life? And this then is one such rendition. You can see a person in the left side of the tiles there, showing some scale. These lava tubes are much bigger than the ones that we would have here on Earth because the gravity is 1/6 that of the Earth. Plus, Earth has an environment, a weathering environment that basically erodes and helps collapse lava tubes. On the moon, that isn't so. So here you have a relatively accurate rendition of what the inside of a lava tube could be. In the next picture, we have yet another rendition of what the inside would look like. But notice in this particular case, at the top of the image, we have the skylight that has been sealed with a dome, a window. So here you can have natural sunlight coming in through a thick glass dome and providing natural lighting on the floor of the lava tube, and yet still provide you with the protection. Moving on to the next slide, we have yet another rendition of what the inside of a lava tube might look like. And this shows multiple levels, sort of like what you would see in a mall here on Earth. But once again, artificial light is provided and plants are growing, and the plants are an important part of this. Not only do they provide recycling of the air and water, but they also provide a pleasant environment, something that we will need in space. We need to be able to have life with us. Now, this, of course, does not address the growing of food. This is merely a picturesque mall type setting. But in the next pictures, we'll begin to see what we might be able to do initially with a lava tube. Now, this particular picture is one that I drew that shows the relative depth of a lava tube and the relative size based on some satellite images that were taken, and the lava tube is actually in basaltic rock, and it has a relatively thick basaltic rock roof. And in this image, I've closed off both ends of the lava tube. It's not a big lava tube. We have to start small, obviously, but the settlement inside this lava tube would include interconnected inflatable habitats on one side and hydroponics modules on the other. The hydroponics modules would be where most of the food and recycling of waste is done. But in a presentation I gave to an agricultural community, one of the questions was, well, where are you going to get the soil? And that actually is a very good question, because soil is very rich in microbes and nutrients and microscopic life that is important for sustaining our lives. So this is a lunar subsurface science station that basically is working on agricultural research to support human life. And we'll need to do that on a much larger scale as time goes on. So this, the next slide shows that this is not new. These ideas are not new, and there's quite a bit of recommended reading material that we're going to go over here very quickly. There is a classic that you see in the small print on this screen. The Moon is a Harsh Mistress by Robert Heinlein, and it's from 1966. And it's a fun, entertaining book to read, but it doesn't match what we know now about the Moon. Okay, it does not mention lava tubes. And in the next book called Welcome to Moon Base, you'll see that quite a few individuals have thought about what this might look like. And the cover of this particular book, Welcome to Moon Base, by Ben Bova, is something I consider to be a classic. So if you think of evolution of reading material, you would start with The Moon is a Harsh Mistress, and then evolve to Welcome to Moon Base. But then you would want to move on to the next reading material slide, which gives you 3 books. It talks about the current age. Okay, and the first book is called The Space Barons by Christian Davenport. A very good explanation of who the Space Barons are and what they're doing and why they're doing it. The second book recommended is The Space 2.0 by Rod Pyle. Gives a very good rendition of the current state of events and where we're going. And then there is a book by Robert Zubrin, The Case for Space, which is a very good reference book as well. And finally, the next slide is what I consider to be the penultimate reference for the Moon, and it's called The Moon, and there are 4 authors, David Schrunk and Mr. Sharp, Cooper, and Thangavilla. I probably didn't say his name properly, but the point is that this is probably one of the best reference books for what we can do on the moon, given 100 years or so. Very good reference book. And so I ask you to join the National Space Society in our efforts to educate the public about where we're going in space and why it's important. And I ask you to, if you're so inclined, consider becoming a space ambassador and help spread the word to the general public. So thank you for your time. I hope you found this informative. And if you would like me to speak to your group, certainly feel free to contact the National Space Society and we'll make it happen. Thank you.
Dear Earth, we're sorry for all the things we've done to you. We didn't mean to hurt you, but our needs got the best of us. Now we know there's a better way, one that will give us everything we need without harming you ever again. It's all about electricity. Space solar power. The sun provides clean and virtually limitless power 24 hours a day. Space solar power is clean, abundant, and the costs of collecting and transmitting it back to you, dear Earth, are negligible. And space solar power is virtually emissions-free and kind to you. Space solar power will help us to repair the climate and make you healthier than ever. To learn more and donate, go to go.nss.org/SSP.
Hello, everybody. Thank you for attending our virtual ISDC. We're all really looking forward to getting back together in person. And next year, we're going to have our event in Arlington, Virginia, and it'll be around Memorial Day weekend. And we're hoping Jeff can join us there again as well. We're very honored to have Jeff Mamber, the CEO of NanoRacks, tell us about some of the latest developments with NanoRacks. NanoRacks has been so instrumental in enabling capabilities on the International Space Station. Now they're reaching to the next level of items, which I'm really excited about. Jeff will touch base on that in a little bit. Jeff, thank you for coming to our virtual ISDC. We really appreciate it.
Sure. Thanks, Dave. It's great to be here, and sorry about the noise behind. I'm in downtown Washington. It's never a dull moment here, but it's great to be with you. And yeah, let's hope that next year it's way better. So
sounds like you have Formula One racing behind you there.
What can you do? It must be the president.
Yeah, there you go.
So do you want me to start with a little background on NanoRacks? Is that what?
Absolutely. Yeah. Give our audience a good feel for where you guys came from.
Thank you. Thanks, Dave. And thanks, everyone, for giving me this opportunity. So NanoRacks, for those of you who don't know, we started about 11 years ago. And it's hard for the younger people in my office to realize, but 11 years ago, there was no commercial pathway to the International Station, a space station. There was no way to, if you had an idea, if you had a project, if you were a university or high school student, if you were starting a new market in biopharmaceutical or small sats, there was no way to work on the International Space Station other than to try and reach out to NASA or to wait for a NASA program. And what NanoRacks really took the lead on, we were the first company in the world to own, market, and operate on behalf of our customers our own hardware on the space station. We started with little hardware we call mix sticks, which are sort of like big test tubes. We had nano labs, which are standardized laboratories on a platform in the CubeSat form factor. I made the decision early on. It was Dave Anderman's idea for the Nano Lab. I made the decision early on not to patent so that we would have an open source. And we do have some competition today, but it just has not developed the way we were hoping. And from those little beginnings of the mix sticks and the Nano Lab, we grew into an external platform that's still outside the space station. And then we came up with the CubeSat deployments, commercial CubeSat deployments from the space station. We've now deployed over close to 300 CubeSats, the first CubeSats of Planet Labs and Spire and GomSpace and other friends, and really proved the entire market, and provided really some great data points that led to the dedicated launch vehicles for CubeSat deployments. And today, as I think we'll talk about more, we're now looking at the coming era of private space stations. But before we get there, we're just still in the early days of our biggest achievement, and that is the arrival in December 2020, of the Bishop airlock. And that is a project that's a permanent addition to the International Space Station for cargo and satellites to go out of the station. It may also be able to go back in. It allows for research. We'll talk about some of that, I hope, our new space farming program. It has Wi-Fi, it has power, and somehow, by the grace of the gods of space, we self-funded this thing. It's over $20 million. Our partners included Boeing and Thales Alenia over in Italy, and others. It arrived at the station, and we turned it on, and it looks like it's working. And so we're all waiting for, which is not a trivial thing for something that complex, of that complexity. Brock Howe, our program manager, led the project from inception to the successful docking with the station. And so we're all very, very excited. It's the largest piece of private property on the space station that's in use. And so we now have customers in over 30 countries, and looking forward to the next chapters in space utilization. So that's where we are with NanoRacks.
Are you a landlord for a gateway to access from the space station to space and vice versa?
Well, I'd hesitate on using the word gateway because everyone at NASA then thinks you're talking about the cislunar. But yes, we see it as a toll booth. The previous gateway on the International Space Station is the Japanese, the JAXA airlock, which is wonderful. And we've deployed, as I said, several hundred satellites using it under treaty obligations between NASA and the Japanese government. But our Bishop airlock is 5 times larger. And it's an example of the power of the public-private partnership between the private sector and the space agencies. There was no government funding in the development of the airlock, and yet now the ISS has a shiny new piece of hardware on the station. what's the chance that the space agency, and I'd humbly say that if NASA was doing it or NASA contracted it out, it would be $30-40 million. And so, you know, what's the chance that NASA would have those funds at this time? We saw a niche. We took the chance. We have a very robust public-private partnership with NASA, and they've come in as a customer, but after we committed, after we were bending metal, after they saw the parameters, et cetera. And same with the European Space Agency. And we've recently signed our first commercial customer, I should say our first company, which is the Japanese robotic company, Gitai. And we're very excited to be working with them. So it's a wonderful example of the private sector coming in. The infrastructure was committed to and invested by the taxpayer, by Congress. And we're very, very proud to be making a permanent addition to the ISS.
Yeah, what's amazing is that you basically have applied standards that have become industry-wide, right? And now you're moving into a level with the Bishop airlock. Is that going to create a whole new set of standards for operating as an interface between the station and space?
You raise a really good point. One of the legacies of the ISS, in my view, is what we've learned about public-private partnerships. I mean, full stop. Okay, when we started at NanoRacks, there were very few examples of really how you handle emerging ecosystems. You had the COTS program for bringing cargo up. It's different. Okay, this is on a human occupied platform. Where do you entrust the private sector to contribute? How do they contribute? And then the other thing is you sort of grow into a niche. Several companies have approached us now about doing airlocks for private space stations. It's our dream to have our own private space station, but you know, we would be very pleased to contribute airlocks to other companies' platforms. So suddenly we're in instead of doing mixed sticks at $15,000 only, which is a great price, or Nanolabs a little more expensive, you're talking about airlocks that can range, you know, in tens of millions of dollars, depending on whether it's human rated and what sort of capabilities you want. So yes, I think it's a very good example of how the private sector can complement the government obligations or the government desires or policy.
Well, I take it, I don't know if you're free to discuss this, but are you in negotiation with Axiom?
Well, I wouldn't be free, but Axiom, I think, has most of Italy tied up, and they're doing their thing, and so I think they're relying mostly on Italian industry, from what I understand. So, and you know, Italians among the best in what they provide for space stations. And you know, I'm hopeful. It's a very ambitious project with Axiom, and I'm just hopeful they can pull that off.
Yeah, for sure. I figured you're both based in Houston, so there should be some interplay. So what's the most instrumental thing that the Bishop airlock has allowed to occur at the space station that wasn't an option before?
Great question. It was almost an aside from me, but you know, we have Wi-Fi, we have power, and certainly our bread and butter will be deployment of cargo. NASA's gotten excited because they're beginning to think about things that were not possible before. They're thinking, for example, of putting a big toolbox on the outside of the station. So if an astronaut during an EVA forgets a tool, there's now a tool chest out there. And they were limited in size with the JAXA airlock. We're looking at possibly deployment of trash, which right now has to wait for the cargo vehicles to come and be packed. There may be value in making a more hospitable environment for the space station, especially as we get more visitors. And whoever thought that, you know, we do the Bishop airlock to increase the life environment of the astronauts. We're in some great discussions about using it for research, basic research, and because it's very powerful, and you can have outside space environment access, and then you have Wi-Fi and you have power. So there's a whole bunch of things. One of the beautiful things about the industry and the community is everybody in this business is a thinker. Everybody, I don't want to use the word dreamer because that's different. Everybody's a thinker. And if you say, hey, we have this airlock and it has this capacity and it does this, you start to get inquiries from people. And NASA starts to say, wait a second, we could use it for this. We could use it for this. And so it's a wonderful part of the community, is that once you have some really, it's a variation on build it and they will come. But, you know, once you have a piece of real estate in space and as part of an ecosystem, in this case, the ecosystem is the ISS, and it's up there, well, there's going to be a lot of people saying, wait, I can use this for this.
Having fabulous unintended consequences.
Yeah, well, that's the story of NanoAct. Yeah, so, in fact, if I may slide into the Outpost program, because it was an unintended consequence. Several years ago, I mean, we all know the ISS is finite in its lifespan, and it's now been up there, you know, gosh, for 20 years, and things are beginning to wear, and you're beginning to get decay, as well as like the Bishop airlock. You want to have new generations, and you want to move beyond the ISS. And so we began to tinker about, man, it must be 3 years ago now, with why not bringing back the old Werner von Braun concept when he was the head of Marshall, of repurposing the fuel stage. And that in those days, it was the Saturn V. And the original plan of von Braun was that they would retrofit the fuel stage, the second stage of the Saturn V, on the ground, and that would be Skylab. And as you know, they have, and once the fuel is empty, you would have a human occupied space station. We call that wet lab. And NASA made the determination that it was technology did not allow it. And so they did what we call in the industry dry lab, where you outfit it on the ground. It was empty. It was not used as a fuel tank, and it went up in a Saturn V, and that became the Skylab program. So we wondered, why not look at advances in software, advances in robotics, and see if it's possible to do that retrofitting on the ground today, and have it used as a fuel tank. You know, once the fuel tank is empty, instead of throwing it away, instead of discarding it, use it as a space station. NASA was skeptical, and to their credit, they listened and listened, and they had looked at it with shuttle. For some of the folks watching this who remember, they looked at it with external tank, and they decided then that it was too dangerous. And to their credit, they gave us a study contract, and we teamed with Maxar, our friends in robotics. And they have robots that are on Mars today that are amazing. They spring to life and they do all sorts of things. And son of a gun, we had a kickoff at Marshall, and at least one of the people present had been there the last time NASA looked at it 25 years ago. And he listed all the reasons they were against it. And in 6 months, we successfully demonstrated that we could overcome those concerns. And today it is possible to take a fuel tank, scar it on the ground, put in robots, put in basic building blocks, fill it with the fuel, have it go to space, perform its function, and then instead of throwing it away, you can convert it into a space station. And so that is an ongoing program. We have a first in space coming up later this year on a SpaceX Falcon, where we're going to be testing some cutting. We've never really cut robotically metals in space, and that's a key part of the program. And so we're taking it step by step. And we're also working with ULA, Centaur, Vulcan, and we have multiple contracts. We're looking at it commercially, and it's not for the next few years, but we see the future of in-space colonization, utilization, commercial space stations being the reuse of in-space hardware, and that's one of the prime things we're working on in NanoAct.
So would Maxar be your instrument for tooling as far as the metal operations on orbit?
They're our current, and we like them, and we hope we continue, but we imagine we'll expand, and there'll be other robotics, and there'll be, we have software partners, and really what we bring to it that folks like is we're hardware neutral, and we know the customers. So you can have all the engineering, we're in the US government that passed the point of let's have a great engineering something. They like the fact that in NanoRacks, we can also bring in the customers. And so we're already speaking with customers now who say, if you can get me this in 2024 or 2023, if you give me this power, if you can get me 5 weeks of time, I'll pay for that. Okay, and then to quickly wrap in one other thing, we just opened up in Abu Dhabi now, the Starlab Oasis. And we just hired our first researchers, and we're going to be working in Abu Dhabi on space farming, as well as using the harsh environment of space for seeing if we can mitigate climate change and helping turn deserts green. And we see that the outpost program, as we call it, the repurposed upper stages, one of the first functions we have for it commercially is as greenhouses. And so we're very excited about it. So sort of wraps up the whole thing. We're using the ISS today. We know there's a new chapter coming. We don't think that in the future you'll manufacture the platforms on the ground. We want to be more green. We want to help eliminate the orbital debris, and for cost efficiencies, reuse the fuel tanks, reuse in-space hardware, and then we see ourselves as being one of the first customers with the greenhouses. So that's our ecosystem right now.
I can see NanoRack setting standards in terms of robotics and agriculture and space. You guys are leading the pack, and
right, and vertical farming, robotics. We want to be there on the moon. It's a niche. It's not the rockets. But we're in this for the long haul, and we think that food sustainability in space, food sustainability on the Earth, especially with climate change, is key. And one other thing quickly, I'm a little concerned that we show relevance of the space program. We in the business take it for granted. And I want to see more, and I want myself to be contributing more to what everyday people here on Earth would say, hey, this is good. They're using space for, Earth observation, monitoring, looking at environmental changes, maritime ships, ecological trends, and now with this NanoRacks program in Abu Dhabi, also to having researchers 24/7 looking at using the environment of space for research in ag tech, biopharma, and other things that up to now we've only done as one-shots. NanoRacks is going to be supporting with our partners, Abu Dhabi Investment Office, ADIO. We're going to be supporting a whole range of using the environment of space to help us on Earth with the problems we face.
Yeah, with the IAC event coming up in Dubai, I'm hoping to get there and see more of the developments. NanoRacks, what a fantastic company. Jeff, thank you so much for joining us. Look forward to meeting you in person again soon, and we really appreciate how you've contributed to our program.
Well, I appreciate it. I love what you guys do, and thanks for inviting me. And next year in person, let's do it, okay?
Yes, absolutely.
Right. Okay, take care.
All right. Thank you, Jeff. Bye-bye.
Bye-bye.
Hello, everyone. We're back with Steve Jurvetson. He is a venture capitalist, and he created Future Ventures, which is a fairly amazing achievement. Sits on the board of SpaceX and Tesla, I believe, correct?
Tesla just stepped down after about a decade last year. Yeah. But had been. So from the early days, so been from the beginning of Tesla and SpaceX and Planet Labs as well.
How many people could say I used to be on the Tesla board?
Oh, probably 2 or 3. Yeah.
Okay. Yeah. That's a pretty rarefied club. So anyway, you are very involved in financing new space across the board and a lot of other things, but to interest of us, especially new space. And I wanted to chat with you today a little bit about some of your thoughts looking ahead towards the human settlement of the solar system. and I guess we'll stop with the solar system. It'd be fun not to, but we've only got so much time, right? We talk a lot about moving out to the moon. We talk a lot about moving out to free space settlements, and especially about Mars. And thanks to Mr. Musk, we may soon be able to do at least 2 of those things, and perhaps Jeff Bezos will help us do the 3rd. We'll see. But I'm wondering about, and you've talked about this before, how do we sort of pick up the pace of doing this? I mean, we've been talking about it, well, since the early 20th century, but seriously since, I guess, the late 40s, early 50s. And yet so much still eludes us. I mean, we haven't even figured out if humans can reproduce in no gravity or lower gravity environments yet. There's a lot of things we have to figure out: reproduction, food, governance. So I'm going to turn it over to you. Sure. What do you think?
Well, those are all topics dear to my heart. I think it's an exciting time. I mean, if we step back, the first big, maybe obvious point to make is it hasn't felt this exciting for some time, right? And I think one of the reasons is the pace of experimentation has gone way up, right? When you have weekly launches, when you have some estimates by the FAA, for example, that humans are going to be going up or down almost every week in the near future, that's kind of an exciting time, right? We haven't had that crackle of excitement perhaps since Apollo. So that I think is the key point, and it drives perhaps part of what you were saying, is that if we could increase the rate of experimentation, the perceived and actual progress would go way up. People would see progress as it happens, versus like in business as a venture capitalist, we do not like to invest in companies that need to hunker down for a decade, then pop out the other side with some incredible accomplishment. And you can look at SpaceX as a canonical example of how better to do it, right? Interact with customers, both government and commercial, from the beginning, develop capabilities like the engine in the Falcon 1 that you roll into the Falcon 9, that you multi-stick for the Falcon Heavy, learn all kinds of, reusability kinds of control algorithms that you then can apply to Starship, and so forth. That's why I think SpaceX is so exciting, that they have moved to a software and simulation domain, what was a physical trial and error experimentation domain in the past. And they are continuing to rapidly increase the rate of experimentation. Gosh, what we could have done if we took that approach increasingly to lunar and Martian exploration. And I think that's where we're going to be going over the next 5 to 10 years, Moon and Mars respectively. So that's all exciting. There are a lot of, as you alluded to in your question, a lot of really important questions to be addressed. Everything from, as you say, governance to, if we want, for example, let me start with mammalian reproduction, which you mentioned. If we want to think of Mars as the route by which we can best make humanity a multiplanetary species, a very laudatory goal. By the way, it's good to have goals. It's good for a space program to have goals. Like what is it about the Moon and Mars that makes us want to go there, right? And having an economically self-sustaining base on the Moon and a fully self-sustaining base on Mars, or colony or civilization, however you want to look at it, is a good goal. So let's take the Mars civilization idea. It would be nice if we could reproduce on Mars, the human species. And we talk about becoming a multiplanetary species and including humans in the mix. It'd be good if that worked. It'd be good if we tested that, and we haven't. And so I'm actually talking with a small sat launch company about personally financing a mission where we put guinea pigs in a SpinSat and have webcams on them. So this would be the quick and dirty, less than $10 million easily, all in cost, to see if it works, right? Send up guinea pigs of all different stages of gestation, first week, second week. And I picked guinea pigs because I did a little research. Like I did a Google search, who's got the longest, sort of bake cycle, more like 60 days instead of 30 days for a rat. Anyway, and just see if they give a live birth. And if they don't, that would definitely motivate some more experiments. If they all give perfectly live births as documented by webcam, then hey, good, checkbox, that seems to work, right? Because there's a lot of scientists who think it might not, by the way.
Why is a longer gestation cycle better?
Just because of loading and being just a step closer to figuring out if something goes wrong, when does it go wrong, right? Mm-hmm. So imagine on the other extreme, you had a 1 week gestation cycle. You need to do payload loading and launch very quickly. And that I talked to this company, and next day integration might be possible, but it'd be nice if you had any launch delay that your whole experiment hasn't completely gone off the rails. Because what I'm talking about, not just assuming they can mate in space in zero gravity, that's going to be complicated. I'm thinking about artificial insemination at precise moments in advance. So you have, like barely pregnant to, last trimester, if you will, for the poor little guinea pigs. Now, there's all kinds of PETA and animal welfare questions that come up, but someone should do this experiment somewhere. Like this is a really inexpensive experiment to run, and there've been attempts in the past that got shot down. There's a as I learned from Chris Hadfield, there is a way you could in theory do this experiment on the ISS, but it introduces too much vibration supposedly to actually run the experiment, so it's just never been done. So, like, wow, what a big, bold, unanswered question. Do mammals reproduce or not in Mars? Oh, by the way, not just zero gravity. Spin it specifically for Martian gravity. That's the most important. And if you're curious and that works, you might as well try lunar as well. But I think it's less important for humanity to think about reproduction on the moon as on Mars, because ultimately I think the moon's going to be in a dependent outpost, because by the time we get big enough on the moon to be interesting, we'll already be on Mars, and that'll be the more interesting place for humanity to settle, if you will. Right.
So not that, excuse me, this is none of my business, but is this something that you would actually consider, that this particular experiment, a business investment or just an investment in the future because you're interested?
No, I just think about it as a nonprofit one-off. Be like, someone should do this. Like, wow, like sometimes when you think about in the philanthropy world, where is there a market failure? Either governments can't, for PR reasons, or just haven't for whatever reason. And the cost of launch is coming down so far. And, and soon there'll be satellite buses that are more widely available for things like this, that are circular, that fit in the fairing and could easily be spun up to whatever gravity you need, and such. Oh, and that comes back to the experimentation question. One of the reasons I think the moon is interesting as a waypost to Mars is specifically on the question of how rapidly can you learn? How rapidly can you run experiments? And so given both the proximity and of course the orbital dynamics, which is the moon's always there, whereas Mars, like every 26 months you're waiting for your next window for a good Mars program, you can just iterate on everything, energy harvesting, cellular agriculture. Obviously we're not gonna have cows or goats on Mars, and this isn't a vegetarian argument. It's just, that is a ridiculous proposition. You will instead grow the meat. Companies like Upside Farms and others are developing cellular ag alternatives. That's the obvious way we'll grow meat on Mars. Test that on the moon first, right? Test all kinds of things, basically food growing, habitats, radiation sheltering, all the things. And oh, by the way, maybe start to get some international standards around things like the power rail. Is it DC or AC? What are we going to breathe? Is it 21% oxygen, low pressure, or is it full on air with nitrogen? On Mars, you might not want the nitrogen. So there might be arguments looking ahead to Mars to say, let's breathe just pressurized. I mean, I'm not sure that's the answer, but it's a question that should be had. Like, do we want to make, all the airlocks and everything more interoperable by breathing the same stuff, if you will? Because the ISS is breathing air. Apollo obviously was, low pressure oxygen. So, there's energy. I think it would be interesting when you talk about expanding governmental regulatory bodies if the DOE and Nuclear Regulatory Commission would make the moon a bit of an unregulated zone for novel small nuclear infusion reactors. A little extra radiation off in some crater isn't nearly the same thing when you have no atmosphere. So wouldn't it be a wonderful testing ground for novel nuclear designs, especially portable fusion and fission reactors, next generation designs, of course, that could power the transition phase. Ultimately, you want, of course, a sustainable, just like on Earth, you're going to want a sustainable presence on Mars. You're going to want to do a lot of recycling. You're going to want a lot of solar, ideally. But day one, you can get a lot out of a nuclear reactor, as you know. And so it could very well be that we'll depend on that base load while we're building out all the other infrastructure and figuring out how best to build, ideally, energy harvesting devices with the local resources, right? That's what you really want to get to as best as possible. So that will take some time. And so I'm thinking back again to the moon as test bed, frequent iteration cycles, rapid learning cycles, and potentially a little less regulation.
So just to free flow here a little bit, what would your permanent solution to energy requirements on Mars be if you're trying to have a low environmental footprint?
That's a good question. So you have less solar flux, but less atmosphere. So, solar probably is a big part of the answer, but I think fusion would be ideal, right? I'm assuming that there's enough, I realize in that assumption that there's enough heavy isotopes in the frozen ice as there is in the ocean water on Earth. I haven't thought about that deeply enough, but I should find that out before I speculate on the answer. So let me just say, I don't know is the right answer to your question, but these are the exact questions that should be addressed. What are we going to eat? What's going to be the energy source? What's going to be, ideally the manufacturing methodology that we use? And another point I'm learning, we want to move as quickly as possible to local learning on Mars. So again, if this orbital dynamics is not solvable problem, right? This is not going to go away. This is like every roughly 2 years that we go to Mars with a new piece of equipment made on Earth. It's not only that we eventually want to make everything on Mars that we need on Mars to live and thrive. In the early days, we ideally want to be able to run as many experiments locally as possible. So we don't want to wait for some new, scientific payload to come from Earth to be able to answer new questions about what's going on Mars, to prospect for resources and what have you. We might want to think ahead. What's the way in which we can most easily bootstrap the pace of local experimentation, both in food production, exploration for resources, you name it, right? You want to do that locally. So you want gene synthesis machinery on Mars, right? So as you're doing all kinds of new, let's just say GMOs on Mars, right? We're going to optimize the plants and stuff to grow in that environment. You'd want to run those experiments locally very rapidly versus wait for some sort of dependency on Earth for genetic constructs, as an example. So again, today I think a lot of thinking should go in how can we increase the pace of learning as opposed to thinking we have the answers.
So assuming that will somehow work as you're discussing, just to sort of sidestep a little bit, something we also discussed previous, there's been a lot of conversation about how we close the cislunar, the argument for business in cislunar space, right? What we're going to do on the moon, what the benefits are, how much water will cost on a regular basis, fuel, all that kind of stuff. There's been some discussion of that with regard to Mars, and I'd be interested to hear your ideas on that. Is there any business case for Venus?
Yeah, so let's start with Venus. I think Venus is a wonderful thought experiment. It has more landmass than any other planetary body, which is kind of interesting, like more than Earth, if you exclude the oceans, right? But it's a freaking hot house hellhole, right? And boiling battery acid, pressures that are intense. It's really, interesting. Sort of, it's kind of like your drunk neighbor. You're like, just try not to look. What a greenhouse gas disaster gone wrong, right? Wow, would we want to march down that path? Now, my personal view is that Venus, in this, I say it's somewhat tongue-in-cheek, but not really, it should be an unregulated zone. Do whatever the hell you want, right? University projects that want to drop a biological payload to try to terraform Venus, just do it, right? Because how could you make it worse? I mean, at least for life as we like to see it, at least for human, let's say, outpost. Unregulated zones are really valuable. We don't have them that often. When the FAA grants one, when the FCC grants one, wow, you have this flourishing of innovation, right? Within those unregulated zones. And so I like the idea of Venus is, anything goes, wild, inner west, and when you say west or north, so like wild inner loop. And ultimately, like the fact that it's far and away the largest surface area is kind of interesting, at least, non-liquid surface area. So intriguing. A related point is governance. You alluded to it earlier, we haven't really spoken to it, but it is an interesting thought experiment of what governance should be. And the connection here in my mind is, I think that's also a place where ideally you could have experimentation. Like, do we really know a priori the best way to govern human society for human flourishing, right? We have the great experiments on Earth, but then they tend to get locked and loaded and they don't change much. Yeah. I'm thinking about an extension of the idea of, from charter schools, which most people have a sense of and either believe they're good experiments or not, but they certainly are experiments, right? The rate of learning societally can go up on what may or may not work in education if someone's running an experiment. Paul Romer, an economist, argues that we should have charter cities, that Shenzhen might be an interesting example so far, where the Chinese government said, look, we're going to have this new development area, which is currently rice paddies, back in the 80s. And we're going to allow Western companies to do business here openly. And oh, by the way, if you think they're going to exploit workers and this is bad for the Chinese, whatever culture, don't move there because no one's there now. I mean, effectively, no one's there now. This is going to be a place you go to if you buy into this governance modality. And of course, it's thriving. It's the economic, bright spot of China by far, outperforming other regions that didn't do the experiment. So take that idea a step further. A colony is a lot smaller than a city to start. And what is the best way to manage when you're 10 people or 100 people? It is not obviously capitalism with democracy, right? Somebody's got a monopoly on oxygen and is charging a market rate. It's a thought experiment. Oh boy, right? It's sort of obvious you're going to need a little different modality. It could be authoritarian. It could be more socialist than capitalist. Not that I like either of those at scale, but early on you might need that, right? An authoritarian like this. These are the rules. We've appointed a despot, and like maybe it's on some rotating schedule. Eventually, maybe you move to direct democracy. for a variety of reasons, as Elon has speculated, versus representative democracy. Are these transition phases? If so, at what scale? And my main point in thought that I want to contribute is, don't assume we have the answer and let's lock and load around one of these. I mean, I think it would be really wonderful, whether it's different countries doing colonies on Mars or just one initiative doing multiple outposts, trying completely different governance models for human flourishing, and then checking in every few years on like which one's doing better, right? Did the elected, one that went straight to direct democracy break down in some sort of uprising? What happened, right? Especially under the trials and tribulations of living in a harsh environment, right? There will be a lot of psychological stress. Right?
There's an interesting thought that comes to mind here, as you've probably read before. When before Wernher von Braun published the Mars Project back in 1953, it was actually the appendix to an absolutely wretched science fiction book he wrote called Mars: A Technical Tale, which is
I don't know this
title for you.
Yeah.
And in that book, the grand ruler of Mars was called the Elon.
Oh yes, that's the only thing I have heard. That's the only.
Do any ideas, perhaps? I'm just wondering.
Yeah, no, you need more than one, right? So, well, at least not, you don't need one, but you might want to run more than one experiment, even if you have one grand, supreme leader.
So I guess the governance of Venus, if somebody, if we ever have people there, they're probably going to be at drifting cloud cities. So if they misbehave enough, you just
toss them off the plank,
put them outside, or toss them off the platform. Yeah.
It's always good when you have a game plank for, you need to. Every society has had a way of deporting, put Napoleon on an island when you're not, instead of just killing people, as and in a way that helps in some cases in colonization, right? In other species of animals, there's the non-alpha male has to go off and make a living somewhere else, and this is how they propagate, right? So there's, joking aside, an argument for getting kicked out of the herd. Now, if you can't live on your own, that isn't obviously, as straightforward how that would work.
Well, it works very quickly, actually.
well, the resolution that you're not surviving, but the propagation across the planet, you might want to think about how you're going to keep. I mean, that's an interesting question. A plan for kicking someone out of the tribe. What is that?
Yeah. So, I'm just kind of taking a jumper here. Do you ever see Mars as being a profitable endeavor? Not. I mean, I know that's been discussed, SpaceX in particular, about there's money to be made on taking people there.
Right.
And bringing them home. So there's the idea.
More on taking them there.
Yeah, well, settlers, tourist trade, what have you. Is there a bigger business case there?
That's a great question. So it's the farther out you look, the less clear it's how we'll get there. But you could imagine that the long term would be like, what's the value of America if you were Isabella? And a related question, gosh, she didn't really capitalize on the majority of the upside, even though she had a venture deal with Columbus, interestingly. Percentage of the carried interest, all this would look like a standard venture investment. So let me start with the moon, because it's a little closer in time and space and a little perhaps easier to imagine. That tourism is compelling, by the way, because it can be a short-term trip, right? I personally want to do a EVA in low lunar orbit. Hasn't been done yet, but it should be a piece of cake compared to other things. Shoot through the valleys really low, like about as low or lower than Apollo 10 went. Would be great, and I'm not committing 2 years to it, right? So the thing about Mars is it's more of a colonization effort, or on the vacation side, it's more like a European vacation, right? Some Europeans will take 2-year vacations. I've never taken a vacation longer than a couple of weeks in my entire life, so that's a foreign concept to me. So I think a moon is a vacation spot. Mars more for settlement on average. I mean, of course, there'll be exceptions. There'll be plenty of exceptions, but in the long term. The moon offers all kinds of interesting revenue opportunities. You could, because of its proximity, you could do a railgun, of course, into low Earth orbit, and for water, it'd be cheaper to do that potentially than getting it off the Earth's surface. So for a low Earth orbit economy, the moon is an interesting adjunct, I think. Some interesting modeling we did back in 2014 when we had this sort of Open Lunar, which is now the Open Lunar Group, but we convened at our offices a group of NASA and business people to focus on what would it really cost using today's technology to build a lunar settlement that's economically self-sustaining. And the conclusion was single-digit billions. If you went all in with a SpaceX, inflatable habitat, let's go right to the lipid crater, kind of like, quick and dirty kind of solution. One of the crazy conclusions was the easiest, most predictable business model was reality television. Sadly, like, you'll make money on that. And then of course it gets the mind going, like the Hunger Games, the resources drop on the moon at distance and you're running to get them. But that's just me, of course, fantasizing on how off the rails reality television might take it. But more seriously, your question was about Mars, and there a much different question is, would you ever go to Mars to bring things back to Earth? And if not, what is it? I think it's more like the analogy to the Americas. It's like, building the new world for humanity. What is that worth? In some ways, uncalculable amounts, but also a little unclear. Does the ship that takes you there capitalize on all that one can do when you get there, right? Like, again, back by analogy to Isabella, remains to be seen on how that all works out, not to mention governance within existing space law and future space law, what international agreements form around that. A lot of great questions. And I think when you have the frontiers of the unknown, this is always the case. There's a lot of unanswered questions because no one's ever done anything quite like this before. I do think it is exciting. I think there'll be no end of people who will want to take on the charge of participating, whether or not they're clear what the business model is in the long term, right? Meaning the actual people to go there. It's not like you have to paint that picture to make it make sense. You have to just paint a picture that's survivable and you can thrive there. That's what matters. And I think we as a planet should embrace that wholeheartedly, one way or another. And we can leave it sort of like it's back again to the, first I forget what was this. I don't remember which comic strip. First we steal all the dwarves, steal all the pennies. Then there's like some unclarity. Then there's profits. I think it's one of those. But on the far end of it, you can see that there's a big price to be had. And so I come back to, like, if you're not bringing resources back to Earth, then you're, basically, other than the long distance tourists, what is the return payload, right? And I'm not sure it's going to pencil out that mining a Martian resource that we lack on Earth and lack on the moon and lack in the asteroid belt is going to make the most sense. And again, Mars may have a slight advantage, but it's got the gravity well in terms of mining versus mining, let's say, a Psyche or some other interesting asteroid. So again, I'm just rambling through this, but in my gut, thinking about some of these things on the fly, and I must say, it just feels to me that Mars is more of a civilizational expansion versus a resource extraction for Earth's benefit.
Yeah, and I guess we're nearing the end of our time here, but I guess there's also an argument to be made for, at least what I've tried to make, is Mars has a little bit more of a sense of place than the moon does, certainly than Venus does, because you can stand on, theoretically, you can stand on Mars for more than 10 minutes without it, being exterminated.
Sure.
But again, thanks so much. I really enjoy these talks, and
absolutely
again really soon.
Sure. Good news is we'll all be going there within our lifetime. If we just don't have any car accidents between now and then. This is something that's all going to unfold, and it's going to be fascinating to watch. I can't wait.
That's great. Thanks.
Thank you.
Hi, everyone. My name is Adam Moss, and this past year is my first year serving as a co-coordinator for what we call the JSC SSDC. That's the Johnson Space Center Space Settlement Design Competition. We hold this every year down in Houston, Texas, with students from both Iowa and Texas. And we are really glad to have some of those students here with us today from the winning team of our regional competition. We have Maggie and John and Colin. Hi, guys.
Hey.
Hi. Okay. Tell you what, could you maybe introduce yourself real quick and tell us where you're from?
Yep. Hi, everyone. So I'm John Moe, and I'm from Houston, Texas. This is my first time participating in the Space Settlement Design Competition, so I found it a thrill.
I'm Colin Houts. I'm from Sioux City West High School, and this is my third year competing in the Space Settlement Design Challenge.
Hi, everyone. My name is Maggie. I'm also from Houston, Texas. This is my second year competing in the SSDC competition, and my second year also being able to qualify for internationals. So I'm super excited to get to participate again.
Yeah, very good. Thanks for joining us today. If you're not familiar with the SSC, the Space Settlement Design Competition, what it basically is a industry simulation game. So we have approximately yearly about 200 students that compete. We split them into 4 companies, and then we give them 24 hours to meet all the requirements of a 7-page request for proposal, or RFP. This year, these students had to design a settlement that was going to be on Astoria, an asteroid in the asteroid belt. Maggie, you want to tell us a little bit about what you had to do for this RFP?
Yeah, so as someone who competed in the past, it's very obvious that every year the RFP is a little bit different. So that way we're kind of challenged to come up with new ideas every single year, and we're not allowed to kind of reuse the same settlement design as in previous competitions. So this year, the focus was on commercial ventures. So using the asteroid belt, we were able to create systems and structures that allowed us to mine on the asteroids, as well as allowing our settlement to serve as a commercial base for any other incoming or future projects that we might design. So some things that we had to really pay attention to was the difference between residential life and commercial life, as well as mitigating the sound pollution from either part.
Very good. And so this year's RFP had some challenges that maybe you hadn't faced in the past, correct, Maggie?
Yes, definitely. We had a lot more focus on commercial ventures rather than focusing on things like entertainment or living structures as in previous years.
Yeah, very good. Very good. So all these students are split into 4 different companies, and then your companies are split into divisions as well. Colin, would you mind telling us about the different divisions within your company and briefly what their jobs were?
Yeah, so the company's kind of in a branched out structure with, of course, we all vote on a president who leads the company and leads the meetings and all that stuff. And then there's vice presidents of engineering, which is like the kind of the whole systems and structures and operations. They kind of oversee that and make sure that everyone has a good idea of the plan and design of our settlement. And then on the other side is the vice president of marketing. And they're the whole presentation, how we're going to present our proposal and how we're going to make it so that the audience understands what we're proposing and can see why the strengths and the strengths of our proposal. And then on the engineering side, there's also 4 more groups, which are the 4 engineering sections: operations, structures, humans, and automation. And each of those groups does a different part or focuses on a different aspect of the settlement. And so like operations is food, water, infrastructure stuff. Automation is kind of like the name implies, automation, making sure that the menial tasks of the space station are taken care of by like robots and computer systems. Humans is the housing and entertainment and everything to make sure that the citizens of the settlement can have a nice and easygoing life. And then finally, structures is the whole structural system of the settlement, the design, how artificial gravity, all of that sort of stuff. And so like it kind of branches downward, and each of the leadership positions is voted on by the groups.
Yeah, very good. For me, the first time this year, one thing that really impressed me as a teacher is just the complexity of this task and how it forced everyone to work together. It was really neat to see. John, you guys had the winning presentation for this year's JSC SSDC. What do you feel set your company apart from the other companies this year?
I think one key feature that our company had that I didn't notice in any of the other ones was when we were presenting, we had a background that set us all apart from everyone else. Every single person that was presenting had a customized background that really showed who we were. And as a group, our background matched our slides, so everything was in sync. And then we also prepared somewhat of a script for each slide so we could go through smoothly.
Yeah, one thing I really remember about your proposal is kind of the branding you're talking about, right? And so there's actually a marketing and a branding component to this as well for this industry experience. So not only do you have all the engineering and the science behind it, but then you also have a lot of these soft skills and marketing and branding with it too. And you guys really excelled at that. So hats off to you. Maggie, you're a veteran of these competitions. What do you think is the best part of SSDC?
So I definitely think the best part and the most unique part about SSDC is probably the experience that we get in a real life simulation, especially with the time crunch with these RFPs. You really get 24 hours to break it all down, to decide on who gets to perform what tasks, to perform them, and then to put them all back together. Like you said earlier, with the branding and the company logos, it's really a unique experience that I don't really get to experience in school, especially with a lot of classroom-based learning where it's kind of problem solution, but here it takes a lot of that company structure, learning how to work together. Even when everybody's feeling that pressure and everybody's a little tired towards the end, we still need to put together, especially as the deadline might draw closer and everybody's a little, feeling the pressure. And I also think that just the content of the entire competition, the training sessions beforehand, as well as the tips that the red team and pink team reviewers are able to give us as we run our presentations by them, they give us a lot of invaluable kind of industry experience that we don't really get to experience elsewhere. So I definitely think that's the best part of the competition.
Yeah, you made a great point. One thing I think is fantastic with this competition is all the exposure you get to industry professionals, engineers from all different walks of life and all different corporations working side by side with these students is a really powerful learning experience for you guys. So you mentioned the red team and the pink team. Maggie, can you tell us a little bit more about what that is?
Yeah, so especially when you compete at internationals, to a lesser degree in regionals because the time is a little shorter, but during some of the competitions where we might have more than just 24 hours to work on our presentation, somewhere about halfway and about 80% of the way through the competition, we're allowed to run something called red team and pink team. So what that is that they bring in industry professionals, like you mentioned, from Boeing and from we had last year people from Boeing and from places like the Dow chemical plants who were able to guide us on the more technical aspects of our presentation and places where we might need a little more guidance. And we were able to basically mock our entire slide deck and our presentation to them in the same time frame, in the same situation that we would have done so officially, and had them give us feedback. So they were able to tell us very technical comments as well as comments on our presentation skills and our overall, like you said, company branding. They were able to pull in industry professionals from each of these areas to give us feedback. And I definitely think that helped us increase the quality of our ultimate presentation, definitely by a lot. And also helped us just in general talk to people who were more knowledgeable than we were about certain technical aspects. So for example, I was able to email back and forth with a Boeing engineer last year about dust mitigation systems, which is something I definitely wouldn't have been able to do if it hadn't been for SSDC.
Yeah, the volunteer base for these SSDCs is just a critical part of these competitions, and it is really cool. So thanks for sharing about that. John, what do you think, as a veteran as well as SSDCs, what do you think is the hardest part in these competitions?
Since this was my first time, I found simply the time crunch, since I've never experienced truly something where I get assigned it and then within 24 hours I have to complete it. This is my first time with that. So that was the most challenging thing. Managing the time with such a big group. These are things that we don't normally do in our day-to-day lives, because in classes, it's normally like small groups, maybe up to 3 people. Most assignments are 1 person, and you get assigned it and you have like 3 weeks to finish it. So it's mainly about how you split your time up within 3 weeks. But in this situation, we have 24 hours to plan everything and complete it and combine it as a group fluidly. And communicating between such a large group is never easy. There are many like clashes, and you have to really just talk it out and figure out what can be the best way to cooperate together.
Yeah. So John, tell us a little bit about that, because that communication between departments is a huge deal. So I don't want you to throw anybody under the bus, okay, or point any fingers, but Could you give us an example where maybe some communication had to happen?
Okay, so since there's 4 different branches, and the way we set it out is each branch had a head, so that helped with communication. So the branches would feed to the heads would feed upwards. That made it a lot easier. So, but if it was not split like that, it would have been much worse. So since we split it like that, we had groups coming up. We had we had like hourly meetings where we would combine, have the heads talk about what they just went through and what we'd continue moving forwards with. So that way we could plan everything out before something happened.
Yeah, and I want to make a note that your company structure was up to you as students, right? Each company had a slightly different structure, and it was interesting as an observer, as an adult from the outside, you could see that some structures worked a lot better than others. And that's very common in industry as well. So that's another neat part of this competition. Colin, you've been part of both in-person and virtual competitions now. Do you like one better than the other? Or what's some advantages of each? What do you think?
Yeah. So I definitely think that the in-person has a lot of advantages. I mean, you get to go down to the Johnson Space Center and see where NASA engineers work and just carry out their day-to-day operations. And that's really, really cool. And you get to go visit Houston, especially for us Iowa students. And that's a really good advantage. One disadvantage of that is, for some students, you have to drive a really long way. So you're a little tired before and after the competition, which can affect how late you can stay up and how much energy you have to put towards the competition. While on the other side, the online portion, you are at your own house, so you have your own space and you can be very comfortable working with others. And things can move. This last year, things went really smoothly online. The first year, so I've done one competition in person and 2 online. The first time I did it online, it was right after the pandemic started. So everyone was still kind of getting used to the online stuff. So it didn't go as smoothly, but we also had more time. But this year it went really smoothly and we could all kind of communicate in our own individual spaces. And when we all came together, it all turned out really well. And so I think both the online and in person are really good options for the competition. And as they were set up in both ways, everyone could kind of work together. And even though there's disadvantages and advantages to both sides, it went really well with the design challenge.
Oh, very good. Very good. So we're running short on time. First of all, I want to congratulate all 3 of you on being invited to participate in the international competition that's happening in Florida in July. You guys are going to do great. And I look forward to meeting some of you there as well in person instead of just virtually. We have time for one last question. So if you had just one sentence, what's one piece of advice really quickly you would give to future competitors in a space settlement design competition?
I think for me, it would just be keep your mind open and be creative. There were a lot of issues that, I thought that I had set solutions for that we found better solutions for. So just keep your mind open, be creative, and be willing to accept the challenge.
Very good. Thank you, Maggie. How about you, John?
I think you should definitely get enough rest the night before, and then also don't close yourself off from advice from others. I think everyone's trying to help each other out for the competition. And that's your friends. Your friends are your best.
Very good. Colin?
I would just kind of say to explore new things and look for options that you might not think of. So kind of look outside the box. Don't just go for the solution you first think of or that you've used sometime else.
Mm-hmm. Very good. So, hey, I want to thank all 3 of you for your time, for sharing your experiences with us. We want to wish you luck at the international competition in Florida. We'd also like to thank everyone viewing from the NSS for your continued support of this program and all those industry engineers and professionals that have been helping us out. We really appreciate it. This is a one-of-a-kind thing for our students. And as an educator, I want to thank you for that. So thank you, everybody. See you later.
Hello, everyone. My name is Rod Pyle. I'm the editor-in-chief of Ad Astra magazine and have been doing some of the interviews on ISDC. I want to thank you all for sticking with us for these last 3 days. It's been an awful lot of fun for us. I hope it was for you too. If you enjoyed what you saw, I'd like to encourage you to join the National Space Society at space.nss.org. And if you're already a member, of course, as you know, you can always donate more because we like that. So we're here for our live Q&A. Instructions on how to submit your instructions are scrolling across your questions are scrolling across the bottom. And we rounded up some of our best speakers to hang out with you for the next hour or so. And I just can't tell you how happy I am to be here. The one person you haven't seen speak so far is in the middle. That's Aggie Coburn. She's the director of publications of the National Space Society and my partner in crime for the magazine, part of our very, very small staff. So let's launch right into it. We've got some questions coming in, but I'd like to start before we take an outside question. I'd like to ask Scott Bolton a question, who's the PI for the Juno mission to Jupiter. Scott, you recently did a flyby of Ganymede, which was pretty darned exciting, and those first pictures are breathtaking. And I wonder if you could talk about that a little bit and let us know when that was planned and the big structure of things.
Yeah, that was actually a great surprise for us. So last year we started looking at the possibility of an extended mission. So we were coming up, and in fact this summer and this next month, we would have nominally ended the mission and we would have, for planetary protection reasons, changed the orbit and gone into Jupiter. But everything was healthy and everything was still working, and so NASA opened up the possibility of an extended mission. We started looking at the orbits, and as our orbit gets twisted around, we were crossing the plane where the satellites orbit closer and closer to Jupiter. It used to be we would pass them pretty far out, and we found out that basically just at the very end of the prime mission and at the beginning of the extended mission, we had the potential to pass by Ganymede. And actually use it to change our orbit and steer us so that we would then pass by Europa and then Io and have multiple flybys of these things. And so we jumped at it, right? We were basically a Jupiter-centric mission. We were focused on learning about Jupiter and the origin of the solar system and what's inside Jupiter. And all of a sudden, we were able to become like a full system explorer. Go by the satellites, we go into the rings. I mean, it was really exciting to just, even though our instruments are designed to investigate Jupiter, it turns out they're actually ideal to go look at Ganymede and Europa and Io as well. And so, you saw some of the early results, and those images were spectacular. We flew by at about 1,000 kilometers above Ganymede, and then about 15 hours later, we were flying by Jupiter. And so it was a wang bang, really fast thing. But it was great. And we're sitting there digesting the data, trying to figure out, all this new ideas. We mapped the ice shell so we can see where potentially the ice is thinner or how it changes in composition with the different colors. You could see all these features on Ganymede, giant craters, and also, these linear features that are sometimes thought to be associated with tectonic faults or in the ice, And so we mapped all that. We're busy looking to see if anything's changed since Voyager Galileo days. Just a great opportunity. I'm really looking forward to all of the satellite flybys that we're going to have over the next few years.
Well, it's so exciting that you've got these kind of timestamps now, right? I mean, we haven't been to the outer solar system much, but you have some things decades apart where you can actually make comparisons now, which is pretty exciting. Hank, I've got a question for you, and then I'm going to turn it over to Dave. I got a couple of emails while the ISDC was running asking how just normal folks can sign up for the high seas simulation, which at this point is primarily lunar simulation. So could you talk about that just a bit?
Sure. The easy way is to go to internationalmoonbasealliance.com, IMA, International Moon-Based Alliance. Or highseas.com, HI-SEAS.com or .org, I forget. But anyone can go as long as you have something to do while you're on faux Mars or faux Moon.
Do they need to provide you with some kind of a research proposal, or are there any special qualifications?
Well, we can't just go up there and party. You know, our lease with the with the Department of Land and Natural Resources that we actually do science up there, and so it's not an Airbnb. It's a serious science mission, and you have to have something that you want to find out. You can become part of a mission that is doing something, or you can have your own mission. And yeah, we don't like people up there who have nothing to do, but you know, contemplate their navels. That is something we found out in the Mars missions is you got to keep people busy or they go crazy.
Hank, how many people are up there at a time?
Well, there's 6 people, but the way we set it up now is one of them is always us, and the reason for that is because otherwise we'd have to train them for a week before sending them up, and that is just too much work and too much time. So by having one of us on the crew, it just means that people don't wreck things or do things wrong, or when something does go wrong, they know what to do. So that takes the place of training.
So Dave, I fibbed. I have one more question. I'm sorry. Speaking of training for harsh environments, Pascal, you have an operation in a slightly further reach up in the Arctic. What's happening with the Houghton Mars project?
Well, the Houghton Mars project is a Moon and Mars analog field research project. We're based on Devon Island in the high Arctic. Devon, most people know, is the largest uninhabited island on Earth. It's about the size of West Virginia or Croatia, in case that's a reference for any of you. Let's see. It's actually less populated than even West Virginia, if you can imagine that. It also is the largest continuous expanse of polar rocky desert. So, you know, it's a rocky desert is a climate environment that's even harsher than tundra. Tundra is still grassy. Alaska is mostly tundra. Beyond tundra, you get to the rocky polar desert. And so that's what Devon Island is. And then it has this large meteorite impact crater, Houghton Crater. So we've been going up there every summer for the past 25 years. Can't believe it's been a quarter century. And in fact, this past year we couldn't go because of COVID. And this coming summer, it's still pretty iffy. So we'll see what happens. But we have a backup plan to go somewhere closer. We'll just keep it at that. So,
and could you just talk a little bit about some of the things when you're up there? You're testing a lot of technology, some of it from NASA. What are the kind of activities that you do up there in terms of hardware?
Yeah, so you know we've done relatively few full up simulations in the sense that we don't lock up crews and have them simulate being on the Moon or Mars, except in very specific settings. For example, we'll do a pressurized rover traverse with one of our livable Humvees. So then we have a really well constrained environment to do the simulation in. But the rest of the time, we're just going about our geological field work. And it's through the methods that we use, the practice of doing this, that we then extrapolate to lessons learned for the Moon and Mars. And I think one of the most exciting lessons so far that we sort of come up with, or solution that we've come up with for Mars exploration is how to make the spacesuit lighter, because it's really a big challenge. And I talked about this in my chat with you this morning, Rod. But the bottom line is, we right now have a spacesuit that weighs about 300 pounds on Earth, and we really need to bring that mass down to about 150 on Earth, so that by the time we're on Mars, that thing would have a felt weight of only 60 pounds, which is still considerable. And so the only way to do this is to offload stuff. And we need, therefore, smaller oxygen tanks, which are heavy in your backpack. We need smaller batteries that are heavy in your backpack. We need we need to recycle the water, or replenish the water, and carry less water in the suit. So the solution really is to not view you and wearing a spacesuit as the exploration unit, but you and your ATV, your rover, your unpressurized rover becomes your mobile backpack, and it carries the reserves. It follows you. We can do self-driving following robots easily now. And it's not one of those robots that you cannot take over and drive yourself. it's a drivable ATV. It's your main unpressurized rover. So we have this concept that turns into a concept of operation where, for Mars at least, you'll have each astronaut having their own ATV, and that ATV will essentially be a backpack that can drive itself and follow you. So you will always not be very far from extra reserves of oxygen, water, and batteries.
Well, I'm trying to find a way to offload about 40 pounds myself, so if you find any secrets, do let me know. Dave?
Well, I've always said that going to Mars is a good weight loss program.
Yeah, but
pretty instantaneous.
Same. Dave, you want to toss out our first question?
Sure. I want to follow up on that. So, Dava Newman at MIT, former NASA administrator. So she's been working on counter pressure spacesuits that are lightweight. Is there any interaction with Dava in terms of what you're doing?
Yeah, and in fact, Dava is on the board of the SETI Institute where I work, and so we do communicate. We haven't really sat down lately and sort of compared notes on spacesuit systems. She's working, I think, in solutions that will more directly affect the part that will remain on the astronaut, the suit itself. Whereas on our end so far, we've been working on the life support system, which is what you sort of have to lug around on your back, and that is what we want to offload onto a vehicle that follows you. That's sort of
yeah. It'd be like your puppy dog following you around, right?
Yeah, but Dava is doing really interesting work, and we're all on board that as well.
Yeah. All right. Hey, Bruce, you had a wonderful opportunity to spend some time with Steve Jurvetson, and it was really fascinating to hear your conversation with him. But I imagine there's a little sidebar chats that our audience might be intrigued to hear about. Are there insights you could share with us that you learned from Steve?
Yeah, be careful the hobbies you pick because they can have repercussions. I mean, I don't know how much you spend on that, but those pictures you saw today, that represents a lot of money. But anyway, it's good. It's good to have resources. No, it's just super cool. As a lifelong space cadet and all that. I was a kid when to date myself, John Glenn went up on my 10th birthday. So so that kind of got me started on this whole thing. So when you look at all of this history and all the people, and he was talking about some of these people, and I've actually had the opportunity over the years to meet some of these people and to see where some of this thing was, where this stuff came from and all that. And so it was just a real thrill to be just that close to so much history. It was just truly breathtaking.
Yeah, no doubt. I mean, yeah, it has to be pretty inspiring to be in that environment and just soak all that up. What aspect of his little museum did you find most intriguing?
It's the little kind of sidebar stories that go along with it and everything. Like when he showed you some of the Russian stuff, and that they literally had a machine gun up there, and the Cold War really wasn't going to be so cold, maybe. So the mixture of the Soviet and the Russian and the American space programs was just interesting, and to see. In some ways, how much things have advanced, and in other ways, how things really haven't advanced that much. So it's really going to be interesting. What I'm excited is we can now look back at our half century of space exploration and all that. It's going to be really fascinating to me what's going to look like in another half century when the next generation of people are going to be sitting around and hopefully at this conference talking about what they did. Those crazy people back in the 2020s, look at what they did.
Yeah.
I don't want to nerd out too much here, and I imagine Isaac knows about this too, but that machine gun was on one of the Salyut stations, the early Soviet stations. It was a 20 millimeter Richter anti-aircraft gun that came from the back of a Russian bomber. And they wanted to test it during that flight, but the cosmonauts kept saying, let's wait. So finally, ground control said, okay, I'll tell you what, after you guys leave the station, we'll fire the thing. So they left and they fired it remotely. And you had to aim the whole station to aim the gun. It didn't have a pivot on it because they couldn't figure out the air seals. So they shot the thing. The station nudged over by, I'm not sure how far, a number of inches anyway from the recoil. And it worked, but nobody's quite sure how long those bullets stayed in orbit. So that was kind of an interesting experiment that may come around to literally snag us in hindsight later on. I got a question here for everybody.
Hey, Rod, would you give me a minute? I just want to put a word out to our viewers. Please submit questions in the chat box, and we'll get those to our panelists. So please get those questions in, and we'll read them for you.
Okay, I've got one off of the space.com feed here.
Oh, you did? All right.
Yeah, somebody who's seen some of Scott's artistic work. So besides being a brilliant engineer, brilliant scientist, Scott Bolton is also quite the artist, working with some very big names in the music industry, among other things. Wondering of the rest of you, I know, Pascal, you're a very dedicated painter. Anybody else involved in an artistic way with their space endeavors? A lot of face scratching going on here.
See, I get to work but I just want to say that I really resent people with talent, you know.
So I directed mine towards writing because I realized early on I didn't have the mind to be a scientist after a year and a half in the UCLA astronomy department, having a severe disagreement with advanced calculus. I thought, okay, I'm going to have to become a communicator. So I was an early but less talented version of Isaac Arthur, I guess, and aimed it towards doing books, which have been fun. But one thing that always eluded me was visual art. And as I think you alluded to, Bruce, I kind of have a dirty little secret envy for Pascal and his ability to paint, and Scott for his ability to put together these incredible projects that he does. Scott, what are you working on now?
Well, I'm working on a number of things, but most of them are video-oriented stuff, space videos that I'm putting together for different musicians, and they might use them in concerts and things like that. But also I'm putting together an animation of what it's like to be on board Juno. If you had a seat on the spacecraft, what would you see if you were flying by Ganymede and Jupiter? So that's the project I'm right at the edge of right now. Hoping to finish that soon. And then I do a little bit of painting and things like that as well. And have gotten connected in with people that even take the amazing space photos and they make quilts or out of them. It's just incredible. I mean, there's a lady out there that uses not only Juno images but images of Mars, Hubble telescope. She's just inspired by it, and some of her quilts and things are just incredible. So I mean, I think art takes all kinds of modes and inspires you. I believe strongly in combining these things together, to the creative and the analytical. So, and I did start off as an engineer, so you weren't totally wrong. Good. I started off as an aerospace engineer.
Okay. Pascal, I don't want to put words in your mouth, but I believe you were inspired early on by the work of Chesley Bonestell, one of the premier space artists of the 20th century.
Well, I'm not worthy, but yeah, I was inspired by Chesley. Well, and then, even before him, because I grew up in France, I was inspired also by Lucien Rudeau, who was an astronomer and who actually did the first, really realistic paintings of the surfaces of the planets and their moons. And he was, in some sense, an inspiration to Chesley Bonestell as well. He was a generation earlier. Lucien Rudeau.
Well, the reason I mentioned Bonestell was because I've seen a painting or two that you've done kind of updating the Von Braun mission, where we were going to hurl huge gliders into the Martian atmosphere, which ain't much of an atmosphere, and they probably wouldn't have had a very good day had they done that. How did you update those to reflect what you knew?
Well, Chesley Bonestell has this famous painting that's at the Air and Space Museum, actually. It's in their permanent collection, called Exploring Mars. And it's a scene where you see a pressurized rover, the way it was conceived in the 50s. It looked like a post-war tank, actually, on tracks. It had some astronauts that were in spacesuits, but they looked like high-altitude flight suits, like the spacesuits of the 50s. and then you had this big shiny rocket that ironically does look like a starship now, but wasn't quite a starship because it had to get to Mars and onto Mars by coming in as part of the fuselage of a large aircraft. And then the whole fuselage section was then erected to become the ascent stage. Then, of course, there were other things that were, in Chesley's painting that would not fly, so to speak now. Like he had his base sitting right at the base of the rocket, so we now know that with the exhaust plume that would essentially blow off the whole the whole settlement that was established upon departure. So anyway, I had some fun updating some of these features and hardware elements, and then of course the landscape also got the benefit of some actual data from Mars about the color of the sky and the geology of the rocks. So I did an update of Exploring Mars, which you can check out on my website, I guess, pascal.net, if you have nothing better to do. That is.
Well, and it's funny you mentioned the updating of the rocks, because I remember Bonistel was a little irked when Apollo 11, when the Apollos started orbiting the moon, and we started getting really good, clear photographs. And he said, "Hey, that's not how it's supposed to look." Isaac, I just got a question asking, and I'll paraphrase it a bit. I've watched your channel. I can't, because I know how hard it is to do that kind of production, especially when you're kind of single manning. I don't know how you find time to do anything else, but what other space-oriented activities are you involved in when you're not doing your videos? Is it just strictly research and interviews?
Well, we do have time for, my wife finds time for me to do all sorts of other things, I should point out. But I would say organization-wise, if it's an interesting project, we try to get involved with it, even if it's just a little bit. You never get to dig into somebody else's projects as much as you'd like to. It's the funny thing, when you're younger and you're new to it, you're looking to get involved in a project and you have all the time in the world. When you're older and you know everybody, you know all the stuff you can get involved in, but you have time to do either fun actual job. So we get involved with a lot of game development, a lot of space art, a lot of early development projects, looking at things like how we do construction robots in space was one I got an email about today. And the answer is I never have enough time to do even the episodes, let alone help on all the projects I'd like to. I think that's probably something everybody here is familiar with.
Yeah, probably.
Well, questions are starting to roll in, and Isaac, I'm betting you have an answer for this one. So I'm going to show the question from Rondra.
How did this is for the
How did the gunfire? Yeah.
It was physically mounted on it, couldn't turn. They probably just flushed some oxygen in the barrel when they shot. It's very quick.
They'd have to have an oxidizer inside the chamber or something like that. Right?
I think people miss in sci-fi is when you stick your finger over the hole to prevent the air coming out thing, people see a hole in the side of a space station and get sucked out the thing. It's a pretty slow process, and the air comes out at about Mach speed, whereas the bullet's coming out at about that too. So I don't know how they did on that one, but it wouldn't be that tricky to put in like a solid oxygen cable, just flush some oxygen in, I should think. But
yeah, and just so it's said, when you think of a bullet, there's no oxygen access into bullet casing. It's enclosed when it fires, so I think it's self-oxidizing. And God knows the Soviets had a lot of bullets, so I think they were well set for their experiment. Dave, you got another one, or?
Oh, yeah, absolutely. I've got a stack growing here. So this is from National Space Society's Seth Potter. I'm going to bring it up. Do the panelists have any thoughts about how settling the moon, settling Mars, and settling O'Neill-type habitats at L5 or elsewhere can enable each other, thereby bootstrapping space settlement? So who wants to take a shot at that one?
We just had an article in Ad Astra about that. I'm trying to remember who wrote it.
Well, I think the key thing there is there's a lot of commonality. I mean, in all those places, there's a lot of common stuff that you got to be able to do. And, there's some differences, what works on the moon or Mars, may not work in an O'Neill colony and vice versa. But I think that, with the food, the water, the air, radiation, there's all kinds of common problems that you've got to solve. And, the solutions may not be identical, but hopefully they will be at least synergistic.
Yeah. Well, that's the whole idea of going to the moon first, is that we'll learn so much that'll translate into going to the Mars eventually. So regolith is very similar and how abrasive it is and things of that nature. So yeah, good question, Seth.
Well, Hank knows something about habitat emergencies, don't you, Hank?
I know something. You know,
you're a little closer to home, but
yeah, everything that I think everything we learn about building a habitat on the moon will work on Mars. You know, and we are looking into centering in situ resource utilization stuff by grinding up the Hawaiian lava rock, which is 96% the same as the regular water, and then centering it into stuff. We started by doing trying to do landing pads with pavers, and it's all interesting stuff, and eventually it's all going to be useful on the moon and Mars. But you were asking me about emergency stuff.
Yeah, did you have you had a couple of slightly urgent situations at your habitat at one point I read about. I think there was a generator failure, something else. I mean, not serious on Earth, but elsewhere.
No, I know. But the one mechanical failure that we had wasn't actually a mechanical failure. It was just somebody woke up early and saw that the lights were out, which means the batteries had drained for some reason. And in the dark, they went in to try to fix it. And they managed to open up the inverter and find out that there was still quite a bit of a charge on the batteries.
Oh boy.
Anyway, I mean, this is like if you went into someone's house who had an electrical panel and you unscrewed the electrical panel and you stuck a screwdriver in there. It's on that level. So so that kind of, he got a shock and he went into shock and yeah, there was a whole nonsense around that. If he just waited a half hour, the whole system would have like booted when the sun rose, because we're 100% solar at high seas, a backup of hydrogen. So we have fuel cells that charge up the battery in case there's not enough electricity for some reason. I don't know what the reason was that the lights out, but every once in a while it'll happen. Somebody maybe turns on a space heater or who knows, and leaves it on.
The shocking experience, no doubt.
Shocking experience, yeah. So it's the reason we keep somebody on, in whatever crews we have now, we always have somebody from our team that knows what they're doing, so that people don't do dumb things.
Yeah.
Well, it's easy to judge people that touch live electrical things, but knowing that I'm in a room full of very curious people, I bet I'm not the only one that notices a kid that a screwdriver blade was almost the exact right size to fit into a wall socket. It's a bit of a surprise the first time you do it. If you do it the second time, then you're dumb. Dave?
Yes. Speaking of shocking experiences, we have some questions about ISDC. So, Aggie, can you help us with this one? What should press release titles be from this ISDC? Is anyone writing this? Would it include something on space solar power? Oh, you're muted.
Sorry. We have a lot of press releases that came out prior to this ISDC. There will be others that will come out post ISDC. So we're pretty good about putting press releases out there. We announced a number of the key speakers that were part of this, and this is going to be repeated in 2 weeks for other time zones. Just so everybody knows, we have a big contingency in India that wants to see this, in Eastern Europe. So in about 2 weeks, we're going to repeat it overseas very early in the morning, so it's their afternoon and evening, and we'll have a whole other series of press releases. So we're pretty good about putting that stuff out. I don't know if it included space solar power. Do you remember that, Rod? Whether any of the
not specifically, it was mentioned in general terms, but it's probably a good idea to put one out because that was a big part of this. And I thought, having seen it a couple dozen times because I was editing the streams, a couple of the student presentations were really outstanding, and it was amazing to me. I mean, I'm in my 60s. I'm still trying to understand half the stuff, and I see these high school kids that are jamming through these difficult engineering projects, and one team drew a patent out of what they were doing already. And I thought, Okay, that's humbling. So, yeah, we'll put something out for them. That's a good idea.
Yeah, we've had a number of students who are part of a space solar power competition that's got some pretty interesting prizes and trips to Dubai and things like that. So that was through Space Canada. So there were a number of interesting things that came out of the space solar power part of it. But we are really good at putting out press releases, thanks to Rod. More than I've ever put out on anything else. It's quite amazing how many we put out there.
Yeah, and I think, Isaac, didn't you do one long segment on space solar power in your series?
Yeah, power satellites. I did that one with Chris Holland, actually, on the designs for that. He used the old Skyline and stuff. It was probably one of our most referenced episodes because it kind of changed me getting the research on that one from thinking that power beaming was a bad idea to a good idea. So,
well, if there's anybody here that can tell us how hard it is to power things with solar panels, I guess that would be Scott Bolton, especially out by Jupiter, right?
That was a challenge. And there were many that thought we were crazy when we first thought about that and said, okay, we weren't, of course, originally we were thinking we'd go with a nuclear power, but we were worried that it wouldn't be available. And so we started looking at solar, and of course we had to test and validate the cells that could work at low light and low temperatures. But there were a lot of people that thought we were nuts, but we put that in. And then, of course, once we were selected and we flew it, now you see Europa Clipper and ESA's JUICE mission, both being solar powered, going to the Jupiter system. So we kind of paved the way. So I'm a big believer in solar power. I like to say sometimes that we were green before it was in to be green.
I'm sure you all saw the pieces that Rod did, the solar power videos. We've got a few different versions of them that we're putting out everywhere, and they're just incredible. They're beautiful pieces on space solar power. So if you haven't seen them, you have to, and we've got them going every place. So that's another thing that we're doing in addition to press releases out there. Oops, sorry about that. Is doing things like that so the world knows about it.
Yeah, it's called Dear Earth. If you have a chance, it's worth watching. Dave, what's next?
Well, we have a question from Alif, who is our social media expert at National Space Society. And she says, what is the soonest do you reasonably see passenger vehicles making the Mars transit? And, based on space starship developments, I think we got to see a cargo mission first, and it'll follow shortly, right?
I see Pascal grinning. Go ahead.
2032.
2032.
Put down an act. Okay, we're taking
all
it back.
Right. And you heard it straight from the expert. So
what about the moon?
Put that on the calendar.
Oh, wait. We're already going to the moon. Isaac, what's your shot?
What are we defining passenger as for 2032?
Humans.
It could be the most. I'll go with Pascal on that. Might be a bit optimistic, but 2032. Yeah.
Okay, Bruce, you've been watching
2020s. It's too soon, and 2032 sounds plausible.
I think everybody is underestimating Elon and his tenacity. There's what's called Elon time, but he's getting better. So I'm thinking, 2026, 2028. I think he has a real possibility of putting people on Mars.
I like that answer. By the way, just in case anybody was wondering, that's not a picture of Alif down there. I believe that's a picture of her father in a naval uniform. So Alif is substantially more attractive in many ways. What's next, Dave?
All right. Let's see. We're going to go to Robert Allen. Hi, Isaac. Hi, Isaac. We want to encourage you to do a video about the future of spaceports on Earth. So do you have that in the queue yet?
Well, we did do a spaceports in space one time back. We haven't actually done one on Earth. And that does sound like a fun topic, but it's going to be so dependent on, like if you're doing a mass driver, Ecuador looks really nice. If you're doing a space elevator, the equator looks nice. Other places, it just depends on what your technology is for getting into space. And I don't know what the spaceports of the future are going to look like, though, yet. It might be a fun episode to explore.
Yeah, that will be a little creativity involved there. let's see, moving down here. Well, Alep's got another one, but I'm going to take Bruce McKenzie. The exhaust plume. Oh, we did talk about this exhaust plume aspect.
It's before we came on, yeah.
Yeah. And during lunar landing, could put gravel into lunar orbit, which might hit you in the back of the helmet after one or more orbits. Let's see who. I'm reminded that Sean Mahoney from Maston Space Systems talked about a mission coming up in 2022 that's supposed to fly with the first Artemis test mission, where they're planning to spray a mat on the regolith before the plume actually hits the surface. It's a way to impinge the debris from blowing all over the place. But who wants to take a crack at this question here? How do you prevent?
We're missing the main expert that I know about this topic, who's Phil Metzger.
Right.
But these are taken into account. In fact, in discussions right now about the Artemis base camp, for example, there are discussions about not only having Starship launch pad and landing site on the moon be some distance away from where you would have your habitat structures, but it would be behind an obstacle and possibly at a slightly different elevation to precisely get sort of circumvent this issue of having a large amount of your dust crash back onto you after a few orbits around the moon. So it is an issue.
So Phil also wrote a recent paper. I just read a little bit of it about the amount of thrust needed to land a large Mars lander that included people, presumably, would probably be sufficient if you pick the wrong spot to land to gouge out enough regolith below you that the rocket would fall into its own crater, which would really be a really bad way to land. And I guess especially if you've got something like Starship. Bruce, how do you think do you have to just send robots to build a landing pad first, or what do you do to abate that?
Well, if you notice the design that Elon and SpaceX is using for the human landing system, the landing thrusters are not at the bottom; they're up higher and they're angled so that you kind of get away from that problem. I mean, back to Bruce's question there. The issue here isn't like you're gonna do this and it's going to come back and hit you. I think the whole issue here is, are you just going to ruin or make untenable the whole lunar atmosphere for whatever it is you want to do? And so I think this is where we need to be more thoughtful. I have the same problem with asteroid mining and things like that. How are you going to do this in such a way that you're not just creating massive amounts of zero gravity junk piles, and stuff like that. So there's just some thought that needs to go into this. I mean, it's a doable problem. You just need to do some good system engineering.
And I don't know if it was thought about before this or not formally, but I do remember the 1950s when the U.S. Army was working with von Braun to, Isaac's going to chuckle when I say this, on Project Horizon, the 20-man Army base on the moon, where we were going to stand off from the communists with nuclear bazookas and so forth. One of the things they were trying to figure out was how to utilize small arms on the moon. And there's a lot of discussion about, gee, if we fire a bullet square out in front of us at some soldier and miss, is it going to come around and hit us in the back? And I think the odds are probably pretty small, but I guess they could go into orbit if they're at the right velocity.
I think the muzzle velocity of most rifles, though, is just Mach 1 or 2 Earth speed. I don't think that's anywhere near enough for the moon orbit. Is it like 2 kilometers per second? Or can anyone remember what it is off the top of their head? The order velocity of the moon?
Let me think. No. I don't know.
I think it's at least twice the typical rifle speed, though. So
well, and the result of that was they decided to do air guns instead, because they figured, I don't have to kill anybody, I just have to puncture their spacesuit.
Yeah.
That was
what I meant to say is, if you take a look at the Chinese lander on Mars that brought the Zhurong rover onto the surface, if you look beneath the lander in pictures that show the ground right underneath the lander, you will see a pit that's several tens of centimeters in depth and in width that was essentially excavated by the lander thrust exhaust plume, basically. And that was a small thing. That was just, I think, 7,500 newtons.
So we'll go back to Dave for the next question, but just for a quick moment here, because we're just a little past the halfway point, I want to give Aggie a chance to talk about our Society's magazine, Ad Astra, now in a bookstore near you.
Yes. Yes, Ad Astra is in many, many bookstores, about 800 bookstores across the country now. And next issue will be out fairly soon, and we're going to be in the bookstores for the next year or so, and hopefully well beyond that. And just about every major city and lots of minor cities. And many of you have written articles for Ad Astra, so I thank you for that. And we are going out in a big way. So that's something new for the National Space Society and Ad Astra magazine.
And it's the best deal out there because it's not full of ads. There you go. Look at that.
There you go. I was going to look for one right here. I'm glad you had
one. The other space magazines are 40 pages and 15 of them are ads. Scott Bolton has to leave us soon. He has another commitment. Thank you, Pascal. You're a pal. Scott, did you want to say anything to wrap up?
No, it's been great to share this with all of you. I'm fans of all of you here. And
the other way around, but okay.
Yeah, right.
Well,
who's
also,
the famous guy here?
I thought about the debris issue, that's brought up. It's something we have to certainly worry about at the Earth, right? We learned our lesson early on, putting out a lot of debris into Earth orbit and realizing that there's no way to remove it. So I think it's really important to think ahead as we start to think about the moon, Mars, and other places, that we do things wisely. And that it doesn't just take thinking through it, but it means that we have to have some sort of cooperation and organization between the various entities that are going to go off and do things, because it only takes one party to make a serious mistake that we all end up screwing things up and suffering. So it's institutes and societies such as this that help to make sure that kind of coordination can happen. And so I appreciate the question that came in about that.
Just could you give us a quick preview of what we should expect next from Juno?
So, okay, so I think toward the end of July, we fly, we're in about a 45-day, 48-day orbit right now. We're at 53. And so we'll fly by a little bit more distant to Ganymede again. This time we'll get better shots of the poles and from far away, and then go over the pole of Jupiter again. And we're getting closer and closer to the poles. And so one of the exciting things is eventually we're going to be able to map out those polar cyclones with our microwave instrument, which we'll see underneath to see how those routes are. And I'll give you one hint of something that is fresh science that we just got, which is the last time we went over Jupiter, we took images of that North Pole, and it looked like the cyclone, which 8 cyclones were in an octagon shape. It looks like that's breaking up. We thought we saw that happening once before, and then the next time we came around, they were back together. But it looks like this time maybe we're watching a change. So the next orbit is what's going to tell us if that's really true or not. And of course, that feeds into the science. We don't really understand how those cyclones get made, how they're maintained, what's really driving them. And Jupiter is the only, we haven't seen that many giant planets, but Saturn doesn't look anything like this, right? So it's a great, I like to think that we're going to start doing a monthly weather report on Jupiter.
Are there limitations to Juno besides financial? I mean, you have solar power to keep the buses going, but what about fuel for navigation and things? What is the upper limit on that?
So all of those, I mean, there's a number of resources that any one of them could be the limit. One, and setting aside finances, because NASA's probably not going to be the one that's the limit to us if everything's working. So you have fuel, right? Because we have to use the fuel in order to point the antenna to the ground. Even if you're flying around okay, and you're able to take data, if you can't downlink it and point the antenna at the Earth, which takes some propellant, then that sort of defines the end of your mission. You could have solar cell or battery degradation, although we're tracking that. And then also the fuel. Right now, our estimate of the fuel is so that we would last another 40 orbits or more. All the way through the extended mission, we added something like 42 orbits, and we calculated that of course, you never know exactly how much fuel you're using. There's a little bit unknown, and you're aiming at the 90%, and you hope that you're more efficient. So far, we've been doing really well. The thing that we've most feared and has generally thought to be the thing that will really limit Juno is the radiation. The radiation at Jupiter. And as our orbit goes through there, we're going into harsher and harsher radiation regions. We can't stop that. There isn't enough propellant or rocket power to actually undo what Jupiter's gravity field can do. We're just mere mortals. Jupiter is a giant, right? So the radiation will probably get us at some point, but that may be a graceful degradation. That's what I'm hoping. Certain things will start to have problems, but we'll still get to be able to work others.
Yeah.
Well, we just have to keep our fingers crossed.
Yeah. And Scott's time is up, so thanks for joining us. And
thanks for having me.
Thank you so much, Scott.
Thank you.
See you, Scott.
Bye-bye.
Dave, I have another question from space.com from Daniel Yont. Whether orbital moon or Mars should we use inflatable or hard shell habitats, I think he's saying, and a mix of module types. Also, what data has been gained from the ISS inflatable Bigelow module?
Well, let's see, Pascal, this sounds like your turf, right?
Yeah, I'm a big believer in inflatables. They work well on station. It's too bad that Bigelow Aerospace folded, but I think there are follow-up activities that are involving inflatables, at least conceptually. The trick, of course, is that inflatables in contact this is generally true with any piece of space hardware. As soon as you get in contact with surface materials and surface operations, you're dealing with a much more abrasive and unpredictable environment. Having just inflatable structures on Mars earlier on, I think, would be a bit of a mistake. I think we should sort of have the same approach where we would start with a few modules that are really rigid and robust, buriable bags for radiation shielding, which is really the most effective way of getting radiation shielding at the surface of both the Moon and Mars. But then over time, really understand you need more volume, and one very efficient way of expanding the living space is to use inflatables. But do that incrementally, not go inflatables up front before you really have a thorough first-hand understanding of what the surface environment is like and living and working there.
Well, I guess I would extend that question, and maybe Isaac or Bruce, you know more about this, I imagine, but my understanding is that actually hard shell metal habitats can actually make radiation problems worse because high energy particles hit that and then they fall into more smaller particles and actually become a larger risk. So if inflatable, or as Bigelow preferred to call it, expandable, perhaps a better way to go in the long run.
Sure. Well, as Pascal was saying, nothing's ever going to beat just dumping a regolith on top of your habitat as cheap radiation filler. That is one thing I like inflatables for, is you pop the thing open, you get in place, and you can probably get away with barely anything, especially on the Moon, and just sealing up as you go, kind of not long-term being kept up by the inflation. It's just that's what's there to hold the structure up while you back over by the wall with shell on top of it. But yeah, some types of radiation shielding can actually make other types of radiation worse.
Yep. And in pop-up inflatables are actually a really interesting concept, because we were thinking of using them. In our ConOps on Devon Island, for example, we have these temporary structures that we erect, some of which we would like to see implemented in the form of inflatables, because they would come in really handy. So these would be temporary emergency shelters that would be pop-up things that you would not spend a lot of time in. They don't have to have a very long lifetime, but they would really provide shelter in a contingency. The other thing is, as far as the transfer to Mars and back is concerned, inflatables, if the station experience is sort of confirmed and transferred, I can easily see a crew having the benefit of an inflatable or an expandable, like they call it, an expandable habitat for the journey to Mars and back. And that would actually buy you a lot of volume in space.
I have a quick question for Hank. We were talking about spaceports earlier, And I've heard bits and pieces about something potentially being sited in Hawaii eventually. Do you know anything more about progress along those lines?
Spaceports?
Yeah.
So we were trying to get Kona to be a spaceport, and there's all kinds of how can I say, headaches involved there because you're competing with commercial flights. And if you build a spaceport, there's going to be times when you can't fly commercial because we need that window while something is taking off, and even like horizontal takeoff and landing. In general. So, for example, Virgin Galactic comes in glide, and it only has one shot at it, so you can't have another plane on the runway during a flight in case that something goes wrong with the plane and you can't move. Then you won't be able to land, a horizontal. So we haven't really had a lot of good progress there in terms of the spaceport in Hawaii. But don't count us out. We're working on this.
Well, I don't know if access is a problem, but I once stopped at an absolutely horrible place called Johnston Atoll on my way to the Central Pacific, which is down just off the equator.
Wow.
It looks like a dining room table in the middle of the water, and it's just big enough for a runway. And so our plane landed there, and we got out, and there's a little tin shed over in the corner, and that's about all there was. And I said, "What do they do over there?" And he said, "That's where the Army burns their chemical and biological weapons." I said, "Gee, are they doing that today?" And he said, "I don't know. I don't see any smoke." But I guess or it might be a consideration if transport wasn't a problem. Dave, what's next?
So this has to do with radiation in transit. This is from Cornelius Dutcher. What breakthroughs are still necessary in radiation shielding before we have lots of people going beyond Earth orbit? Isaac, you want to take this one?
Cheaper rocket fuel. Where space radiation shielding is concerned, there's a lot you can do with magnets. There's a lot you can do with special materials. At the end of the day, the thing that helps the most is just raw mass. So anything that lets you handle certain materials like hydrogen better to actually not let them escape, which might go with graphene, would improve that. Anything that lets us just pack more mass in and move it economically would help with that. There's a lot of individual things you do with magnets, electromagnetics or permanent ones, but at the end of the day, cheap rocket fuel is the one that really solves that because it lets you get thick armor.
Yeah. And then water's rocket fuel as well. So if you jacket the spaceship in water or ice,
Mm-hmm.
Pascal, you want to take a shot at making an ice ship?
No, I mean, I agree with that. And in fact, water, both contain hydrogen, and hydrogen is a good absorber of most of the high energy radiation that we're worried about. Of course, you need 2-3 meters of it, but you can imagine a transfer vehicle to Mars with its walls serving as food and water. And I often explain in talks that if you follow what happens to the water, it turns into urine or sweat, and then you recycle it. We do that on station already, so you can maintain that shield of water. As far as food is concerned, you consume the food, and it turns into, I guess, poop for lack of a better word, and that is still a resource in deep space because it is replete with hydrogen. So you want to essentially carefully collect your poop in Ziploc bags, emphasis on lock, and that goes back on the wall. That goes back on the wall, really, where you took the food in the first place. So I do envision this exercise that people on station don't have to do because, of course, on station you're still inside the Earth's magnetic field, so your radiation environment is very benign. But if you're in deep interplanetary space, you're going to want to manage your radiation shielding. If it comprises food and water, you want to manage that. And by the time you come back from Mars, you're going to be surrounded by essentially a year's worth of yours and everybody else's, crap.
I can envision a whole series of new cliches being generated by
Well,
this activity.
I want to do the post-flight interview with the first crew member that got assigned something worse than KP duty for a year and a half onto Mars. Like, all right, you've got.
But one of the things is the guys at NASA Ames are actually came up with a concept called the wet wall, and they actually built the life the regeneration system, the ECLIS system, into the walls of the spacecraft, and you actually do use that as storage and processing, and then all of that plastic that's in there, and the processing equipment, and the actual mass of the wet material, the water there, as was mentioned. So, and again, if you think of like the expandable habitats, which have a thickness to them, then this starts kind of looking interesting. So there are some synergies here if we get a little creative in our thought processes that really could be attractive.
I have a little high sea story. In the very first mission, we had flushing toilets, which were not very realistic because we ended up having to send truck up there twice a week to collect the black water. So we switched to a toilet that has sort of like
an incinerate.
No, anyway, it's a toilet that has wood shavings and bacteria.
It's a biodigester, yeah.
Biodigester, and then they'd have to turn it over after doing number ones, make sure that, and then pour some more powder in on a regular basis. Well, there was a crew who actually didn't follow the instructions, and this biodigester turned into a cesspool. And so they contacted us and said, "What can we do?" I said, "Well, you guys are on Mars, so
figure it out.
Really nothing we can do to help you guys. So you're going to have to figure it out." And they end up.
What would Mark Watney do? Yeah,
they're going to have to. So
I'd be really curious how long it would take someone to come up with a way of making bio out of that or something like that.
They have to do it the hard way.
You're the taste tester, Isaac. Okay. So, Dave, guys, new trajectory here.
I got to say, they dealt with it, and future crews heard that story, and they were very careful after that.
Here's your beer. Have a good time, newbie.
Hey, our old Fred, who's been working so vigilantly in the background, vigilantly, is our Fred Becker. Fred wants to know, and this is kind of related, is there a way to chemically or otherwise treat Martian soil to make it safe for people?
Yeah, so the main issue with the Martian soil, right? I mean, it's sort of three factors. One is abrasiveness, which is believed to be less than the lunar regolith because there is some weathering on Mars, but it's still going to be very abrasive. So if ingested, it will tear up the tissues of your lungs. The second issue with the Martian dust is that it might be extremely fine grain, or at least have a component that's very, very fine grain, in which case it will clog the pores of your lungs. That's essentially Miner's disease with coal. It's called silicosis. So that is a problem that's very hard to deal with, the very finest particle size fraction of the Martian dust. So that is not toxicity, that's just mechanical issues with the dust. And then you have the chemical toxicity, which is the peroxides and the perchlorates. The perchlorates in particular will attack your thyroid. The peroxides will just be an irritant to your skin, to flesh, to tissue. It's just, just think of hydrogen peroxide in solid state. Okay, so that's what we're dealing with here. But the good news is that both the peroxides and certainly the perchlorates are washable out of the soil. So if Mark Watney had done that, he would have been growing potatoes on Mars. It would not have been poisoned by perchlorates, and the story might have been, might have worked better. But in any case, it's a process. I mean, imagine having to wash, tons and tons of water. If you come, sorry, not tons of water, tons of soil to clean it, and in order to make it non-poisonous for you to grow food. So not immediately, I would say.
Yeah.
So
the perchlorates are also a valuable resource too if you extract them and put it in a form of like rocket fuel or things of that nature.
Exactly. Perchlorates can be used as rocket fuel. That's a good point. So you could recover that. And again, it's a whole process that would have to be set in place for you to do that. Yeah.
So I've often thought we could make a wonderful sequel to The Martian, where Watney wakes up one morning realizing, oh, his whole escape was just a dream. And he's actually stuck on Mars, and not only is he being poisoned by his quarter acre of Martian potatoes, but he also suddenly realizes that taping a big piece of plastic sheet over a hole in the side of your habitat. It doesn't do much when you're in a near vacuum and you can't breathe anymore. It'll be a very short sequel, about 4 minutes. Look kind of like that scene out of.
To be fair to Andy Weir, whom I happen to know and lives in the Bay Area, he actually was aware of several of the shortcomings in his story, because he obviously is really technically savvy and understood that there were some issues, but his publisher did not want him to fix those problems, and so there you go.
In the grand scheme of sci-fi hardness, I've put at least a 9 out of 10. So
I have
solid.
an Andy Weir story. So after our longest mission, which was 12 months, 6 people staying in our habitat for 12 months, we invited Andy Weir to come to Hawaii for the when the crew coming back to Earth. Unfortunately, Andy Weir doesn't fly on planes, so that never happened.
Yeah, right.
We found out when we invited him to ISDC that he doesn't particularly like flying on planes.
No,
but he's a great interview on Zoom.
Yes, as long as he doesn't have to get on a plane anywhere. I wanted to thank everybody that was a part of ISDC, because we had over 60 segments as part of ISDC, which was really quite remarkable. And it was a lot to put together. It was a lot of time spent doing the interviews. We can see how interesting it is doing something live. So we decided for a 3-day event, we were going to pre-record most everything and organize it and put it all together. So there was a lot of work that went involved in not just the interviewing, but the putting it all together, the speaking to everybody, the editing of it, the organizing of it. And you're seeing a few of the people here that were involved in that team, but there were a number of others as well. And I want to thank everybody that was involved in that for all the hard work. Yeah, it was a lot of work, a lot of fun. And, when you hear numbers like 50,000 people saw some part of it, it's exciting, and it's really something that needs to be congratulated. But yeah, I think we'll stay away from doing 3-day virtual events for a while.
Yeah, it's funny when we do this in person that the 4 days seem to breeze through because you're meeting new people, but doing it all in a virtual environment, it's a bit of a grind. And Rod, I don't know if you want to say the marathon hours you racked up doing this.
No, it's about 300, but I will say, the beauty of something live is you get to talk about poop in space. If you have Pascal on your call.
That's true.
Program that, so that brings a whole new angle to long duration space flight for me.
We don't even have an astronaut on this panel that we went
If there
there.
are kids watching, don't try this at home.
So we're really counting on next year being in Arlington, Virginia, and everybody being together. And hopefully all of you will be able to join us there and doing a 4-day full-scale ISDC with everything that involves, and having lunches and dinners together and enjoying lots of activities. And, really getting to know each other, which is what you can do at a live event that you don't get to do the same way at a virtual event. So I think it turned out really well. I think it was a lot of hard work and a lot of time, more than we ever imagined. But, well worth it. And the other really nice part of this is it goes on. It lives forever. We'll do it in a couple of weeks for another marketplace entirely, but the content of it is not going to go away. People can see it endlessly. We'll have hundreds of thousands of people seeing parts of the 3-day ISDC over the next several months, many months. So that's kind of the nice part of it. And you can pick and choose and see different segments of it over again. So there's some really wonderful things about it being virtual. Yeah. And then there's other.
We will eventually segment these pieces up, but if you want to see the entirety of day 1, 2, or earlier today, I believe they're up on the space.com YouTube channel already.
Yeah, and the NSS channel as well. They're already there. So, they're starting to rack up numbers on their own. So that's fabulous. What do you say? Maybe 2 or 3 more questions?
Yeah, if you got them, sure.
All right. Yeah, we got some good ones here. All right. This is from Stefan Lite. There are a lot of good work being done on terrestrial high-density vertical farming. Has anyone studied how to adapt that to space, and how well you can feed folks if you use the best current methods? Vertical farming. Isaac, I think you've done some work on that, right?
We did an episode on space farming specifically. We've done vertical farming in our episodes on ecologies, but For space farming, we just try to look at what would you be doing in terms of, do you have your light source on hand from the sun? Are you getting that your 24-hour light source? Do you need to do something different with the moon? Do you need to provide gravity? How much gravity by rotation, for instance, does a planet actually need? And it works out to be really dense. If you got the right conditions, you don't need that much power to go things on. You got that photosynthetically calibrated light, mostly red, a little bit of blue, and some other things. Otherwise, though, you just pack it in there, and you can. I think we worked out like 2 kilowatts per person. Might be as little as you need to actually grow food, but that was a very theoretical maximum kind of number. So there's definitely some options there for really dense growth in space.
And there's some products that are being grown right now that are highly valuable on the market and have really taken farming in new directions. That'd be the cannabis industry. So
why did I know you'd say that, Dave?
And there's controversy number 2. So Hank, have you done any of the
beyond space no cannabis?
have you done any of this kind of stuff at the high seas?
Well, we did a little bit of. First of all, I think the amount of volume that you actually need to make a dent in the diet is multiple times the size of the space we have assigned to humans.
Yeah.
So we have 1,200 square feet, a 1,200 square foot dome. I think that we need like multiple domes that size to actually feed people.
Right.
Having said that, we did grow lettuce in this little vertical. It looks like a little tree, and that little bit of fresh veggie that was harvested, I think once a week, was hugely. How can I say? It was a huge success because everything else that they eat, it was there from the beginning of the mission, so it's freeze dried. Add water and make whatever, and so that gets old real fast. Having a little bit of fresh veggies is a big deal. So yeah, we're looking at doing more of that and expanding that, and maybe having another dome that does just for food kind of thing.
So there's several companies that are actually looking at this that have at least are studying this on Earth. One that we talked about at the Space Portal many years ago was Freight Farms. They're out of Massachusetts, and they do vertical farming in old shipping containers. And they were highly intrigued about this, about the possibility of putting one of these things on the moon. And then Orbital Farms here in California is actually looking at this, and as their name implies, they're looking at actually, doing stuff in orbit. And there is a little mini facility up on the ISS right now where they're growing vegetables there to Hank's question, that really, even a little bit of variety in the diet can be very important psychologically as well as nutritionally.
Yep.
So Dave, how many more questions do you have? I've got one more.
This one's from Aaron, our video production wizard. So let's give Aaron a shot here. And Aaron, thanks for all your hard work. What realms in regard to technology, development, etc., have a society in space have the biggest gaps in advancing to make that a reality in terms of making food, logistics, and the like?
I think we were just talking about farming. I mean, you look at Biosphere 2, if you've ever been there, they have a huge footprint, and not everything's devoted to food production, obviously, but because they're experimenting with various ecological zones and biomes and so forth. But they had a real problem sustaining themselves on the amount of acreage they had, and that represents a pretty big footprint for a settlement.
Food production for sure, and also waste management. Waste management is society, that is a huge issue in places where you don't have running water.
So according to Bryce Meyer, that's all connected, right?
Right.
Yeah. One of the guys that works for me in Pisces, the Pacific International Space Center for Exploration Systems, spent 8 months in Biosphere 2, and he said 8 people spend all of their time growing food, and they were always hungry. And that is no way to run a space colony. So
waste management is not really a source
automation.
Of farm, so,
yeah, we need to robotically grow food and just use the time that you spend in the greenhouse for entertainment or psychological, whatever, but it shouldn't be somebody's job. Growing food shouldn't be somebody's job. So we have to figure out that robotically. And I've been to the Netherlands. I'm originally from the Netherlands, and doing a lot of stuff there about growing vertically and robotically and all that kind of good stuff. Labor is expensive.
It's the perfect example, though, of getting those investment kickbacks down to earth. You know, if we can get automation up in space to grow food, think about what that's doing down here. You know, think about more automation on being able to grow crops other than grain or wheat automatically. Berry crops or things that need something delicate to come. Huge payoffs for us. Huge payoffs. And that's one of those examples of going back into space and vice versa. Not just Tang, though I like Tang.
So I have a question here from Deborah Elzy. I think I'm pronouncing it right. Asteroid mining, is there gold in them rocks? And then she followed up with actually platinum. And I remember talking to Steve Jurvetson about this, and we kind of agreed that if you bring back an asteroid full of platinum, that's great, but the market kind of goes kabang, and suddenly your platinum isn't worth as much anymore. But what are your takes on asteroid mining, the current state of that idea?
Well, I would say the big thing to remember is an asteroid by itself doesn't necessarily have a ton of valuable minerals easily accessible. If you take apart Mount Everest, you're going to get more gold probably than there is the entirety of Fort Knox several times over again. And you don't really want to be baking it back out. You want to send that all home. The other use of stuff is great for maybe construction purposes, but the metal itself, you probably wouldn't crash the market on stuff like that anyway, but you'll be getting out bits by bits. You're not just going to come home and say, I got $2 quadrillion worth of gold. That's just not how that works out any more than you point at something like Montana and say, hey, look, there's $2 quadrillion worth of gold in Montana. There probably is.
So let it be remarked here today that Isaac was the first person to advocate dismantling all of Mount Everest.
I have.
Or hollow it out, leave it
But
there
back
so you
in
can look at it.
2016, the NSS did a workshop that actually Steve Jurvetson hosted for us. And one of the topics that we worked on at that workshop was this idea of a space commodities futures exchange. And Bruce Cahan led that up, and several of us participated in that. That has proceeded on, and they're actually in the process of trying to do that right now. But the economics of this are brutal. It's one thing to have an asteroid that has a lot of valuable materials in it, but they're diffuse. It's not like there's huge gold nuggets, or platinum or anything else there. You have to process, if you'll pardon the pun, an astronomical amount of material to get at that stuff, and then to get it from where you have it to where there's a market for it. What's it going to cost you to get it from here to there? And this is where the transportation costs come in. So it sounds really cool, and I would really like for that to be true, but I have yet to see that really pencil out. But I'm ready to be pleasantly surprised when somebody does.
Yeah, I actually think that there's a period of a history 3.5 billion years ago when the Earth and the Moon were bombarded by asteroids. And on Earth, we lost them all because of subduction tectonics. But on the Moon, they're all still there. So if I was going to go asteroid mining, I would go to the Moon and mine them on the Moon. Yes, it's probably diffuse, but we can have infrastructure on the Moon that processes a huge amount of lunar material and extracts those materials. And so if we can find it on an asteroid, we'll be able to find it on the Moon, and the Moon will have infrastructure within.
And in some of these things, gravity does help.
Right. I mean, just imagine going far away and trying to mine from some rock that has no gravity. That you have. It's just way more complicated than mining the Moon.
I want to second something that Bruce said there, because space resources, of course, is a whole topic. You could spend a whole conference just on that. But I think we've had the tendency lately to cheapen the meaning of the word resource. Just because you have an element or compound that you can use, that you normally use on Earth as a resource, just the fact that you have it up there doesn't mean that it is a resource. In fact, the truth is, none of these things that are out there are resources for us. until the cost of extracting them up there and somehow putting them to use is going to be cheaper than the cost of hauling them all the way from the Earth. And you take water, for example, even water, which is something that is drawing us to the lunar poles, and we're so caught up in this whole water fever. We should realize that once we have Starship, a single landing of Starship can probably land 100 metric tons of clean, purified water on the moon, if that's what we want. And now you have 100 metric tons of water sitting, on a water tower, with a tap at the bottom. I'm exaggerating, but the point is, at what point in our future are we going to have 100 metric tons of clean water extracted from the polar region sitting where we want it to be on the moon for us to do stuff? It's, my guess is decades and decades from now, not a few years. And that's not to say that we should not be pushing the boundaries of prospecting and resource assessment. So we are doing the right thing, for example, with Viper, that's doing prospecting. But we're still a long ways away from knowing that we somehow have an economy there that is to be seized. And, not to mention that 100 metric tons of water that's sitting on Starship can be recycled. So it's not like you just use that once and then you throw away the water. You want to make a long use of it. So, and then 2 Starships is 200 metric tons of water, and 3 is 300. And you know what? Each Starship launch will be expensive, but how much will it cost in infrastructure setup, in operations, until we have 300 metric tons of water sitting on the moon waiting for us?
I kind of agree with the concept there, but at the same time, that's also 100 tons of water extraction equipment you could bring on that same flight, and 100 tons of solar panels and ionizers and all that stuff is potentially a lot of water.
All I'm saying here is that, to me, it's not as immediate as what one might think. And for one thing, wanting to set up the Artemis base, for example, at the South Pole is actually setting ourselves up for a lot of challenges that may or may not be the right thing for us to do right this minute, at this stage of lunar exploration, until we know really where the water is and how we can extract it and what infrastructure will really take for us to do that properly. Anyway, just some food for thought. There's a bandwagon here, and I like to keep my head out to make sure that I can jump off of it.
Dr. Lee, Renaissance man and contrarian.
We're going really fast down that road there.
Yeah, I actually don't think that we're going to the South North Pole for the water. I think there are other volatiles that we are going to have difficult time finding on Earth that are existing there because of billions of years of I don't know, comets passing by. But water itself is, yes, that's one thing. But there's other things that were minerals that are grown on the moon that were grown in a vacuum. How many minerals do we have on this planet that were grown in a vacuum? So I'm hoping that we're going to find unobtainium, some stuff that doesn't exist on Earth that we find over there that turns out to be more valuable than platinum, which we could mine on Earth. It's
right. So the turns out is really the key word here, because I agree with you. I'm not suggesting 1 second we stop exploring. I mean, we have to understand better what's out there, and I'm prepared to be astounded by what we find. It's just that, that's different from saying that there's an economy out there waiting for us, and that's all I'm saying. It's one step at a time, and let's be really pragmatic about this.
I totally agree, but I think that some kind of mining is going to be the economic driver for what happens on the moon. When we discover something that we haven't got on Earth at all, oh my gosh, then there's going to be a gold rush.
And that we need, yes.
And that we need, of course, yeah.
But the other part of this puzzle that I think kind of goes back to go big or stay home is having enough people in space where you actually have a market for these materials in space, and not just looking at always bringing things back to Earth for use here, but harvesting resources in space for using in where you are makes a lot more sense than making doing stuff on the moon and then sending it back to the Earth, and hopefully that you're going to make some money on it. But you need to have enough people, and you have to have an economy to do that. So the question is what is that critical mass, and how quickly are we going to be able to get there? And obviously, what language are the people that do that going to speak is part of this equation.
Yeah, exactly. I mean, you look at Antarctica, for example. The Antarctic stations still use only solar power as a local resource and the ice. We at McMurdo we pump seawater actually and desalinate it to provide water supplies to the entire base. But everything else is brought in. We're not growing our food in Antarctica other than for experiments and studies. From an operational standpoint, we're not harvesting in Antarctica. We're not really using local resources. Part of it is because there's a moratorium to not touch the resources, of course. But even if we were extracting resources in Antarctica, it would not be, for use there. It would be just for export to the rest of the planet. And again, it's not 1 second I'm suggesting that we shouldn't explore the moon and really assess its resources. I'm just saying, we have to realize that we could be facing a lot of challenges before any of this is established as economically viable.
Well, we've run well over time, and I personally would like to stay here for another hour, but I know you all have other things to do. So thank you very much. It's been a real pleasure. Thank you, everybody who's watching, for hanging with us for the last 3 days. And I'll just say it one more time. If you're not a member of the NSS, join. And if you are, don't forget to donate. And the website is space.nss.org. Dave, any final words from you?
Well, we don't know what we don't know, and I think when we get to the moon, we're going to learn some pretty phenomenal things that we're all trying to figure out, but really we're not going to know it till we actually start doing things there. So I'm really looking forward to that. And then we can revisit this discussion, and God knows where we're going to go with that. Thank you all very much. This has been fantastic.
It's been a real pleasure.
Thank you.
Thanks, everybody.
Bye-bye.
Bye.